Welcome everyone, this is Michael Gibbs and welcome back to our Cisco Certified Network Associate Training, our completely free CCNA 200-301 course. So the Cisco Certified Network Associate, or the CCNA 200-301, is considered the de facto industry standard for Intro to Networking, and it's the Cisco system's primary Intro to Networking certification. And today we're here because we are running a completely free CCNA bootcamp. We will cover some Cisco networking essentials, and this is network engineer training, network administrator training, or if you're like me and you're working in cloud computing, this is networking for cloud computing, and these are critical cloud computing technical skills. And if you're a cloud architect, these are critical cloud architect skills. And that's why we're doing this Cisco certification training completely free. Whether it's a CCNA for beginners or free network training, or whether you want to think about what is a computer network or networking and cloud computing, that's why we're here with this Intro to Networking course, because we want you all to have the best careers. And whether you want to be a network architect, a cloud architect, an enterprise architect, a solution architect, a network administrator, a network engineer, we've got to know the network and the data center, truthfully. But today we're talking about networking, and we're super happy to do so. So before we begin, let's let you know, I want you to know a little bit about the format. We'll be going for approximately 3 hours today. Then we're going to have a nice, relaxing weekend. And then next week on Tuesday, we're going to start back up 3 hours per day to get all of you cloud hired, network hired, or anything that you want. So I'm so glad that you're back here today. So let's keep it up. Just letting you know, if you've just joined here and you're trying to get your first cloud architect job, please sign up for one of our cloud architect webinars. How to get your first cloud architect job. They are completely free. And to let you know, we try to come out 2-3 times a week on YouTube Live to answer any kind of cloud architect, cloud computing questions you may have to build the best career. So let you know that. And also, if you're looking to get AWS certified, we have a completely free AWS Certified Solution Architect Associate course on our website. If you're looking to take the AWS Advanced Networking, guess what? We have a completely free course for that on our website. And now we have this completely free CCNA course on our website. So go out there and get any job you want. If you haven't read it yet and you're interested in cloud computing, we have a completely free AWS Certified Solution Architect Professional Exam Guide. And it'll start you from the very beginning, and it'll get you all the way to cloud hired, or at least partially the way there, at least the technical components of cloud hired. So download it. It's completely free. My team and I wrote it, and we're happy to offer it to you. So today we're going to get back into talking about networking, which, let's be fair, is one of my absolute favorite topics in the world. And yesterday we started to do some, and today we're going to do a lot more. Ruben, good day. Gaurav, good day. Good to see you. Chijoki, good to see you. We're happy to see you. Earl, CCNA, fantastic. Darstarda, welcome. Hello, CCNA. Eva Doikia, good to see you. Thank you for having that blue wrench again. LM, it's nice to see you, LM. Precious, thank you so much. And yes, the blue wrenches. Eric, welcome back. Hello. LM in Mozambique. If you're the family I know, it's wonderful to see you. And if you're not and you're from Mozambique, it's wonderful too. Theo Q. Sharon, wonderful. Good to see you this morning. Nick B, hello. And yes, thank you for those blue wrenches. Anasaya, yes. CCNA, fantastic. So let's do this. Alexandro, CCNA, Kalispera. Mick B, CCNA. Let's do this. All of you, if you're ready to get started, type hashtag CCNA. And then I'll know you're here. I see some people are already doing it. BD DuPoint, Nike, always wonderful to see you. Marjan, good to see you. Sharon, CCNA, fantastic. Cloud hired, network hired. That's my motto. Sanchin, CCNA, Linux, CCNA, fantastic. Cloud hired, yes, CCNA and cloud hired. Ruth, go cloud, thank you so much. Hello from Gambia, welcome from Gambia. Hasnat, good to see you, CCNA, and Precious, CCNA, and Brian, CCNA, and Sarah, CCNA, and Faisal, cloud hired. I'm all about that. Caroline, good to see you. Angelo, good to see you. Caroline, CCNA, yes. Rhea, CCNA, and cloud hired. And Emmanuel, CCNA, and Millicent with the smiley face, good to see you, Millicent. Stella, Chijoki, and Earl, CCNA. So Georgetta, CCNA, and Sanchin. So Stella as well. Okay, good. Theo Q, CCNA, and Precious, CCNA. All right, Amandu, I love it, CCNA, and Faisal. Cloud hired and CCNA, and Ryan Wagner, CCNA. Fathy, CCNA. Jeannie, CCNA. Jeannie, I'm so happy you're here today. So fantastic. And Mick B, CCNA. Danica, CCNA. And wow, Ruth, CCNA as well. Faisal Cloud hired. So Williams, I'm loving this. Always wonderful to be here, and we are excited to be here with you today. MJ, CCNA, I love this. And Jeannie, it's good to see you. Jeannie, we're going to get involved in some fun routing stuff today. And thank you. We were very happy to help out, Jeannie. So today we're going to talk about routing. And yes, hit the like button. If you're not a subscriber, subscribe. If you know others that want to learn networking or cloud computing, please invite us to the channel. Share it. You know, we want to help as many people as we can. And that's why we do so much free content, is we just know that it's not easy for everybody. Let me make sure my cell phone's muted, because let's just face it, I get a few thousand phone calls per day. We don't want anybody getting in the way of our networking parties. So we're going to talk today about different kinds of routes. And I know I already got us a little bit past some of these things, but that's okay. We're going to talk about it. So I really want you to get the concept of routing. And really the concept of routing is going to be as follows. What we actually do is we take data and we go to the device that has the next level of intelligence. So over here, we've got a PC, and a PC doesn't have a routing table. At least most don't. I mean, sure, you can stick 8 network interface cards in a server and you can route between subnets in it, sure. But, you know, most PCs have one Ethernet card and you plug it into your switch, which goes to your router, and everybody's happy. So I know we briefly talked about this, but I'm going to do it again and again and again in case you guys just joined, or if you didn't completely understand it the first time, I'm going to make sure by the time we're done, you do. So PC says, I want to go to www.gocloudcareers.com. So the PC does a DNS lookup and says, who has the IP address for www.gocloudcareers.com? And then the PC knows it's the IP address. So the PC looks at its routing table and says, do I have a route? And the PC doesn't, because the PC is not running OSPF, BGP, or routing protocol. But when we install most of our PCs, they have something called a default gateway. The default gateway is where you go when you don't know where to go. So if router 1 is the default gateway, the PC says, I want to go to www.gocloudcareers.com. And then DNS tells them what is the address site. And then what does this PC do? It says, I need to send my device over here. ARP! Who has the MAC address? And this router responds. It's called proxy ARP. I have the MAC address. So the PC sends its device here. Now, when the traffic gets to here, the router looks in its routing table and says, what's my next hop? To the B. So the router sends it to a next hop, and then the router says, what's my next hop? And it sends it to the next router until it gets to the server. Now the message gets to the server, and the server is doing its thing, and it says, I'd like to respond to the message. I am www.gocloudcareers.com. So the PC looks in its routing table. Does it have a routing table? It's got one route. Maybe it's got a route to its loopback, and it's got a default gateway. So the PC says, I know what to do. I'm going to send it to this router here. Who sends it to this router here? Who sends it to this router here? Now, once it gets to this router, the router looks on its subnet and it says, I have the route. ARP, who has the MAC address? Well, I actually knew it from the previous one, from the previous request, and it sends it through the switch. And that's how routing is going to work. So I want you to look at the routing logic. Routers have what's called a routing table. And that's basically a map of how do I go here, how do I go there? How do I go to Eva Doikya's house? Get into the car, drive to the West Palm Beach airport, fly to London, fly to Hungary, pick up a car, make a left, make a right, make a left, make a right. That's how we do it. So routers have a routing table. It's kind of like the GPS in your car that tells you rerouting, recalculating, here, there, go. So the data comes in and the data gets sent. It's really that simple. So look at it this way. Router wants to reach this device over here. This is Cindy the cat on my computer tearing things apart. Over here, we got Eva Doikya over there. So Cindy the cat wants to send a message to Eva Doikya. So Cindy the cat gets on my computer, and with her little paws, she walks on the thing, and it's poorly typed, but she sends it to Eva Doikya. She managed to get her IP address right. So she sends a message to 172.16.2.9. So again, I'm going to walk you through one more time. PC says, do I have a route? The PC does not, but it has a default gateway. So it sends the message here, which then looks in its routing table and says west and up, which goes here. And then this says it is directly connected. So that's how it works. That's how it works. So let me show you this. What happens is the routers and the PCs build something called an ARP cache. And what really is it? It's after the PC now knows that the router has the MAC address for reaching Ivadoikia, it puts it in its table. And why does it cache it and put it in its table? So it doesn't have to go, ARP, who has the MAC address for Ivadoikia? And it does this for the following reason. If these devices send broadcast, we'd be full. The network would be full. So we cache this. Why do we cache the DNS requests on our PCs too? And we'll talk later about what is dynamic domain name system and how does that work? Because otherwise they'd have to ask the same question every single time. So they cache it. So keep that in the back of your mind. That's what's going on. See what happens if we've got our IP packet like we talked about. And because we're putting on an Ethernet, we have to put an Ethernet header, which is how it goes from a packet to a frame, from layer 3 to layer 2. So what your route table is going to look like this. Let's say we've got a packet that comes in on Gigabit Ethernet 00. We've got our packet. And then the router looks at its routing table and says, I know this subnet, this /24. Send this subnet out to reach this address. Send it out serial 0/0. Hey, guess what? To reach 172.16, use this interface. To reach 172.16.4, you don't have a route, so the traffic's going to be dropped. How about reaching this one? There's no route, so guess what? It's going to be dropped in many cases. If there's no path, that's what happens. So we're going to actually start getting involved in a lot of routing configuration. So we're going to make sure we have our fun with this and just make sure. So we don't need to, let's go here, let's go here. So let's deal with some different routes, and we're going to have some fun with it. So let's go back to our happy EVE-NG server. And let's just, what we'll do is we'll create a new lab here, and then one second, close lab. Let's go create a lab together. If any of you guys ever desire to get an EVE-NG server, these things are great. If you're in a hobbyist perspective, there's a GNU3, which sort of works out okay as well. There's also a Cisco, I think it's Packet Tracer, that's another good product. Or you can just buy a cheap CCNA rack on eBay. I highly recommend that. So now that we're going to do this, we'll get 2 routers. Actually, let's do this. Let's give ourselves 2 routers. And we'll be doing some stuff with some switches too, which is going to be really fun. But let's just connect these 2 routers. Actually, while we're at it, let's add a 3rd router so we can have a little bit of fun. Let's have a little bit of fun with this. Let's start them all. Okay, so what we're going to do is we're going to start configuring some IP addresses on each router, and then we're going to configure some static routes. Then we're going to walk into some dynamic routes. We're going to have all kinds of fun when we go through this. But remember, we need a path to get to the destination. So what we're going to have over here is going to be as follows. Let's make this guy router 1. And it's booting. These things aren't the fastest things in the world, but they do their job. After we do this, we're going to look at ARP tables and things. So I just want you guys to get a real feel for everything.
All right, so it looks like we lost Mike. The powers went out at his house. He'll be back on in just a second.
All right, well, let's talk about some networking without some routers for a little bit. See if we can figure out what's going on after the fact. So that's okay. We've got lots of ways we can play with this. So let's talk about, when we're looking at routers, what are we going to be looking at? What is the special sauce that we're looking at? So what we're really going to be looking at is we're going to be looking at the configurations, and I'll show you what these mean. And then basically speaking, we're going to be looking at the routing tables. So let's go back in this particular environment. Let's see what we have here. So, if we're looking at the running config, so our routers are going to have two configurations. They're going to have the running config, which is up what they're running with, and they're going to have a startup config, which is what they boot. Now, if you do everything right, you configure your device, and you either do a copy run start or copy running -config to startup config, or you type WR or write memory. What it's doing is taking anything that's going on in the system, and it saves it so the next time your system's booted. Kind of like this. If you save your document in Word, it's saved for you. But if you don't save your document in Word, guess what? It's not. And not being saved, it's not going to be there the next time. So kind of keep that in the back of your mind. We're looking at the running config. Now, as we network engineers and architects, we're really concerned about whether our traffic gets to its destination. So half of what we're going to look at is we're going to be looking at our show IP route. Now, when we do this, we're going to see the full look of the routing table. And the routing table will tell us how we learned these routes. Did we learn them from OSPF? And if so, guess what? They're going to say, oh, are they in between areas in OSPF? And if that's the case, guess what they're going to say? OIA. If they are external, and we'll talk about that later, they're going to say OE2. But the point is, we're always going to know from what the routing table looks like how we learned it. So let's walk through this scenario here. This route over here, this specific 172.16, that's the CIDR range, right? Now we can see that 172.16.1.0/24 is all directly connected to Gigabit Ethernet 0. We also know that we can reach 172.16.1.1/32. That's the directly connected. That's the IP address directly on this interface. Then we can look over here, the 172.16.4.0. We can see that's again directly connected, and we can see the IP address on that interface. Same thing for this subnet. So that gives us a lot of things. Now, I mentioned what happens is when we go from a layer 3 address to a layer 2 address, what we're really dealing with is we're looking at the MAC address. We're going to keep a table of MAC addresses. Now, I previously had told you that the way we do MAC address tables is really as follows. The way we're doing the MAC address tables is we're going to store it in the routers, and it's going to be in the form of an ARP cache. So we're going to be storing it in the ARP cache. So let's look at what the ARP cache shows us here. If I do a show IP ARP on the router, it's going to show us the IP addresses and the MAC address and how long it's been there. So look at this address, 172.16.1.1. This is the MAC address that's associated with that. And we know that we learned it via Gigabit Ethernet 0/0. So that gives us a bit of an idea what's going on. Now, the next thing that we have is we've got another IP address that we learned. And we can see we learned that 35 minutes ago, but what else can we see over here? We can see a lot of really cool stuff. We can see the IP addresses, et cetera, et cetera, et cetera. So, we kind of know a lot about what's going on here. So I know we did this yesterday, and I was going to do some more with you, but, technology does what it does. Bill Gates was demoing Windows 98 and his computer crashed. I live in South Florida. We get a power thing every single day of the week. Usually my surge protectors, UPSs do their job, but occasionally we figure stuff out. So let's look in this particular position. The PC is here. He wants to reach the far end of the link. So what happens? The PC is going to put, the PC doesn't know where to go. So the PC has a default route. Now, what if on this router, we did a route that said IP route 172.16.2.0, send it over here. That would be a static route. It would work perfectly. I do this 172.16.4, go to this next hop. Now, once it's on this router, that router is going to say, you, everybody, ARP who has the MAC address, and this guy's going to respond. So this guy responds to the router, assuming this router has a static route that says to go to 172.16.1.0, go here, or a default route that says if I don't know where to go, go here. Anytime we have that, now we're in a position where we can really do some pretty cool stuff, because that's how we have the ability to go from point A to point B. How do we learn it? What do we know? Why do we know these things? We know it, quite frankly, for the following reasons. They're very simple reasons. The routes are there. We're looking at the routing table. So those are the kind of things that we're trying to look at. Kind of keep that in the back of your mind. Keep that in the back of your mind, and you should be in good shape. Okay, so now let's look at another environment, like where we would put a static route. So if we put a static route in here, you know what we'd have to do is we'd have to tell this router, hey, by the way, to reach this subnet, go here. So what I do, I'd be on this router and I would type up a command that looks like this: IP route 172.16.2.0. Next hop, we would find this IP address, and it would be, let's look at it, 172.16.4.2. And that would be my next hop, because that's what we see over here. So, you know, keep that in the back of your mind. I'm trying to see if I can try and bring up my server a little bit. Trying to bring it up there for you. Doesn't always work, but I'm still trying to see if we get lucky and can bring it back. So now if we do a show IP route, we'll get it. But if we do a show IP route OSPF, a show IP route static, a show IP route BGP, you'll see what we're going to get here. We're going to be able to filter it so we don't have to look at as much. So if we do a show IP route static, note what it looks like. You see an S next to it. If it was learned via RIP, which we don't use, guess what? It would say an R. So kind of keep that. So we can create a static route for a host, or we can static a static route for a subnet. So this is a host. We route this to a single next hop IP address. Now this is a regular static route. This is a route for 10.1.1.0/24. So it's going to take anything that looks like this and send it over here. Now here we're going to have a route for a specific host. And why is it specific? We're going to go 10.1.1.9, 255.255.255.255. Guess what? That is an exact match. 10.9.9.9 is the next hop IP address. So you can keep that. Now there's this concept of a floating static route where you can have a static route, and if it goes away, you know, it goes away. But reality is why are we doing floating static routes? All we can realistically do, and the best place to do this is we can make it quite simple. We can just use a dynamic routing protocol. But what we could do to make this more believable is we could say, hey, wait, this is preferred. If this doesn't work, we could have a manual static route. So what is this going on? We're running OSPF over here, and we're creating a static route over here. So how is this going to work? If we actually look at the route, if we do a show IP route over here, what we're going to see is the static route has this weird thing over here where it says distance of 130. So what is distance? So the Cisco routers have the ability to determine which route is more believable. So on the Cisco routers, they have things with regards to believability. So which do you think is more believable? A route that I physically said, hey, go here, versus someone that somebody heard from somebody else. the manual static route that I pop there is really believable. So what happens is the Cisco routers use a concept of administrative distance. And they look at routes and routing protocols. They look at RIP, which is a terribly unreliable protocol, and they give it a high number. They then look at things like IGRP, which is not the most believable protocol in the world, and they give it a relatively moderate to high number. They look at external BGP and say that's pretty accurate. They give it a metric or administrative distance of 20. They look at an OSPF external route and they say that's less believable than a standard route, and it's got a different distance, et cetera, et cetera. So EIGRP will have its distance. External routes via EIGRP will also have different distances. And what we have to do is, if we want to override the default behavior of a routing protocol, we have to say, hey, more believable or less believable. And we do that by playing with the distance. There's a distance command on our router. So if I've got 2 routes to Chris's house, I learn one route via EBGP, which has got an administrative distance of 20. I put a static route to Chris's house that's got an administrative distance of, say, 1 or 0. And that's more believable. But if I took that static route and changed the administrative distance to, say, 130, and I learned the route to Chris's house via EBGP, which is, say, 20, the route to Chris's house would be far more believable than the static route. Now, if I change the distance of that static route back to 1, poof, all traffic will be taking the static route versus BGP. So that's what we're talking about when we talk about administrative distance. We have the ability to make certain routes more believable than others. So we could use a static route at really low speed links to not send them. So let's look about adding a static route. How do we do it? Well, in this case, we're going to create a default route. So what do I do with routers? We do config T or configure terminal. But, kind of keep that in the back of your mind, config T. Then that'll enable us to do it. So here's the routing command, IP route. In this case, it's a default route, which is 0.0.0.0, exact match 0.0.0.0. Send it out, serial 0/0/1. That'll work. Now going back, this will show you how we learned it. So if we look at the routing table, note it says S. Why? Because it's a static route. Note this says C because it's directly connected, and L means link local. So keep that in the back of your mind when you're there. So let's do another set of routing. Permanently adding static routes to the routing table. We can basically do the IP route. Look, this is a route where we're sending 172.16.2.0 out serial 0/0. And I'm going to tell you this, I don't ever like to make static routes this way. I like to do things intelligently, which is where I like to give them an actual next hop. So I would prefer to do this 172.16.2.0 and then give an IP address of the far end as opposed to which interface to just leave and hope somebody else takes it over. And here's where you can see an example of using an exact match IP route. We're going to take the 172.16.3 subnet /24, and we're going to send it here. That is a very explicit route. So now in this particular case, let's look at what we're getting. If we do a show IP route OSPF, we might find that we've got a default route that we learned via OSPF. Note that distance is 110. And what you see next to it is the metric or the cost to get there. So you can see this is what's going on. We do a show IP route. We can see what the next hop IP address is, and we can see the outgoing interface. So what do routers do? I got 2 limbs. I look at this. I got a packet on one limb. Packet comes in. I look in the routing table. I say, go out that limb. And then I'm like, nope, nope, nope. Go out this limb. Nope. Go out that limb. Go out that limb. So routers are like octopuses with limbs everywhere. They take the traffic in and they send it out as fast as they can out another limb. That's what routers do. So just kind of keep that in the back of your mind as we're doing some of these things. So let's kind of look at some of these things that we can potentially do, and some of the administrative distances and some of this stuff. So there's that concept. Now we had less visuals and less labs to be able to demonstrate this. So let me do this. Let me see if anybody has any questions for about 15 minutes, and then we're going to get to routing And we're going to talk about router on a stick and switched virtual interfaces and switched ports, etc., etc., etc. So Chris, if you want to look through the chat box and see if there's any questions.
Yeah, there's some questions related to career and training preparation for cloud careers. But if you'd like to answer that, we can, or if you want to suggest that they come to our session on Monday, we can do that.
If it's on a couple, let's answer a couple questions and go back to the content, and then we'll invite anybody to the session Monday. So, okay, so Saksham Malik, let me be very clear. There are no certifications that will make anybody a cloud architect. Absolutely zero. What makes people a cloud architect is as following: extreme knowledge of the network and the data center, and knowledge of the way the cloud works, how it works, and how to design systems on the cloud. It takes knowledge of virtualization, knowledge of firewalls, knowledge of VPN concentrators, knowledge of servers, server virtualization, containers. It takes knowledge of system design. It takes executive presentation skills, executive communication skills, CXO relevancy, the ability to do an ROI model, the ability to give a presentation in front of 1,000 people, the ability to sell $1 billion solution, the ability to show the customer that if they buy $1 billion of technology, that really they're going to get $3 to $5 billion in business value by generating a business case. It involves, asking a customer about their business challenges and creating a design, and none of that is covered in certification training. To train that, you have to master the network and master the data center and master the cloud and master system design, communication skills, et cetera, et cetera. Now, we have a program for that, and you can do it, but you can have the AWS Certified Solution Architect Professional, the CCIE, the Google Professional Cloud Architect, and still not be hireable as an architect unless you get those skills. So it's not about certifications. Certifications don't get anyone hired. Now, certifications build your resume, which can get you an interview, which is why we do certifications, to help get that interview. What gets you hired is in the knowledge in your mind, the right attitude, energy, enthusiasm, communication skills. We've got a program for it, but that's what you need to do. And join us on a Monday or a Wednesday, and we can go into extreme depth on how to do this. Chris, do you want to bring in the next question? But every one of you can get these jobs if you put in their fight. Angelo, use cases of using spanning tree versus routing. Well, Angelo, as a rule, I haven't used spanning tree in 20 years. Why? Every crazy spanning tree network, I ripped it out and I put layer 3 routing, and the comp thermal was really helpful. So if you've got 1,000,001 VLANs for some reason, and your team doesn't enjoy routing and they don't have the sophistication for routing, people do switch networks. But if you've got the sophistication for routing, don't do any of this layer 2 stuff. You're going to get yourself in trouble with spanning tree loops, bridging groups. It's fairly complicated. And it's easy when you compare how spanning tree works to OSPF, for example. But chances are I don't use a lot of spanning tree, and I use routing because routing is fast. And you don't get, and it's easier to avoid a routing loop with good configuration than a switching loop. So it's a good question, Angelo. If you've got the ability and you have good routers, you're going to use routing. If you don't have the ability and you're looking for just simplicity, you're going to switching. But that's a good question. LM, what is the advantage of using the default router? You have to have a router. So if you don't have a default route in your PC, you're going to have to manually add a route for everything. A route to one website, a route to the next website, a route to the next website, a route to the next website. Or your PC would have to run a routing protocol with your router, such as OSPF, EIGRP, BGP, et cetera, et cetera. So you have to have a destination to get there. So if you don't have a default route, you have to have the exact route. So on internet routers, guess what? They have full routes, no default routes, full routing tables. But unless you want to take on a full routing table, LN, which right now is about 800,000 routes, and stick all those 800,000 routes in your PC, you're going to have to use a default route on the PC. And that's why, because it says if you don't know where to go, go here. Otherwise, you need to take in the 800,000 routes. Excellent question. Tech with me fan. Okay, this is an extremely good question, Tech with Mufaz. So if we run a routing protocol like OSPF, it's automatic. If we don't run OSPF, we have to configure static routes. And by creating static routes, that's going to build the routing table manually. So it determines whether you use static routes or dynamic routing. That's really the part that helps us configure this. Good question. Use cases for bridged internet and enterprise solution? Ugh. I can't think of any use cases for which I would do it without ripping it out with a layer 3 link, but people use bridging for the following reasons. Like if you're going to connect to AWS, they want you to send them on a VLAN, and they're doing this because they assume it's going to be too complex to have a layer 3 link going back, and they're trying to avoid it. So they're using layer 2 bridging. If you wanted to extend VLANs across a campus, you'd be using bridging. Or you could just create extra subnets on your switches and route between them and have good access control lists and filters and QoS policies between them and not have any of these problems be routing. So people like switching. So if you're dealing with people that want to run a layer 2 shop, you're going to use bridging. If you're dealing with routing people like me that really hate layer 2, you're never going to use any bridging. So I see of no point to use bridging when you can use routing, because the speed to heal is so much faster. But keep that in the back of your mind. There are organizations that don't want to use routing protocols because there are people that understand routing protocols. Someone with good knowledge of routing protocols is a $200,000 employee. Someone with knowledge of spanning tree is a $80,000 employee. So lots of times people go for the spanning tree because they don't want to have to hire the sophisticated people to truly understand routing. Which devices use static IP and dynamic? Generally speaking, as a rule, anything that matters gets a static IP address. So your routers get a static IP address. Your servers get a static IP address. Could you imagine NSSA trying to connect to a server, and today the server's IP address is 192.168.1.150, and then you get a wide system reboot, and then you get a 192.168.1.139, and you can't even find it? That's the kind of stuff that actually happens in these environments, and that's why we're really, really, really so critical of making sure that we never use dynamic addresses on servers. So PCs like your PC, yeah, that can get in a dynamic IP address anytime it wants. Not a big problem ever. Never. But by comparison, it is a massive problem if you need, by comparison, a server and its address changes, and you can't imagine going to a website that wasn't there because its IP address changed. What an excellent question you had there. Earl Owens, well, routing on a stick is layer 3 routing. Now, if you're asking whether it's better to route on a layer 3 switch than routing on a stick, we're going to get into routing on a stick and show you why it's probably the worst idea ever. Having said that, no, routing a router on a stick is layer 3 routing. And we'll show you what that means when we get to that content very soon today. Williams, as we configure the static IP address, the next hop is not a default router. The next hop is the next router on the link. So that's a pretty good question. So let's go back to this particular environment, because we wouldn't be configuring a static route over here. So let's go back over here in this particular diagram. So let's say I wanted this PC is going to have a default route, which says, if I don't know where to go to router 1. Now, router 1 could have a route that says, if I don't know where to go to router 2. That we could do. But we could just say, hey, to reach subnet 172.16.2.0, go to this next hop IP address. And that's typically what we're doing, because what if we had an internet connection over here? That would be where the default route would go. If this was, say, going to the internet would go here, we get a default route, and we'd have a specific route taking us to this next hop. So we can only do one default route. And the default route has to go for stuff that we don't know. The default route is almost exclusively pointing to the internet, because your routers will have a routing table of every route in your enterprise. So the only time you're ever not going to have a route for the most part, is if you've done some route filtering to keep the routing table small, which is a very smart thing to do, or you're going to the internet and that's why you don't know where to go. So I hope I answered that question for you, because that was really a pretty solid question. Of course, we'll cover radius and 802.1x, etc., because it's definitely part of this content. Can I explain the concept of virtual routing and forwarding? Sure. So very simply, so here, let's create a new slide, insert, hold on, how do I do this? Oh, I see what's going on. Oh, that was not supposed to happen. So let's go back and let me find this. Apparently I enabled editing to add a new slide. And as soon as I did that, that effectively kicked me out of being able to look at this. So let's keep going. Bear with me a second. Well, what we'll do is we'll just answer it up front, and then after this we'll go back. So here's a switch. Got a switch. Take this switch, and and beside the switch, we group 20 ports together over here.
You're not sharing your screen, Mike.
So we create a switch here. These are ports 1 through 10. 1 to 10. That's VLAN A, which is ports 1 to 10. This is VLAN B, which is ports 1 to 10. Now this is going to be VLAN C, which is going to be ports. This is going to be ports 11 to 20. And this is going to be 21. Whatever, we just pick some ports to 30. And then I want to make this clear exactly how simple this is, even though it feels kind of complicated. And this is now the switch, which is got VLAN D, which is ports 31 to 40. Okay, so this is a virtualized switch. Now, VLAN A can't talk to VLAN A, VLAN B can't talk to VLAN B, VLAN C can't talk to VLAN C, and VLAN D can't talk to VLAN D. We just upgraded our switch to a router. Okay, now A is a virtual routing and forwarding interface, and this is for customer. So this is for customer 1. Now this is the virtual forwarding and forwarding interface for virtual customer 2. Now this is virtual customer 3 for the service provider. Now we've got the 4th customer. This is VRFC. And this is VRFD. And now this is customer 4. By the way, this VRF thing that we're talking about, that you're asking about, this virtual route forwarding, was what was created for one of the primary clouds, specifically RFC 2547 BGP VPNs. This is a cloud. This cloud was pretty much, it was done by Cisco and Juniper. Ivan Pepanajak wrote a really good book about it. I mean, it was really fantastic. He's one of the original CCIEs. So instead of being a switch, this is now a router. So this is now AT&T's router. And AT&T now has your routing table in one version of OSPF, somebody else's customer in OSPF, somebody else's customer in OSPF, and somebody else's customer in OSPF. So we took a router and we just created virtual routers inside of it. Now, VMware 20 years ago, take a server, install a hypervisor, chop that server into multiple virtual machines. Okay. Cisco created the VLANs 30 years ago. Take a switch and chop ports up. 30 years ago, 25 years ago, we're starting to get into cloud computing. So what did we teach all the cloud providers? To create virtual routers where their customers' information is separate. So the modern cloud computing that we're using today with virtual routing and forwarding tables, where do you think this came from? Cisco 20 some years ago. So that's what we meant by virtual routers. And the cloud provider, everybody's got their virtual private cloud, which is basically their little virtual private data center sitting in the cloud provider. Guess what we're dealing with here? The same thing via Cisco 25 years ago, except when Cisco created this, they don't have to call it elastic. They don't have to issue 15 million press releases and pretend that it's new. It's something they did 20 years ago. It works great. Every service provider uses it. So I hope I answered your question. That was a really, really, really great question. Mark, pretty much the only routing protocols that we would ever use in today's world are OSPF and intermediate systems to intermediate systems. There are only interior gateway protocols that we'll be using. Exterior gateway protocols include BGP. And that's pretty much it. Now, granted, there's an EIGRP, which we don't use for the most part. There's a RIP v2, which we don't really use anymore, which are also interior gateway protocols. There used to be this thing called IGRP, which was this classful, ugly routing protocol that was a little better than RIP, but not as good as EIGRP that Cisco invented many years ago, about 3 decades ago. And then when they invented it, it was a good routing protocol. But in today's world, it's all OSPF. Where do proxies come in? Nowhere close to this. And it really has nothing to do with networking proxies. In fact, proxy servers are all systems admin work. And here's what a proxy is. And unless you're working in the Middle East, chances are you won't be using many proxy servers. If you're working in the Middle East, you will be, because direct internet access is not allowed in a lot of Middle East locations. For example, when I was in Dubai, every piece of traffic goes through a proxy server because they don't want to allow people to get to anything that's been deemed illicit. So, they use a proxy server. But here's what a proxy is. So you've got your network, got your computer here, got a user.
Make sure you share your screen.
The user wants to connect to the internet. So he connects to this proxy server. The proxy server goes out there and connects to the internet. And yes, we've always used a cloud for the internet. All a cloud means is you don't know what it is because the information is hidden from you. So now, user wants to go see www.gocloudcareers.com. This user is not allowed to go to the internet. It goes to the proxy server. And the proxy server says, can I go to www.gocloudcareers.com? And the proxy checks its list and says allowed. So the proxy server goes to the internet. Internet comes back and the proxy server delivers it to the user. Now, another user wants to go to the same website, www.gocloudcareers.net. And they hit this website and it's already there, so it gets sent to them. So it does some caching as well. Now what happens is this user wants to go to this AWS exam dump cheat exam copy of it. And the user sends its request. It hits the proxy server. The proxy server says, bad site, bad site, bad site, and sends a response back to the user that says, sorry, not allowed. So a proxy user is used to control the user access. And that's what a proxy server is. And again, it has nothing to do with networking and everything to do with servers and systems administration, but kind of keep that in the back of your mind. So are we going to talk about Cisco Wireless? Not a lot. We will a little bit probably, but not a lot. Why? Because we deal with predominantly architects, and cloud architects are dealing with people that need reliable, and we never put anything important on wireless. The only thing that we use wireless for is like desktop users roaming around, stuff that we don't care about. Everything that matters is all going to be wired, not on a shared multi-access network, just due to the kind of problems that we can occur. Chris, did we have any more before we go back to content?
Yep, we got one more.
Okay, let's answer one more. So the reason we use the BGP routing protocol for internet is as follows. BGP is extremely scalable, meaning we're going to take in 800,000 routes per internet service provider, where OSPF or other routing protocols will fall apart once we get to about 10,000. So We need the level of scalability provided by BGP. Additionally, in BGP, we do the following. We have the ability to take in routes from one person and another person and prioritize one link over another. So BGP is used because it's extremely secure, it's extremely scalable, and because it's highly tunable. So I can connect to this internet service provider, this internet service provider, and this internet service provider. And the things that this internet service provider has the best routes to, I'm going to go, versus this internet service provider versus this internet service provider. So we use BGP because of the scalability, the tunability we get, because no other routing protocol gives us that level of scalability. And that's a really, really great question too. Excellent, excellent, excellent. So fantastic. So let's go back to some content, unless there's any other questions, Chris, that came in since the last one. I will find out where we are in our presentation, since when I wanted to draw these to make some demos, it didn't cooperate very well. So I'll be with you in a minute. While we're at it, if everybody can type hashtag CCNA. So now we're going to talk about routing between switching. So there's realistically a couple ways that we can do this. And when we're routing, when we're actually routing in between VLANs, we have two options. We have, the thing called a router on a stick. And mind you, I haven't used router on a stick for over 2 decades because it's the worst possible thing we could do, and I'm going to show you why. Or we could use switched versatile interfaces, or we could not do anything crazy like a router on a stick. We could just create a cable from each VLAN to the router, and that will be not as good as a switched versatile interfaces, but nothing out there is as bad as router on a stick. And I'll be demonstrating to you why. So please remember this. In this particular environment, if this switch has 2 VLANs, and this switch has 2 VLANs, and this switch has 2 VLANs, we are going to have to be able to route between VLANs, because VLANs can't talk to each other. Now, there's 2 ways we could do this. We could have, if there's a VLAN, if there's 2 VLANs here, we could have 2 Ethernet ports on the router. One cable would go to one VLAN, and another cable would go to another VLAN. And we could have one cable to go to one VLAN, and another cable to go to another VLAN, and one cable to go to this VLAN, and one cable to go to this VLAN, and we could route between them on the router. That would be perfect. Everything would work fine. So one cable per VLAN goes to the routers. I got a gigabit for VLAN 1 and a gigabit for VLAN 2. How much throughput is that over 2 gigabit links? 2 gigabits. Now, I can do router on a stick. Router on a stick is create a trunk port between this one switch and this router and route between VLANs. So now we've got a 1 gig piece of fiber. We've got VLAN 1 and VLAN 2. So of that 1 gig, we're sharing it amongst 2 VLANs. Now, let's add 10 VLANs to the switch with this crazy router on a stick concept. We're now going to put, and I'm going to show you how to do it, all 10 VLANs all on a single port. So we're now going to have to share the bandwidth on it. So router on a stick was this horrible thing that we did back in 1990 something. But the performance of it is so bad. So what's it going to look like over here? I'm going to draw it out for you again. In this particular environment, we've got a router. We've created a trunk port, trunking VLANs 10 and VLANs 20. We're trunking them back to the router, and the router is going to have 2 sub interfaces, and I'll show you what that looks like. So on the router, what we're going to do is we're going to go to the interface itself, and what we're going to do is as follows. We're going to take the running config, and we're going to go interface gigabit Ethernet. Note 00. Note that little 0.1. What we're doing is we're taking our interface over here. We turn the interface on, and then we create a sub interface. And in here, we basically call it interface gigabit Ethernet 0/0.1. And then what we do is we tell it to trunk VLAN 10 inside of this gigabit Ethernet part. We say gigabit Ethernet 0.0/1. Here, take VLAN 10. By the way, here's an IP address. And then over here, we say we create another sub interface. And we tell it trunk with a .1Q tag VLAN 20. And we give it a different address. Note what's on a different subnet, .10.20. So then when we configure this on the device, here's what it's going to look like. It's going to look like as follows. We've got the IP address over here. And in this particular case, we've got a sub interface with an encapsulation. So you can see what we've got it. We're going to look in our routing table, and here's what you're going to see. You're going to now see that you've got this subnet on this logical interface that we just made, 0.10. We can see what the IP address is in the local interface. We can then see we've got another, guess what? Another sub interface on this thing, which of course has its own subnet and IP address. So now when we look at this, what are we seeing? We're seeing the internet ports and all of the sub interfaces. So now let's go look in here. And as we look in here, let's look at the VLANs on the switch. We can see we've got these VLANs. We can see what's going on with these VLANs. And it really gives us, a fair amount of things. So the only problem that we're really talking about right now is this. And this is a pretty significant problem. We've got a router that may have 50 ports on it, or a switch that may have, let's say the switch has 100 ports. And we now, and they're all a couple of VLANs, and we now stick this on a router. And we have multiple VLANs all on a single cable. So let's say I'm drawing this. We've got a switch over here that's got 100 ports. I just drew a router. Now I'm going to run a cable between them. This router, if this is a trunk, all on a single port, is going to be maxing this gig out. This link is 1 gig. 1 gig. So picture this. Let's say on this link, we had VLAN 10. VLAN 10 needs 800 megabit per second. Now let's say VLAN 20 needs or desires or could use 1 gigabit per second. And this is nothing. 1 gigabit per second. I mean, I send more data than this in my house. Now, if this is the case and this link is only 1 gig, not so good, which is why I say router on a stick is about the worst idea in the world. Not so good. This link is the constraint. And can this router even do a giga throughput? That's another story. Where switches are designed for this. So now, if we had 2 VLANs and 2 cables, and each cable was 1 gig, do we have any constraint on the network now? Or is the network smooth and high performance without that little thing? So, do we all see why I'm talking about not loving router on a stick? Does it make sense to people when I say router on a stick is not necessarily the most beautiful, simple, and elegant solution for that reason and that reason alone? Is that obvious to everybody? Because if it's not, let me know. And if it is, let me know in the chat box. If you get this and understand why I don't like router on a stick, tell me CCNA, hashtag CCNA/got it. Because I want to know you got it. And then we're going to get into the other ways to do this.
We're missing your Jeopardy music, Mike.
Oh, that's right. Do 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 do. boom, boop, 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 bum, 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 bum. Okay, tech with Mufaz, you don't get it. So, tech with Mufaz, I want you to think about this. You've got two cars that are each trying to drive 100 miles an hour down a link that only supports one car at 100 miles an hour. When we add the second one, both slow down. So, got a big pipe and a big pipe, life's good. You got two things that you want to shove down the same thing, everybody suffers. So router on a stick, if I've got 100 gigs of throughput that I need to do, and I've only got a 1 gig point, we got a problem. So Mufaz, heck with Mufaz. The thing is this link is the constraint, becomes a constraint. So we might need more than one link, more than one link, more than one link. And that's the reason why. That's the reason why. So hope that makes sense. Now let's talk about the other way to do this, the real way to do this. So with that router on a stick idea, it was terrible because we had everything going down a single trunk port. Now it would get better if we had multiple cables per VLAN. So that would be cool. But really, the only intelligent way to do this is with a layer 3 switch. So what is a layer 3 switch? What if I told you that you could put a switch and a router all in the same device? And it would look like this. Instead of doing this ridiculous router on a switch, what if I took my switch and inside of my switch, I could let's get rid of the fill. Now this is what to put it into context for you. This is what we've been doing now for about 20 years. Let's just make the text the right color. So now let's draw ourselves a VLAN. VLAN A. VLAN B. VLAN C. And then VLAN D. Let's have some fun with it. So let's say ports 0 through 9 are here. And let's say ports 10 to 19 are here. And let's say this VLAN uses ports 20 to 29 over here. And then let's say over here with VLAN D, we do 30 to 39. These are the ports. Now, right now, there's no way to route between them. None, because they're routers. So we have two options. We could do it smart. If we had a router on the stick, which we don't want to do, we could do a router here. And what we could do is we could run a cable from here to here to here. And then we could run a cable from here to here. And then we could run another cable from here to back over here. And then I could run another cable. By doing this, guess what? I've got 4 cables. So I have less of a bandwidth problem, which should be good. So, we don't want to do that. So what if we could actually create an interface inside of these devices called an interface? What is an interface? It's a subnet. It's a logical device that needs a subnet. And we could put an interface, and this one was 10.0.0.0 or .0/24. And this one, let me do that. And this one over here is 1.0. And this is 2.0. And this is 3.0. What if we could just pop an IP address on the VLAN and then turn on the routing function in the switch and ask the switch and take the switch. So here's what these typically look like. So you've got a switch over here. And actually, let's build out the switch for you guys so you can see what it looks like. We're going to turn this into a full switch. So the first thing we're going to do on the switch, because we're going to assume this is a high availability switch, we're basically going to put what's called the control module. And this is the brain for the switch. And then 1 is none, 2 is 1, and 3 is greater than 2. So if we care about this switch, we're going to put a backup control module in case the 1 fails. Now, let's think about how to not have problems in our network. Do we think that we're going to be in an environment where power failures are never going to occur or circuit breakers are not going to occur? Of course we know they're going to occur. And we plan for these things to occur because that's why organizations don't really have power failures. In fact, other than AWS, I haven't seen a power failure in a data center in 25 years because organizations have generators and backup generators, but so there's there. So we're going to have 2 power supplies. And these power supplies are going to be plugged into different outlets in different circuits. This is pretty normal. Going to different power sources. Now we can put a router module in here too. So now there's the router module. If we've got a router module, do you think 1 is enough? No. 1 is none, 2 is 1, and 3 is greater than 2. So let's put a backup router module. Okay, so now we've got a relatively high availability router. Now on this router module, inside the same switch, we can just route between these VLANs because the router module is in the switch. So all these cards, all these VLANs, they plug into the back of the switch. It's this fabric that's got ultra high connections from port to port. So directly in the switch, we're routing in between VLANs. This is the coolest thing ever. Coolest thing ever. I mean, when you start looking, well, I probably should have put that in there. The router is going to route between VLANs, and this is what we've been doing for the last 20 years or so. This is what a layer 3 switch is. This is exactly what a layer 3 switch is. We route in between them. So this is the alternative. So, this would work, although this is 1980. I don't want to call it 1980. I want to call it 1990. That's the problem. But in 1990, remember, routers could only do like 1.4 megs of throughput. So it didn't matter if we had a 10 megabit fast Ethernet port. We couldn't do it anyway. So that kind of puts them into your context what they were. Now, let's talk about the other way we could do router on a stick that wouldn't be so bad. Now, what we'll be able to do is we can actually bundle multiple links together and make them look like one, so we don't have to deal with that stupid spanning tree, because spanning tree is a disaster. So we can bundle all these together and it's going to look like a link and we won't have anything blocking. It's all going to be good, good, good. So now with this, let's say this is 4, and this is called ether channel. People also call it like a link aggregation group. But what if we have over here, if we have 4 100 gig links going from a layer 2 switch to a high performance router. Now, if we've got 400 gigs and this router can do 400 gigs, guess what? Now that router on a stick is cool. But how many people are setting up 100 gig links in ether channel or link aggregation group to use router on a stick? No one, because they would never be involved in doing this when they can buy this, and they've been buying this for the last 20 years. So I worked for a switching company a while back, and 20 years ago, I'm in the switch, or 20 some years ago, I'm in the switching company. And they're like, Mike, look at all this cool bridging stuff we can do. And I said, yep. Look at all this cool routing stuff the switch could do. And they'd say, Mike, routing's too complicated. People don't understand it. And I said, I'm going to train them because I don't want anybody dealing with bridging loops. And they would push bridging loops, push bridging. I would push routing. And my customers never really had any problems. And it wasn't that the other bridging people weren't smart. They were geniuses. And bridging is fine, but there's so much that can go wrong. IP is just so much easier. We don't have to deal with it. So kind of keep that in the back of your mind. So now let's look at it looks like the Cisco way. Let me show you the way the kind of way that it would look like. So here, what we have here is this thing that looks like that's using the router symbol is actually a switch. So what happens is this switch now has VLANs in it, it has VLANs in it, and there's a router module in the switch, just like I drew. So why does this look like a router? Well, switches don't do layer 3. So once you start having a layer 3 switch, we routing people call them routers, even though they're technically layer 3 switches. So what's it going to look like on a configuration side? I would have done this with you today, but apparently my EVE-ENG server after the power outage is not happy. I'll have to invite my master breaker and troubleshooter. She'll come in, she'll lick her paws, clean her hair, she'll start chewing through some cables, and hopefully she can fix it for me. I'll hire Cindy the cat. So, but this is what you're going to do on your device. You're going to actually enable routing by turning on IP routing, and then you're going to put an IP address for the VLAN. And then you'll be able to see it. So you put an IP address in the VLAN, enable your VLANs, and then you're going to look in your routing tables. And you know what you're going to see? You're going to see that your VLANs are actually connected. You're going to see that we've got this stuff connected and where they're at. So just like any other routed interface. So let's talk about how we would troubleshoot VLANs if they don't work. Because, well, we have to make sure the VLANs are up, right? The switches, remember how we had them port shut down and they didn't work? We have to make sure that our routing is right, our IP addresses are right, etc., etc., etc. So when something doesn't work, what do we do? Where do we look for? We look for the following. Look at the routing table. The routing table is going to tell us what's going on. If I do a show IP route here, oh, there's no routes. That's not good. Why wouldn't there be any routes? Because it's configured as a layer 2 switch. How do we turn on layer 3 switching? With the command IP routing. So as you can see, we're getting through this. It's really not that big of a deal. When we want the switches to be routers, they have to be a layer 3 switch, and we have to say, yes, you can do this. So let's do a little bit more debugging and some graphics. Going back here, if we look and notice that something's wrong, we're going to configure it. So let's look right now at this interface fast Ethernet 0/1. Will it work? Why won't it work? Interface fast Ethernet 0/1 shut down. Okay, well, that's not going to work. Why is it not going to work? It's not going to work for the following reasons. It's shut down. Admin down. So if we do a no shutdown, it'll come up. We don't know that until we look in the configuration. We can do a show run, which will show running-config, which will give us the running configuration, etc., etc. As we can see here, we have the interface. It's shut down, and that's why it's going down. So let's play with it a little bit more. No, we can, in certain cases, we can turn a switch port into on a layer 3 switch. We can create a VLAN and say ports 1 through 10 are part of this VLAN, and it's going to work beautifully. Or what we could do is we could take a layer 3 switch and just put an IP address on a port. Remember we did that yesterday? So normally speaking, what we would do is we would say for normal things, we'd create an interface for the VLAN, which would have the IP address. And we would add the ports to the VLAN like you saw me do yesterday. In this particular case, interface gigabit Ethernet 0/1, we have to tell it not to be a switch port, to be a router port, and then we put an IP address on it, and then it'll work. Let me just walk you through this. So let's say we had a switch. We wanted to turn on routing. We would turn on routing. We would put an interface on the VLANs, which have the ports. As long as they're one port up in a VLAN, it's going to be up. But if we wanted to take a single port or a single interface on this device and get us there, we absolutely can do it by basically putting a port on the interface. But it's also doing one more thing that we have to do. It's an issue of just making sure that, what's the word I'm looking for? Okay, I have a feeling I know where our stuff is. So keep that in the back of your mind. Let's go through this. Let's go back to the show interfaces command that we have. Over here, what we can see that the port is up, right? How can we tell? Well, it says show interfaces gigabit 0/1, gigabit Ethernet 0/1 is up. Okay, that means you've turned it on and it's got link. wires plugin. Line protocol is up, meaning it's formed a data link connection. Now, if we do a show interface status, look, we can see which ports are connected and which VLANs they're in and at what speed. And of course, we can show that on the routing table. Next over here, implementing routing interfaces on switches. Basically, it's the same thing, what we're doing now. I'd like to describe Ether channel to you. And Ether channel is a very old technology, and it works absolutely great. If any of you guys desire to do any work in the cloud computing community, guess what? There's a new version of Ether channel, and it's called a link aggregation group. So what is a link aggregation group, and why do we use it? So if you'll recall, when we did switching, and I'm going to, in case you missed it, I'm going to talk about it one more time. I'll actually draw a little picture, and then we'll go back to this. So imagine this. You've got a switch over here, SW, and you've got a switch over here. Two switches. Now we have two links between the switches. And we've disabled spanning tree, which blocks loops. So here we go. We got a PC over here. Let's take a box. Create a PC over here. Let's say this is Cindy. Cindy the cat. Cindy's PC. And over here, we've got this cat named Noni. It's one of the Blue Wrenches, Abigail. She's got a beautiful cat. So over there, we've got Noni that's sitting on the other end. And Cindy decides that she wants to send Noni a picture of a rat. In this particular situation, what we would have is we'd have Cindy sending ARP, who has the MAC address for my best friend Noni. And then Cindy's request would go out this port and this port. And what would happen is it would get flooded out this port. But what would also happen is this switch would then send it out all ports, which would go to this switch. And this switch would send it to this switch. And what's going to happen is we're going to have this packet replicated forever going this way and another one going this way until it fills up the link in a broadcast storm. So what we had was spanning tree that would block this link and say, woohoo, I'm sending my information. It's going to go over here, 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 and here. My communication is going to go back here, here, and here, 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 and here, 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 and here. All kinds of good stuff. All kinds of good stuff. So because of this, what we're actually talking about is, these are the kind of stuff that we're talking about. So now, so what we know is spanning tree as follows. Spanning tree, for example, spanning tree of loop avoidance. The spanning tree will block one of these links. Now, that's great. But what if we didn't want it to? What if we wanted to have two links that worked? Now, what if we could take two links and make them together like one big link? What if we could bundle these two links into a big, thick link? So we've got 4 10 gig links together. Now, if the 4 10 gig links are together and one of these 4 links fails, guess what? We've got 3 more in there. 3 more in there. So as follows. Cindy wants to send something to her friend Noni. ARP, who has the MAC address. The switch forwards it out. All ports except the one it came in on. It goes out to Noni. Noni sends it back. It goes back to Cindy. Now Cindy's sending a picture of the squirrel she caught. Noni's sending her a picture of her favorite tuna. Cindy's then sending her a picture of her ball. Noni's then sending her a picture of her cat tree. Cindy's sending the picture of the cat tree that her father spent $500 on building that she saw and she walked out of the house. And Noni says, that's a shame. I would have loved that cat tree. It's a shame you made your father throw it out. And the two of them are communicating, and they're communicating as life is good. We don't have to block any links because they only look like one link, even though there are 4 links bundled together. That's called Ether channel. That's called a link aggregation group. That is Awesome. 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 So now let's walk through something that looks a little more official, and I'll show you an example. Here's what we're doing over here. We're going to just show interfaces port channel, and here's what we're going to see. We're going to see the line protocol is up. We're going to see what the hardware is, for example. We're going to get a show interfaces status, and we're going to pretty much figure this out. So we can see which ports are there. Look, there's a couple ports in here. Isn't it great? They're all connected. Fast, fast, fast. See, it calls it port channel. So it looks like one link, even though it's more. That logical doing things, that speed, that performance. So let's look at a little more details. We're going to show an Ether channel summary at layer 2. We're going to see that it's bundled. We're going to see what layers we're using, et cetera, et cetera. So this is some pretty cool stuff. So with anything else, if it doesn't work, we got to troubleshoot, and we're going to keep it there. So here's what we're going to do. I have an idea where I think my server went, and I'd like to get it back online, but I'm not sure if I can. So what I'm going to try and do is check my firewall, see if I can find the main VMware ESXi server, and come back to this. And if I can't, don't worry, we will have some fun. So Chris, while I'm going through this, if you could look through some questions and potentially see if they have look through some of these questions, and then what's the word I'm looking for? I'll answer some of them.
Yeah, I'll have questions ready for you when you're ready for them.
Yeah, just bear with me for a second. I have a theory that what happened is after my system came back, the system rebooted, but the virtual machine that was inside of the system didn't come back on. And I think that could actually be the case where if I just go to the VMware ESXi server and turn the lab back on, everybody will be good. So I just want to see if I can actually do that. And if I can't do it, no big deal. We know that it's not done. Okay, 116 is my PC. 11 is not it. Well, you know what? It could be. Let me try 125, then 11, and then 115. I want to try and find out which one of these servers it is to see if I can get back and do some more labs with you guys. Okay, so, I think we found out where our server went. So while you're doing that, I'm rebooting that server, the virtual machine, and hopefully that's going to get us up. And in the meantime, Chris, if you want to bring me a couple of questions, I'd be thrilled to answer it. Chris, if you can have those other people trying to work on that, and we'll make sure that we close by 3 o'clock today. And if you can please inform Mark between 3 and 4, we'll get him a response. With a layer 3 switch, you don't need a router. Exactly. A layer 3 switch is a switch with that little router module inside of there. Exactly. Albert, are switch virtual configuration possible on layer 2? No. This is a router thing. This is a layer 3 switch thing. So on a layer 2 switch like this, absolutely not. The rest of the layer 3 switches in my house, absolutely yes. Good question. You know, that's kind of the thing. So where this came from, Angelo, is as follows. It used to be that switches were fast and routers were slow. So we switched everything. So when I started and I did my CCNA, I spent about $6,000 for a Cisco router that was called the 2500 series router that could pass 1.5 megabytes of traffic. You heard me. I spent $6,000 for a router that could pass 1.5 megabytes of traffic. At the same time, Cisco was selling the Catalyst 5000 switch that could come close to like a gigabit of throughput compared to the 1.5 megs. So, you know, that kind of put it into context of exactly, and maybe it was a half a gig, but it showed you how fast switches were versus how slow routers were. Then fully programmable ASICs came out, and then ASICs came out, and now we have routers that can push a terabit a second of data like nothing. So when we're dealing with that kind of traffic, what happened was we started switching because it was fast. And then this concept of the router on the stick was kind of the stupidest idea we ever had, but it was the only idea we had. So by popping that router in there and not creating all those sub interfaces and bandwidth problems, we called it a layer 3 switch. The term actually came, I believe, from Extreme Networks about 20 years ago. I was using their switches. They were fast as can be. And then everybody else copied them. How does a link aggregation group prevent a broadcast storm? Like this. So if you have a link aggregation group, you've got one wire no matter how many you have. If you don't have a link aggregation group, it looks like you got multiple. And you have packets that can loop and loop and loop in a circle. But you can't loop if you only have one. That's how a link aggregation group prevents it. So in spanning tree, you block one link. With a link aggregation group, you only have one link. There may be 4 bundled in the link. So think of a link aggregation group as a sports team. You get on your team and there's 4 people playing Podosfero. I think it's called football in Europe and Americans call it soccer. So they're all a team. You only see one, and that's what's going on here. There's always at least 2 switches. 1 is none, 2 is 1, and 3 is greater than 2. Switches, yes. And the link, I was just showing a link aggregation group, exactly. Also called port channel, ether channel. Exactly. Does a smart switch have an IP address? You have to manage it. On how do you manage things? Via SSH or Telnet or HTTPS, et cetera, et cetera. And that mandates that it has an IP address. And yes, that is a great question. What accounts for switches being faster than routers? Well, now they're not, but routers used to do this. Packet would come in, the router would look at it and would say, source address, destination address. Let me send that packet to the CPU. The CPU in those days, which was 25 megahertz and had 8 megs of RAM, the CPU would look at the packet and then forward it, and then forward it out. Look at the packet and then forward it out. Look at the packet and then forward it out. So here's the thing. CPUs are slow. You can go out there and buy the biggest, baddest AMD EPYC server with 128 cores and 4 terabytes of DRAM. And if you want to mine Bitcoin with it, guess what? You'll spend $5 a day on this system burning electric, and you'll make 30 cents a day in terms of Bitcoin, because that's how slow CPUs are. Now, you pop 10 GPUs in this system. Graphics processors have much more power processing. Now, GPUs are now running a SHA-256 hashing algorithm. And guess what? With your 8 GPUs, which you have, which is really, really, really great. Fantastic, your 8 GPUs. Guess what? Now you're generating $2 a day of Bitcoin and spending $15 on electric. Now you go to Bitmain and you say, I want ASICs, which is now what switches use. They use ASICs. And instead of being able to generate $2 a day and spending $5 a day, they have a machine as cheap as can be. I mean, it's got like $30 of ASICs in there and a Raspberry Pi. You plug this thing in there and it's hardware. This thing can compute like 200 terahashes a second. It's extremely. This thing generates $30 a day and uses $1 a day of electric. So the point is, switches went from CPU to ASICs, and ASICs are lightning fast. So now you kind of get it. Look, I love AMD EPYC servers. I'm actually using my AMD Threadripper Pro 64-core workstation with a 0.5 terabyte of RAM and a Quadro A6000 card just to be streaming at you right now. And guess what? These challenges still have their problems. So, there's that. Now, Chris, you want to bring in the next one? Robert, everybody calls it a trunk. The term trunk came from actually voice as a trunk port. Link aggregation is extremely different than a trunk. Link aggregation is when you bundle multiple links together. A trunk port is when you put multiple VLANs on a single wire. Now, what you might be confusing is, in many cases, what we do is we create a link aggregation group and then turn that into a trunk. So it goes back to that same problem I was trying to tell you before, with regards to, the router and the stick being like one of the worst ideas we had. And here's the reason. Let me just create a new slide. A trunk is anytime you push more than one VLAN. So you got a switch here. That's the wrong one. Never mind. So we've got a switch here. It's got 10 VLANs. We got another switch, which has 10 VLANs. Now we got one wire between them. It's a trunk port. Always, whether you're in a Juniper router, a Cisco switcher router, all of them, it's always called the trunk port. Now, what we can do is we can bundle multiple trunk ports together, and we can create like 3 or 4 of these together, and that's what's called a link aggregation group. We put multiple wires, and so now what we have is a link aggregation group, and all a link aggregation group is we have multiple wires together looking as one. But now what we have to do is we can create that, but we still have to turn that into a trunk. And the trunk is what happens when you put more VLANs. So you can have a trunk port that's also a link aggregation group, or you don't have to. You could just have a link aggregation group that just bundles 10 gigabit Ethernets for a single VLAN for speed. But if you ever want to push more than a single VLAN, then what you have to do is as follows. If you ever want to push more than a single VLAN, you need a trunk. So you can have a link aggregation group, which is just multiple bundled links, or you can have a trunk on a single link, or you can have a trunk on a link aggregation group. That's really what we're talking about. That's exactly what we're talking about. Okay, so if any of you want to kind of see how we would configure some of these things, let's play with it. We're going to create a new little mini lab over here. Warning, select time to rename. All right, we'll figure it out. So let's go back to EVENG, which should be coming up right now. I'll work on it. We're almost there. Bear with me. Okay, we are up. We are running. We got our routers back and running. Our labs up and running. Apologies. It's really hard to give a presentation in front of an incredibly large number of people, and at the same time, to let you guys know, we're gonna finish around 2:30 today. We're gonna head back up on Tuesday. There's some critical advice some critical things that need our attention, but we will go long and strong next week, and it will be a ton of fun. So let's make sure we have some fun over here. Let's get involved in some of the things that we're doing, and let's have some fun with it. So let's create some routers. We'll create a couple of static routes. What do you mean? So base lab. Let's have some fun. We're going to enjoy ourselves. And in this class, if any of my disciples are on this call and you actually got the message from Chris, if you're able to assist, that's great. If not, totally understand. So over here, what we have, we're gonna have another Cisco router. Let's make 2 of them. Let's make 3 of them. Since there's a little bit of a confusion on the static routes, the dynamic routes, on why we're doing what we're doing, so let's have a little bit of fun. We'll plan on it. Heck, if you want, we can even create a router on a stick. Let's do that. Let's do this. Let's do a little bit of routing, and if we have time, we'll create some routing on a stick. So let's create a wire between these 2. Let's create that's perfect. Let's create a wire between these 2. Perfect. Let's boot up our routers. And while we're doing this, everybody, if you can type #CCNA while our routers are booting, then we're going to have some fun. And I'm always in for fun. Fun's always good. No problems about fun stuff. Let's add a switch while we're at it if we have time to do it. If not, I'll be doing some switching stuff with you. And while we're at it, let's add another link. We'll add a link between this page. Okay, so now we've got some devices, and let's have some fun. Let's just turn them all on, since hopefully I can do some really cool lab stuff today. Start. Debugging and troubleshooting while presenting. I must say, this is cool. So while we're here, let's do this. Oops, that was not what I meant to do. Okay, thankfully this is here. So let's get into our first router. We'll press enter. You guys are going to tell me in the, I want you guys to actually tell me in the chat box, what are going to be my next classes. So I want to go configure this router, my first router over here, right? It's coming up. We got to configure it. So I want you guys to help me. So everybody in the box, are we going to use this ridiculous initial configuration dialog? Yes or no? Why? Because we want to set it up the way we want to set it up. So let's talk about what that actually means, setting it up the way we want to set it up. Okay, our device is coming up, coming up, coming up, coming up. Life's good, it's coming up. Okay, it says router. So should we leave it router or should we make sure we don't get lost? Not sure what's going on here. So, okay, you can see me again. So, okay, so not really sure what happened over there, but all is good. So now we're over here. We're in this particular position, and our device is up. So what should we put over here? And we should configure this thing, right? Should we put a host name on it so we know what it is? Let's call it router 1. We create a loopback address so we can find this. Loopback 0, of course. Let's give it an IP address. Let's call it 1.1.1.1. That is, everybody, a /32. Okay, we're going to do a no shut on this. Now, what kind of an interface do you think we should use for our WAN link? How many IP addresses could be used here? How many are possible in a subnet? 2, right? 1 on each side. So let's do this. Let's go to interface, gigabit int G0/0. Let's come up with another subnet. Let's use the 192.168.1.1, 255.255.255.252. We didn't put an IP address. So how do we get to the beginning of the line, everybody? Control A. Control A gets us to the beginning of the line, and we type IP ADR for address, and poof, let's turn the link up. No shutdown. Okay, config T line VTY 0/4. This way we can tell them this. Let's create a exit. Let's put an enable password. Cisco. All right, we're good. Router 1's all configured. So what kind of interfaces do we have on this? Okay, as we can see, we've got our gigabit Ethernet port, which is up. And we've got our loopback address, which is up. So good stuff, huh? Now let's go over here. Let's go to router 2. Let's make this router 2 work. Now router 2's got a couple of interfaces on it. So it's asking us, everybody let me know, hashtag CCNA in the box if you're having fun. So it's saying, should we enter the initial configuration dialog? No, we shouldn't. So let's type no. Chris Leo may be able to help in that short time. So let's configure this thing. So we got to get to enable mode, right? So how do we configure? We type config T. Now, on the last one, we'll name it pizza because I saw Ruben came up with the host name pizza, and I think that's kind of perfect. So let's do this. We're going to create a loopback address on here for management, L00. We'll create 2.2. Let me give it a nice IP address. 2.2.2.2. I probably should tell the IP, ADDR, 2.2.2.2, 255.255.255.255.255. No shot. Now let's look at the Ethernet interface that goes back to our last one. That's G0/0, G0/0. Now, what's this IP address on this /30? 192.168.1.2/30. So, /30, 192.168.1.0 used by the network, 192.168.1.1 used by the systems, and then we have 192.168.1.2. So let's pop that on there. Config D. We don't need to do this. We just should go to interface G0/0. Put an IP address on it. 192.168.1.2, 255.255.255.252. No shutdown. Now we also have an interface that's going to be pointing to router 3 over here. It's G01. We should probably just use the next subnet, right? So let's use the next subnet. So in this particular subnet, we're going to go to, I already forgot the name of the interface. This is good if you remember the interfaces. So we're going to go to interface G0/1. Then what we'll do, we'll put that on IP, we'll give it an IP address on the next subnet. That should be 192.168.1.5, 255.255.255.252. No shutdown. Line VTY. Sure. Now, what you should do whenever you're finished, you make a configuration. For the exam question answer is, how do you take the running configuration and copy it to the startup? The exam answer is copy. I'll show you right over here. We probably should put a host name on it too. So when you want to save this, you could do, this is the official one, copy running -config to startup -config. That is your test answer. Copy running config to startup config. Destination, yes. And it's going to save it for you. Okay, so we've copied it to the running configuration. Now we should be able to ping across the link, right? We should be able to reach 192.168.1.1. Might we lose one? Ping. Bang, 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 bang. Okay, we lost that one. Everybody, why did we lose that first ping? What is that obnoxious screaming? Who has the MAC address for this thing? What's that called? Everybody pop it in the chat box. Alexandra Polikalo Imapolia Menos, which means Alexander, great job. I'm extremely happy. He just happens to speak Greek and he's here, so why not? So excellent, excellent. It's in the ARP cache. That's the problem. ARP, we lost one due to ARP. So now let's go to our third router along the line, because this is cool stuff. We want everything to be awesome, right? Let's go to our third router. Now, I heard a really creative suggestion for the host name. No, we're not going to enter this ridiculous automatic thing. Of course not. We want to do it ourselves. We want it to work. Okay, we're having fun. All's good. Good, 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 good. Okay, so now we're waiting for this slow router to turn itself on. And now you know why switches are fast and routers are slow. Okay, you can see it. Okay, enable. Let's go to the configuration mode. Let's change the host name. I saw the most creative one, PIZZA. People like pizza. We eat pizza in Greece. People eat pizza in people in Italy, South America, US, everywhere. People eat pizza. So let's name the host name is pizza. Okay, let's create a loopback on this. So interface loopback 0, IP ADDR 3.3.3.3, 255.255.255.252. Oops, that was the wrong. Nope, that was the wrong subnet mask. So let's see. Show. Let's see if I overrode it. Show run int L00. Okay, we got the right one. Good. Big P. Now let's go over here. Now we're over here. We got this gigabit Ethernet 0/0, right? Int G0/0. P GDR. Now remember what's it on the router 2? On the connection link? Show, because it's got to be on the same subnet, right? Show IP int brief. Okay, so over here, what are we seeing? What are we seeing, everybody? We're seeing that we needed to be the next one in the same subnet. Well, if we previously had 192.168.1.5, and the subnet goes 192.168.1.4 for the network, and then we've got 5 and 6 as usable addresses, and the broadcast is .7. Now we know what address goes here. Now while we're at it, let's create another loopback. We can generate some routes. Okay, so let's look at the interfaces on this. You guys are all going to know routing by the end. Let's ping across this link. Might we lose one ping across this link? And if so, why? Again, pop it in the chat box. You guys got it last time, so I'm pretty excited. So let's see, 192.168.1.5. Lost? Bang, 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 bang. And that's what that little exclamation point is called. It's called a bang. So all of it. So now let's look at the routing tables on this one. Show IP route on this one. It's got our locally connected stuff. Now we got router 2. Let's look at the routing table on this one. Now let's look at the routing table on this one. Note, what are all the routes? Excellent, Chris. What are all the routes over here? The routes are as follows. So IP route. All these routes on these devices say C or directly connected. So here we're on pizza. This guy has a 1.1.1. Can we ping it? Of course we can't. Why can't we ping 1.1.1.1 from 3.3.3.3? What does 3.3.3. know? What doesn't it know? It doesn't know how to reach 1.1.1.1. So what if we did this? Let's go to router 2. Can router 2 ping 1.1.1.1? Of course not. Why not? Why can't we ping 1.1.1? Albert, you got it. We don't have a route. We don't have a route. So if we go to router 2 and type config t, IP route 1.1.1.1, .0.0.0 with the next hop of 192.168.1.1. Oops, sorry, I got the mask wrong. Now, look at the routing table. Now we have a route to it. The question is, do we have a route back? Let's try it. Ping 1.1.1.1. We can reach it. Why? We have a root. That's all it took was a root. So if we're on router 2 and we want a path to 4.4, we could do this. We could do IP root 4.4.4.4 255.255.255.255. Pick the next hop. What's the next hop on this device? It is going to be .6, 192.168.2.6. Oops, wrong subnet. That's not going to work. So let's do this. Control A. And take us to the beginning. Let's get rid of that line. Why isn't it going to work? It's on the wrong subnet that I gave it the next hop. It should be 1.6. Let's make sure that's the address that's sitting on this router. 1.6 it is. Oh. Can we reach it now? Yeah, because we have a root. So when we deal with this, it's this. Now, what happens if anything breaks? Is a static route going to reroute against it? Is it going to self-heal? No. The reason I try not to use static routes is as following. You see how these routes are here via static? So now I want you to see something. See this 1? That's the administrative distance or how believable the root is. So the router figures this to be pretty good. So let's get rid of that. Now, let's actually do that. Let's look at the actual routes in here. We're going to get rid of the static routes. So we'll do this. We'll do a config T. We'll do a no. And then we'll copy this in. And then we'll do a no. And then we'll copy this in. So what could we do instead? We could use dynamic routing. Anybody have a favorite dynamic routing protocol they'd like to use for right now? We'll probably should start with an interior gateway protocol, and we'll work our way up through exterior gateway protocols. You guys like OSPF? You guys like EIGRP? What is it you guys love? Okay, so now let's use this. Let's use EIGRP. Router EIGRP1. That work? 3.3.3.3. Network 4.4.4.4. Actually, no, let's just do 4.0.0.0. No, let's just do 4.4.4. We'll have to play and see if I configured our EGP right. Because you know when the last time I used the EIGRP was? About 20 years ago. I think I was playing with it the other day just for fun. See if I did it right. If not, we'll switch it to OSPF 1. See if it worked. If we got any routes. Okay, so now look at this. When you look in the routing table, you can see that 2.2 is directly connected to the router. You can see that 3.3 is learned here. Now, when you look at 3.3, you see this thing that says 90. Now, that's what Cisco calls the intermediate distance. So 90 is a number. The lower this number, the administrative distance, the more the route is believable. Now, this is the actual cost to reach it. So now, do you think we can reach it? Can we ping we should be able to ping anything in the routing table. So 3.3.3.3. We reach 4.4.4? We can because we have a path. So if I didn't give you a route, so let's go back to this routing protocol and let's just show you how easily we can secure this device. So let's do a show run EIGRP. Let's look at our routing configuration over here. Note, I advertised 3.3.3.3. And realistically speaking, I didn't even tell it to not do an auto summary. Realistically speaking, I normally would. And the reason I didn't is in this particular version of iOS, it's still showing us the first thing. It's no longer summarizing by classful boundaries like it would have 20 years ago. Otherwise, I would have had to type no auto summary, or technically no auto dash summary. But I didn't need to do that because the default is not to do that behavior. So let's go to router EIGRP1. Let's do a no network. Now, I just removed, everybody, the BGP or the EIGRP for the 3.x network. Are we going to see it over here? Let's see. See if we can reach the 3. Oh, it's not there. Can we ping it now? Can't ping it. Okay, so look at this. Just look at this. We literally speaking, were able to make it that you couldn't reach anything by removing a route. Now, when it comes to security, firewall, good. IDS IP system, good. Access control list, good. No route, can't reach it. So, if you realize exactly how much we can do on the routing side. So now let's go to router 1. And what heck, while we're at it, let's do router EIGRP1. And now we've got our router EIGRP1. Let's put network 1.1.1.1. Let's also talk about, let's add the 192.168, 192.168.1.0. That was fast. Look at that. We can see the 1.1, the 2.2, and the 4.4. Where is 4.4? 4.4 is actually over here. So what? Let me show you what's going on. Let's have some real fun with this. Let's go to route. Let's go to this one. Don't do this in production. We're going to do a debug IP packet. Over here, we're going to ping that 4.4.4, the 3.3 that we can. Or 4.4 rather. Oh, I probably should have enabled that. Okay, so what are we saying? What are we looking for with this? We can see that the source here reached here. So we can see it going through. No debug. Now let's go to the router in the middle, R2. Let's do a debug IP packet on here. Watch what it does. Now over here, I'm going to ping the same 4.4. But what's going on? Let's watch. So right now, what are you saying? 224.0.0.10, that's EIGRP messages, EIGRP messages. Now I'm going to send an ICMP echo through this router. Oh, it would actually help if I left the oh, that's no, I don't want to run this one. Sorry, I wanted to go to the middle router. Okay, so let's do it again one more time. Not on this one. Okay, so what do we see? We can see, wow, we can see the 1.1. You know what, it was too fast. There you go. See which. No, you know what? Shut that off before we go nuts. So you can see what's going on. Now, let's pretend we could use another routing protocol. So let's just say over here. Now I want you to look at this. So when we get to router 3, which is called pizza. Now look at the routes on this routing table. Note what you see. You see connected, learned via EIGRP, etc. What if, for example, we had a route that we didn't want to inject, that we redistributed from another routing protocol? So redistribution is like translation. So I call Ivadoikia. Ivadoikia's native language is Bulgarian, whereas mine is Greek. So, it's generally best to speak to someone in their own language. So, you just got to keep that in the back of your mind. So, but if I really wanted something that she spoke in Hungarian or Bulgarian or all the amazing languages that Ivadoikia speaks, in order for me to understand a language that's not Greek or English, I need a translator. So keep that in the back of your mind. I need that translator. So we can translate between routing protocols. So let's do a show running config. Let's look on running config on here. And what I can do is I can actually take information from one routing protocol and integrate it. So if I did this, if I do a config t, and let's just say I went to router EIGRP1, here, what could I do? I could basically take a connected interface. You have to, whenever you take the information from one routing protocol to another, you have to tell it the metric. Now, what are we going to see? I just took that redistribute connected. Now, if we go back to this router and I look at it, oh, wait, now I see the 3.3.3.3. It says D, but it says something called EX. That means externally learned or translated. So Ivadoikia's native Bulgarian got translated into Greek, and we're now sharing some feta cheese, and we're happy as can be. Now let's look at this route a little more. Let's look at where it says 170 over here. That's the new administrative distance, and here's the new metric. So let's take some questions for about 10 minutes, and we are going to reconvene on Tuesday and have a networking party. Have a networking party. So let's do this. Let me find StreamYard real quick, Chris, because I've been in about 6 different browsers. Mike, how does an interior gateway protocol function from an exterior gateway protocol? So, Angela, there's a lot of things. Exterior gateway protocols, you have to manually define the neighbors, and they're slow, really slow to converge around a failure, and they're designed to take in millions and millions and millions of routes. Now, an interior gateway protocol like EIGRP, how fast was it? The second I did redistribute connected, 2 routers away, I had a route to it. So interior gateway protocols are designed to be fast, 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 where exterior gateway protocols are designed to be scalable, scalable, scalable. Awesome question. Chris, bring in the next one. I mentioned the wait. Well, actually, I don't want to use wait, and I didn't use wait. The only time I will ever use the term wait is because it's a BGP parameter. What I did use is believability or the trustworthiness, and I used the term administrative distance. So administrative distance is how believable a route is according to what you've told the routers, or if you're using the defaults, what Cisco told the routers. So Cisco will say EBGP or exterior BGP is more believable than EIGRP, and EIGRP is more believable than OSPF, et cetera, et cetera. So good question. you have yet to take the lesson for EIGRP, maybe what you ask what the syntax is, the same as it is for every other routing protocol. The reality is if you do the CCNP or the CCIE, they will definitely make you deal with some of the EIGRP routing protocols. So I like to use a little bit of that when I teach these classes, because there's more than just certification, which goes into getting hired. In fact, certification, I will tell you, is the least important part of getting hired. What it is knowledge, enthusiasm, attitude, communication skills, etc. So I'm trying to give you the more knowledge in case they ask you something on an interview. What is the practical use of a loopback interface? So if I were to remote access an Ethernet port and the cable goes down, I wouldn't be able to access the Ethernet port because it would go down and the IP address would go down. So we create a loopback interface to be the router identifier. Remember, OSPF and BGP have router identifiers, which is based upon the loopback address. So it's an address. If we've got 10 links to a device and 9 of the links fail, we can still reach the loopback because it never goes down. That's logical. So it's management. Why do we assign a /32? Because we only have one host. So if we do /32s, I can create basically 255 out of a single class C network. Very efficient for IP use. Good question, though. How can you relate this to cloud routing? It's 100% identical, Chi. Nothing's different. Everything is the same, 100%. So if you don't understand this, nobody understands cloud routing, because routing goes to the next subnet based upon routing tables. It's identical. Chris, you want to bring in the next one? What bearing does cost have? The cost is how hard it is for you to get somewhere. So if this link costs $1 million and this link costs 1,000, I'm taking the link that costs 1,000. That's just how ugly it is to get there. But the question, let me go back to that last question about how does this routing relate to cloud routing? And I said it's identical. That's why people that have 10 AWS certifications still can't get hired as a cloud architect unless they know the network of the data center, because this that we're talking about right now is identical to the cloud, and it is never, 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 by any stretch of the imaginations, it covered in any of the type of cloud computing certifications. Even the advanced networking doesn't cover any networking. It's honestly, it's like an intro to an intro to an intro to an associate network, of course. Linux Charmer, why are so many ISPs using intermediate systems to intermediate systems over ISPF when picking the two? Actually, Linux, that's not exactly true. I will tell you that, say, CenturyLink in the US is using it. And I will tell you, of all the ISPs that I've designed, I've dealt with 2 that were using intermediate systems to intermediate systems compared to the other 11 that were actually using OSPF. Why are some of them using intermediate systems to intermediate systems? So when we're dealing with a link state routing protocol, specifically for MPLS, what we need as much data as possible. And when we use OSPF, we kind of need to use a single area. Or with intermediate systems to intermediate systems, we need to be in that single area because we're looking for the maximum amount of information in our LSAs, and in between areas we don't lose it. As it stands, intermediate systems to intermediate systems, which is really designed for CLNS routing about 2.5 decades ago, scales really well in a single area. So for that reason, because nobody in their right mind would ever design a single area link state routing protocol, until MPLS came along, then we needed all this extra information. Many of us have used this 30, 40-year-old routing protocol because it's really good at carrying information and it scales well. But most are still using OSPF. Angelo, these classes are so useful. Thanks so much for taking your time to share your experience and expertise. I'm so thankful to be able to be here with you.
There's not any more questions right now. So we'll see if anybody else comes in.
Okay, we've got about 4 more minutes until we have to go. Just to let you guys know, we have so much of an impact in the cloud computing space. We're so recognized for getting people hired. We're so recognized for understanding what's going on and cutting through the nonsense that, just every day, the media is reaching out for us. And apparently something major went in that one of the massive media people needs to speak to us. So apologies. These kind of things affect our lives every day. But, after being in the industry for 25 years, You know, it's just the kind of thing where every single day, if there's a problem somewhere along the line, they're looking for people to help. And we're one of the people that are on everybody's list. So apologies, just sometimes emergencies come over in life. General question, how long is the CCNA test? I think I did mine in about 60 minutes, but I would say it could be upwards of 3 hours. Will this be archived to the channel? Absolutely. We want you to come back and come back and come back. But I love the dog, by the way. Very cute friend there. Any other questions for us? If not, we are so excited to see you next week. Honestly, it's an honor and a privilege to be able to talk to you all. I want you all to have the best networking careers, cloud computing careers, etc. And you know what really excites me? You guys were filling in the answers with the ARP caches, with the routes and the routing tables. You guys have been really doing swimmingly. So good to see you, Jeannie. Sanchin. Everybody do me a favor, type hashtag CCNA. Marjan, it's good to see you. Nikhil. Anya, love that. Sharon, loving the CCNA. Alex, CCNA. Fintech, CCNA. Albert, yes, CCNA, exactly. Sanchin, CCNA. Brian, thank you, Mike and Chris. We were happy to help CCNA. Jeannie, CCNA over there in Las Vegas. Robert Welch, CCNA. Sean Ford, CCNA. I love this. Ruben, CCNA. It's good to see you, Alexander. Always good to see you, Vidoike. Thank you for all your Blue Wrench work. 7 Series Beamer, nice. Nitropan, good to see you. Reginald Dunk. Oh, wow, I'm so happy to see you. Reginald, haven't seen you in a little while. So it's good to see you. And Faisal, fantastic. LM, thank you, CCNA. Reginald Duncan, CCNA. Basir, CCNA. And Anthony, fantastic, CCNA. Mark, it's wonderful to see you. And Nitropan, thank you for all you're doing. Eric, it's good to see you, CCNA. Mr. Gee, love that CCNA. And thank you so much for thanking my team. They do so many things. Caroline, so good to see you. And Lennox, Carmel, good to see you. So nice to see you, Torty. And M. Thomas, CCNA. And Georgetta, CCNA, you are more than welcome. Wood, CCNA in Jamaica. Oh, that's a great place. Oh, that's going to make me, again, every time I hear Jamaica, it makes me think of making bammy and turmeric tea and either a curry or some jerk chicken tonight. Maybe some cauliflower, rice, and peas because I don't eat grains. Oh, that sounds just great. So everyone have a wonderful, wonderful day. Enjoy the weekend. Feel free to go back and rewatch things because I want you to become networking experts. And see you all again on Tuesday. Take care, everybody. Welcome, everyone. This is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers. And I'm super excited to be here with you for day 5 of our Cisco Certified Network Associate Bootcamp. This is a CCNA 200-301 bootcamp. It is a completely free CCNA 200-301, and this is the part 5 of our session. And what is this training that we're doing? We're training Cisco Networking Essentials, and whether you call this Network Administrator training or Network Engineer training or Networking for Cloud Computing training, networking is the heart of everything. So this is very critical cloud computing technical skills, and this is really some network skills training. And if you're a cloud architect, this is a critical cloud architect skill, and this is cloud architect training or network architect training, and really we'll talk about so many networking and cloud career tips. So I want this cloud network training to be really great because I want you all to have the best careers. So you could look at the CCNA course for beginners. You could look at this as Cisco certification training. You could look at this as a CCNA course for beginners. But really, what are we talking about? What is a computer network and networking and cloud computing and networking in general? And that's what we're here to talk about. And that's what we're going to be doing on this boot camp. We're going to be doing more and more and more networking. Let you guys know, in case you weren't here for the first week, we have the first 4 days available on our YouTube channel. And there's a playlist that covers a completely free CCNA program. So go back and see the previous days. If you haven't seen them, tell others, tell a friend. I want you to have the best networking training experience you possibly can. So just wanted to go over those things with you. Before we begin, I want to mention a few housekeeping things to let everybody know we have a completely free AWS Certified Solution Architect Associate and Professional ebook. The link is in the description below. Make sure you get your copy. It's completely free. I also wanted to let you know that this week on Thursday, we'll be holding a live How to Get Your First Cloud Architect Job webinar. You'll be able to come in, ask any questions about learning how to build your best career. We will tell you what hiring managers desire in a cloud architect. We will tell you the skills that you need to learn to get your first cloud architect job. We will tell you how to be the hiring manager's dream hire. We'll teach you how to skip HR to get your resume in the hands of the hiring manager so you can get that first job. And if it was a network architect that you wanted to be or a network engineer, that's the same thing, and you'll be okay in either case because we're going to follow the same strategy. So, I just want to get those points across to you. That's what we're going to be doing. Networking, Cisco CCNA training, the Cisco Certified Network Associate. But most importantly, the whole goal of this is to get you network hired or cloud hired. So let's kick it off with a hashtag CCNA. I'd like to see everybody type hashtag CCNA. When I see that, I know you're here. Deanne, we're super happy to help out. Ash, hello from Seattle. LM, it's fantastic to see you. Eric Stoltz, wonderful to see you. Marty Reamer, cloud hired exactly from Phoenix, Arizona. I'm loving it. Sadie, welcome. Hello. Sarah Ahmed, hello. So good to have you back and love the butterfly. And Marcy, so good to see you back. And Marcy, CCNA as well. Sadie, CCNA as well. LM from Mozambique, fantastic. And Jeannie, I'm always so happy to see you. Tom Orpheus, coming out there from the Netherlands, good to see you. Fantastic. Twinkle, CCNA, Alex, Kalisperasas, LM, CCNA. So this is wonderful. We're all here. We're all excited about Cisco networking, and I love networking, and networking is the heart of everything. The data center, the cloud, the network is everything. So let's have some fun with networking. Today, we're going to be getting involved in some troubleshooting, and we're following the official flow of the Cisco curriculum. Quite frankly, I would normally teach the things that how to work first before I go into troubleshooting. But like I mentioned, I want you all to be able to follow through that official Cisco curriculum and those official books. So we're going to follow this philosophy. What we're going to talk about now is we're going to talk about making sure that we know how to troubleshoot routing. And those are the kind of things we're going to do, and routing errors. So let's talk about debugging or troubleshooting. What is troubleshooting? Troubleshooting is when things go wrong, and trust me, they will go wrong, finding out what's wrong and how to fix it. And trust me, we will be doing a lot of that in networking. Now, we've got lots of ways to troubleshoot, but we're going to walk through a few things. The first thing we're going to actually do when it comes to troubleshooting is I'm going to show you how we walk through it. We're going to go step by step. So let's go back to our routers over here. And in this routers, let's pull up a couple routers. Enable, Cisco. I'm going to add a second router over here. Let's go to this router. Enable. Okay, so we've got two routers over here. Now, if we look at the routing table in router 1, you're going to notice there's a lot of routes here. So I added a couple of routing things over the weekend to make it a little more fun for you guys. So when we look at this routing table, we can see the following. We can see on this one router that it's got a connected, meaning it's attached, 1.1.1.1. So that's the loopback over here. How do we know? It says a C, which says it's connected. Now, after this, what else do we have? We've got this B, which means, look in the legend, it says BGP. So it means we learned this 2.2.2. route via BGP. So when we look in this routing table, we'll see a couple things. We see a 20/0. The 20 is the administrative distance, or how believable the route is. Now, with Cisco routers, the lower the number, the more believable. As it turns out, eBGP has got an administrative distance of 20, which is pretty darn believable. Given things like OSPF are, realistically speaking, 110. And you can see how this is a pretty believable route. So if we had two routes competing for the same subnet, We're going to choose the BGP because it's more believable. Now you can see we've got another one, 3.3.3 is subnetted. How did we learn that? DEX. So D means EIGRP, EX means external, meaning it was a route that we injected into EIGRP from something else. So how are we going to look at that? Look over here. There's a legend. D, EIGRP, EX, external EIGRP. So you can see that over there. Now over here, we can see a 4.4.4.4 because it's an EIGRP. We can see that via BGP, we've got this subnet, etc. We can see the subnet. So on this router, in the routing table, I should be able to ping 4.4.4.4. I can. Good. No? Actually, let's do this. Let's go to the third router instead of showing you this one. So let's look in this topology. We've got a router, a router, a router. So let's go to this third router over here. Let's see what we got over here. Called the router pizza, show running config. Let's see what's in here. Okay, let's look at the routing that we've got here. We've got EIGRP running over here. Okay, so we can see this. So if I wanted to go to ping 4.4.4.4, it works. Now let's say we go to this router, show IP int brief. Now if we shut down this loopback, right now I can ping this. And this is going to be something interesting. I want you to carefully watch this. Now, the second, if I type this down, shut down, it's going to shut off that interface. So we'll shut it down. Now we'll try and ping it. We can't reach it. So a couple interesting things. If it's not there, we can't reach it. So let's talk about a few ways that you can troubleshoot this. Let's pretend that 4.4.4 is a server. You get a phone call. Hey, Mike, I can't reach the server. What's your first step? Ping. Send an Internet Control Message Protocol message to the server, and if it's alive, it's going to answer you. Ping. We've got it. Life works. It's good. So that's how we look for things. The first call we get, we can't find something. What do? We ping it. We want to see if it's there. Now, if it's there, life is easy. We know it's awake. Now, let's pretend this was a server. And we just pinged the server. Let's go back to here. Back to our configurations. We'll turn it back on.
You're not showing your screen.
Control E. Now, very quickly, you'll see once at some point the routing protocols are going to converge, and what you see, you can ping it. So now let's back up because it's routing. But if this was a server, you'd ping it. Now, if I can ping the server, somebody gives you a call, the web server's not working, and I can ping that server. Is the network healthy? Everybody tell me in the chat box. If I can ping the server, even if it's not working, is the network providing transport to the server? Yes. Yes. If I can ping the server's up. So if I can reach the server, is it most likely a network problem or is it most likely another kind of problem? It's most likely another kind of problem. Now let's pretend I couldn't ping the server. Well, look at this network. There's 3 routers here. If I couldn't reach this router, there could be another problem. Maybe the problem could be with this link. Maybe the problem could be with this link. Maybe there could be a routing protocol misconfiguration. But we won't know that because we're going to have to debug that and troubleshoot that a little more. So by doing this, we can figure out what's there. So let's look at what the next step would be. If we couldn't ping this because it was shut down, we'd probably want to figure out where it gets stuck. Where's it lost? How do we do that? Well, if I send a message to something that's here and it's not working, I got to figure out how to get there. So I can do a trace route, and that's going to tell me how to get there. It's going to map the network. Now, this is working. Our network's working. So if I do a trace route, it should show us the full path because there's no firewall somewhere. So let's see what it shows us. Okay, it's telling us it's going. It's a little bit slow, but it's going to map out the network for us. Okay, I know the first router hop. It's going to show us the whole path, you'll see. I know the second router hop. And I'm there. 192.168, 1.6. Guess what? That's sitting on this router's interface. That's over here. Now, that's the path because 4.4.4 is on the same router. So see this protocol that we just used, this trace route? It uses something called the Internet Control Message Protocol. Why do we love the Internet Control Message Protocol so much? It helps us figure out what's going on with our network. Now, you see how I just mapped the network like that? This is great. It enabled Mike, the network administrator for the day, to troubleshoot what's going on. But I just mapped the network. Just like that. I can see it. I know what's going on. So if any of you wanted to go to a command prompt on a Windows, you can type CMD and go to a command prompt. And if any of you are on an Ubuntu system or a Red Hat system or Mac, you can go to the terminal and do a trace route to www.amazon.com. Note, go ahead and do it, all of you, or Cisco.com. I don't care. Go and do a trace route. Actually, you know what? It's a great experience for you to do it. So go do a trace route. And if it's on Windows, it's going to be trace RT. And if it's on a Unix or Linux system, it's going to be trace route. And do trace RT or trace route www.cisco.com. Now you're going to see something interesting. Poof. First, you'll see the first hop. You'll see the second hop. You'll see the third hop. You'll see the fourth hop. You'll see the fifth hop. And then somewhere, you're going to get this star, 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 star. And what does that mean? It means you're not getting any information back. So why might that be when you do an internet-facing trace route? Because what happens is, do you see the way I just mapped the network? This is not good from a security perspective. It's brilliant from a troubleshooting perspective. But if I know all the IP addresses of all these routers, I can actually SSH or telnet into these routers, which is pretty bad, which means a hacker could do this to map the network. So when you go do a trace route to a public-facing internet site, you're going to see hop, 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 hop. And they're getting asterisk, asterisk, asterisk. Next hop, asterisk, asterisk, asterisk. And that's what's going on is the firewalls are blocking the ICMP echo reply to that message. And by doing so, it doesn't let you map their network. So this ICMP thing is a beautiful, beautiful, beautiful thing, but can also help you get hacked. So it's a matter of knowing what to use, when to use it, and why to use it. Oops, that was not what I meant to do. So that's why we're kind of doing these things. So one of the ways on these routers we can do things is we can do what's called an extended ping. And by using an extended ping, we can check our routing. We can source the address from something different. We can send it of a certain packet size. So let's walk through how we're going to do this. I want to show you the different options of a ping because you might need to do lots of cool stuff in your system. So let's just type ping and then enter. Now we could type a protocol. In the old days, it would be IP, IPX, AppleTalk, etc. Target IP address. So let's say we do the same 4.4.4. Now we can send 100 pings instead of 5. We can change the size to 200 bytes. Time in seconds, let's say 2. Extended commands, yes. Let's see what we can do here. Ingress ping, we're not going to worry about it. Source address, wow. Instead of using one of these addresses, let's say we do it from 1.1.1.1, 1.1.1.1. Type of service, we don't need to change it. We don't need to set the fragment bit in the header. Validate, no. Send a standard data pattern. We're not looking for anything complicated. Sweep a range of sizes, sure, why not? Sweep minimum, blah, blah, blah. But can it work? So you see, this gives us a much deeper test. We were able to send bigger messages. We changed the source IP address. Saying this is kind of cool stuff. We lost one. We lost another one. That's pretty darn good. We're getting some really good network throughput over here. We're changing all kinds of sizes, and we've got no problem. This is a very healthy network. All right, we don't need to keep going on with this forever. We'll see. Oh. I think I set that one to go a wee bit longer than I necessarily wanted to go with all those pings, but we'll let it go through its ping and we'll go back to the content. But that's what I wanted you to see. We can do multiple kinds of pings so we can really source our information. And you're going to be hitting content delivery networks like Akami or Cloudfront or Cloudflare when you're going to be dealing with any of these environments. Okay, so let's get that thing to come back to where we want it to. And then where did this thing go? Hold on. Bear with me 1 second. Okay, so let's see what we want to, let's see what we should go through next. We walk through the trace route command, walk through the trace route, some more trace routes. Let me show you a different way to do a trace route when this router is back up and running. We can also do what's called an extended trace route. And after we get to the troubleshooting, we're going to start to get into some really interesting stuff. Okay, so let's go back to here. Let's go look through this. Now we've got our router over here. Make sure we're on the router. Get to enable mode. We rebooted the router, so let's see if all the routing protocols are up yet. They're clearly not. Show IP route. We'll see when these things come up. Not yet. Let's make sure we don't have an erased router over here. We should have our routes very soon. Not yet. We'll figure it out. Give it a chance to converge, come up, that kind of thing. Let's see what's going on here. Loop back. All that stuff's here. We've got network 192.168 and EIGRP. We should be up and running. I don't see why we're not. Didn't mean to do that. Well, then we got to find out why not. So we get to do some troubleshooting, everybody. See, even in real life, when you don't plan on it, you find stuff that just doesn't work. So let's look at the routing table on this guy. That's looking pretty good. we're not getting this 1.1.1.1 thing for some reason. So let's show the run, and then let's go deal with the routing on this and figure out what's broken. So the loopback, everybody, is 1.1.1. The loopback 11 is 1.1.1, and the gigabit Ethernet is 1.1.1.1. So let's see what we've got over here, EIGRP-wise, and let's see what we've also got over here, routing-wise. We've injected the 192.168.1.0 into EIGRP, which is the LAN interfaces, and in EIGRP we have the network 1.1.1.0. So we should be forming an adjacency. We don't have any. So let's see what's going on router 2. Is router 2 not running any routing protocol? That's router 3. Let's go to router 2. Now, what's the IP address on router 1's LAN port? 192.168.1.1. So what's the IP address on this port? It should be 192.168.1.2. Let's see. It is. So can this ping the far end of the link? 192.168.1.1. Ah, well, the first one will be the ARP. The second one isn't working. Okay, so why? What's going on that we can't ping across that link? Why? What should we look? What do we see? What do we see? What do we see? Let's look at this routing protocol. Does anybody see any reasons why we might be having trouble coming across this link? Anybody see any reasons? If you see the reason why this isn't working, put the reason in the chat box. Why doesn't router 1 have any routes from anybody else? The routing protocol is configured, but it's not picking up routing protocols. Anybody know this? Sarah Ahmed, exactly. Robert Timmons, exactly. Ben Christopher, exactly. The interface is shut down. So, this is basic things. So, there's a point when you got to look at something, and when do you bring in the experts? What we're doing right now is not even level 1 support. This is where we've got the super junior people. Is it plugged in? Is there paper on? That's the level that we're dealing with. We'll get to more complicated things when we start talking about routing. That would be tier 2. And then I will show you guys when it's tier 3 or tier 4 or tier 5 when you got to send it to a networking person. So let's go fix this. Back to this router. Remember the interface that you said was shut down? And you saw that it was shut down with the shutdown command. So good troubleshooting, everybody. So interface gigabit Ethernet 00. Int G0/0. No shutdown. Now watch what happens. We're going to get some messages. They're going to show us the interface went up. Now we saw EIGRP make a neighbor change. We saw BGP make a neighbor change. So if we do a show IP BGP neighbor, we've got a neighbor and it's established. Everything's working. So now let's look at this. Show IP root. Look at that. Now we've got some from BGP. We've got some from external EIGRP, BGP, etc., etc. There is a /24, 192.168.1.0/24. Wow. So this router's got a bunch of /30s over here. It's got this /30. And this is the IP address on this. It also has this /30. Now when we go to this other router, we see this /30 and this /30 and the 192.168. Let's go to the pizza router. It's over here. Let's do a show IP interface brief. Again, it's got another 192.168.1.6/30 subnet. So where is this /24 coming from? Why do we have a /24 in BGP? Well, I'll show you why. I'll show you what we did. Now, margin, this is still external BGP. So let's go to this the next router where I advertise this into BGP, and I'll show you what I did. Okay, it's not on this one. It was on the first route. I thought it was. Look at this thing over here. So BGP. Now in BGP, I tell it who my neighbor is. I told BGP to advertise the 11.11.11/32, and we'll talk more about this later. I told it to advertise, or at least put into BGP, the LAN interface. Aggregate address 192.168.1.0. So I told this router to send a summary route. So remember before when I had you guys doing subnetting and supernetting, and I said, this is how we take a bunch of routes down, and this is how we do this? With BGP, I could literally generate any kind of a summary route I want. So let's say I wanted even a better one, config T. Let's say I wanted to go to router BGP 1, 2, 3, 4, 5. Let's say I do an aggregate address 192.168.0.0 mask. See if it took it. No. This is BGP. So with BGP, what we did is follows. We're adding another subnet. So let's go to the next router over. Let's see if we learned any new routes. Look at this. Via eBGP, we learned 192.168.1.0. See, that's what's called the summary route. And if I wanted to, with BGP, I could only send the summary route. I could send a specific route on 2 different links, which is how we do traffic engineering. So summary route on 2 different links, or realistically speaking, go back and do the same kind of thing we're talking about. So that's the summary route. And that's why we taught supernetting as opposed to subnetting. So now let's go back to this particular environment. And the reason we're going here is this is reality. This is what you guys are going to be doing. In today's world, a lot of what you're going to be doing is going to be on the cloud, and that's okay. So let's now let's think about this. Now let's go back to this particular situation. And now let's look about a traditional, normal multi-cloud environment. You got your data center over here. You see? You got a cloud like AWS over here. You got a cloud like Azure over here. You got a connection, a private line, and a backup private line. AWS likes to call them direct connections for some reason. You've got a private line and a backup private line to Azure. And the Azure marketing department decided to make up the crazy name Express Connect for this. And then you've got some VPN backup. So you've got this, and this is your environment. But see, here's the goal. The goal is to have this send a single route, 10.0.0.0/16. And over here, maybe you do this. Maybe you have this, 10.1. 0.0/16. And then over here, you've got a 10.2.0.0/16. See, by doing this, that's what the whole point of that aggregate address is. You can send one route. And that way, or one route, you can send a specific route on this link, a specific one, and a backup. That's the whole point of what we're doing. All of this, and that's why we're doing it, is to traffic engineer our traffic. So, how do you reach these routers? Let's just make sure. So show run line. Let's go back to our server over here, and let's look at this configuration over here so we can see what we've configured in it. Let's look at the virtual terminal configurations on this. That's very important. Okay, so let's go to the pizza router. Let's look at the running config on this one. Okay, so watch this, everybody. On this router, if we do a show IP interface brief, shows us this. So we know on this router, we've got an IP address of 1.1.1.1. Now let's look at the routing. Let's look at the routing table on the pizza router. Show IP route. Now, if we do this, do we have a route for 1.1.1? We sure should. Let's verify it with a ping. Okay, now if I type 1.1.1.1 in here, does anybody know what's going to happen? It's going to transport me. And wow, look at that. I'm on router 1. If I leave this, look, I'm back to my router. If I do this, it's going to telnet or SSH based upon my settings, and it took me to the new router. I am on router 1. Now I can go look at that running. Now let's look at the routing table in router 1. It's going to be different than the routing table on this because I'm in router 1. Exit. So if I were to do a trace route, 1.1.1.1 on this bottom link over here, it's going to map me the path. There's a reason I want you to see the path. So I can see my first hop from here is the 192.168.1.5. Let's see where the next, which takes us to here, which takes me to .1, which is sitting over here. So that's the path. So let's say, for example, over here is where we needed to get to. So if we knew an IP address on router 2, show IP interface brief. Perfect. Let me show the running config to make sure I enabled the virtual terminals on this. Okay, perfect. I did. So what I would ultimately do over here is, if, for example, I did a trace route, and I saw in my trace route from here, my data got lost in this router, what would I do? I'd hop on that router. How would I do it? I'd pick an IP address from that router, 2.2.2.2. Oops. 2.2.2.2. That would open router 2. I'd go to router 2. I didn't set an enable password, so I can't do much. So let's set an enable password for router 2. Now let's go to this router 2. Wow, it took me there. We'll type enable. We'll type the password. And now I can configure this router as if I was local to it. So that's how we've been debugging routers. What do? We ping it. If we can't ping it, we trace route to it. So let's do a little more debugging and troubleshooting while we're here. I'm going to walk you through the way I would troubleshoot a server. It's not working. as opposed to necessarily just the Cisco view. So what we'll do is I'm gonna walk you through a little bit of troubleshooting live. It'll be fun. We'll do it real time and live. You never know what happens live. So let's say over here, we've got a network. It's going to look like this. Kind of a router. Now we got to make routers look like smiley faces because routers are nice, happy, sweet things. Okay, so we've got all our routers. We'll call it R1, R1, R2, R3, and attached to this, we're going to have a switch, SW, and here we're going to have a web server. So the server is going to be plugged into the switch. It's going to be in a VLAN. The switch is either a layer 3 switch or most likely it's a layer 2 switch, and we're now routing to this router. While we're at it, let's draw a link between these routers because it's fun. Let's draw a link between these routers because it's fun. Now you're here. You're the troubleshooting person. And somebody says to you, oops, that's not supposed to happen. Bear with me. Okay, so here you are. You've drawn this beautiful environment out. You get a phone call. Hey, Mike, can't reach the server. First thing I do, I ping the server. And it responds, problem solved. Next thing I do, I ping the server. No response. Now what? No response. My next step personally is going to be to ping the default gateway, which is typically the spot right over here. Why am I going to do this? Because if I can't ping the server, but I can reach the default gateway of that server, it means that either the server's dead or I've got a problem with the switch. I don't know yet, but if I can ping the default gateway, but I can't ping the server or the switch, something's wrong. So what do? I go to this router, and from this router, can I ping that server? And if not, I go to the switch and I look at the server. And if it's got a VLAN mismatch, for example, I can see it. If I can look at these two devices and see if there's an access list blocking something, I can look. But if I can ping this gateway and not the server, there's a problem with either the switch or the server, and that is obvious. But if I can't ping the gateway, I probably have a routing problem. So then I do a traceroute. Traceroute, www.mycatcindy.com. And mycatcindy.com stops at router 2. So I go to router 2, I check the routing tables, I start looking around, and that looks good. So I hop from router 2 to router 3. Look the routing tables back in that direction. I look the routing tables in the forward direction, and I find it. So that's what we're going to do. The first thing we're going to do is we're going to ping it. Then we're going to ping the default gateway. Now, when we ping these things, which do you guys think is a better address to use? So are we going to go do this? And let's say Ivadoikia's got a blue wrench. So am I going to ping the DNS name Ivadoikia? Or if I know that Ivadoikia is 1.2.3.4, her IP address, am I going to ping 1.2.3.4? Well, I'm going to tell you, right thing I'm going to do, I'm going to ping Ivadoikia's name with the DNS name, which is going to say Ivadoikia. And if that doesn't work, before I do anything else, I'm going to ping her address that I know to be 1.2.3.4. Why? If I can reach Ivadoikia via IP address, but I can't reach her by her DNS name, that tells me that there's a DNS problem, meaning whatever maps mycatcindy.com to an IP address, that's going to be the problem. So kind of keep those in the back of your mind. So ping the server. If you can reach it, we networking people are like, hey, life's good. Now, that doesn't mean it's all done, but at least that's the beginning of the troubleshooting. If we can't ping the server, can we ping the default gateway? Can we ping it by the IP address and not the name, which means it's a DNS problem? Otherwise, we're going to have to go router by router by router. We're going to be looking for an access list that's blocking traffic from one subnet to another. We're going to be looking at a missing route. You have a route to the location, but they don't have a route back to you. These are going to be the kinds of things that we're going to be dealing with and debugging and troubleshooting in these environments. But, we didn't go into a lot of detail on routing yet. And because we haven't done a lot of detail on routing yet, this is where we're going to try and get ourselves into some more challenging situations. So where are we going from here? We're going to go to OSPF, which is one of my favorite routing protocols and favorite topics in the entire world. But before we do, and we get into some heavy stuff, there's probably some questions coming from this last section. So what we're going to do is Chris is going to bring me these questions. We're going to answer them, and then we're going to get into some OSPF. And if you guys want, and we have time, I might be convinced to do a BGP webinar or a workshop or something like that too. So Chris, if you want to look through the questions that are out there. Angelo, what is the value of troubleshooting with a team of subject matter experts? A whole lot. At one point, do you call them as soon as you get stuck? Well, I would call them if I was stuck as soon as possible, Angelo. Now, granted, you may or may not have access to being able to call somebody based upon the service level agreement. But what I would do, first thing I could do would be I'd be calling for help. Now, the reality is there's always somebody to call. So, Angelo, what I like to tell people is to be good at your strength. Know your world. And then your network is your net worth. Become an expert at your thing, but find somebody in your company that can help, that's an expert in the other things. Build yourself a team. So where am I an expert? I'm an expert at debugging BGP and PIN messages. That's my world. When BGP is not working, lots of people come to me because I've designed it and it's my world. I'll do the same for OSPF, and quite frankly, I'll do the same for PIM sparse mode and multi-protocol BGP for multicast. Once it gets into switching, I'm calling my switching buddy. Let's face it, that's what I do. So there's always a value in troubleshooting with a subject matter expert. They will identify and find things that you won't. Not just that, you'll learn in the process. So always, always, always a great thing. What an incredibly good question there, Angelo. So Chris, if you want to bring in the next one. Margin, how can you check an access control list from the router? Well, first, there's going to be a point in this course, Margin, where we're going to configure some access control lists, and then I'll show you how you can look for them. But it's a great question. So we can configure an access control list on a router, and we will be doing it. It'll be fun. And it's going to be in the router where you're going to see it. Great question there, Margin. Chris, you can get to the next one. Absolutely. Everywhere in the entire networking world for the most part, /30 for WAN and /24 for LANs. Excellent, Margin. Chris, you can get to the next one.
Waiting on some to come in.
Wow. And we're getting through without a lot of... So NetStat is different. NetStat, and depending upon the kind of computer you're actually on, NetStat will either showing you open ports, and it's dependent. So if you do NetStat minus RN, that shows you the routing table that's sitting on your computer. Ping is an ICMP echo that says, hey, are you there? And it replies to it. So ICMP, or Internet Control Messaging Protocol, is part of the TCP/IP protocol stack to find stuff. NetStat is basically giving you the status of what's going on your Unix, Linux, or Windows machine. Traceroute versus ping. Ping is me sending a message to Chris Johnson on the other end. Chris, are you there? Yes, Mike, I'm here. Traceroute is, I want to go find Chris. So I send the traceroute, and I see that I leave my house, and then I go to FPL, and then FPL takes me to AT&T, and then AT&T takes me to Verizon, and Verizon takes me to Chris's house. That's what you get out of a traceroute, Eric. Excellent question. Jacuzzi, can I expend the extended ping in a traceroute? Absolutely. Standard ping. Jacuzzi, are you there? So extended ping. I can, instead of, if let's say I'm a router and Jacuzzi, you're attached to my right arm, which looks like the left-hand side of the screen. So by doing this, let's say that's you, Jacuzzi. Normally speaking, the router would source the interface from the exiting interface of the router into you. But what if I wanted my nose, which is a loopback address, to be the source of the ping? So an extended ping or an extended tracer will give you the following abilities: to change the source address of the ping, to change the data size. Instead of like a 64-bit byte payload, you might do a 1500 byte payload. It may, with an extended ping, you can change the pattern of the data. You can change the source of the data. Instead of a standard ping is basically 5 ICMP echoes. An extended ping, we can send 5,000. So basically speaking, an extended ping is a ping that gives us the ability to basically tune it or customize it. Same thing for the trace route, and it's an excellent question there, Jacuzzi. An excellent, excellent, excellent one. Any other questions? So before we go back, I want to know you're not sleeping. If you can do the following: if you're having a good time, if you can like, comment, subscribe to the video, and then let us know that you're here by typing hashtag CCNA, and then we'll get back to the content. There should be a good 60 of you here. I should see a good 60 CCNAs, and then I know to get back to things because I know you guys are here.
While we're waiting on all that, we just had a question come in. I'll pop on the screen.
How does TTL affect ping? Great question. So when the ping, the ICMP message has a TTL, if it goes through enough, each router degrades the TTL just like everything else. So if you had a TTL of 5 and you're 6 routers away, you're not going to be able to ping it. Danica, Alexandra, Nyworld Gaming, Twinkle. Yeah, CCNA. Reginald, fantastic. Gabe, it's good to see you here. Sharon, Asaya, fantastic. Sarah Ahmed, Calibus, love that. Jacuzzi, fantastic. Sadie, CCNA. Tosin, CCNA. Leo Parati, CCNA, loving that from Brazil. Eric, CCNA. Abigail Marks, yes, CCNA for life. Networking should be with us forever. Angelo, interesting, thank you. Emmanuel, CCNA, fantastic. Williams, CCNA, wonderful. Eva Doikia, CCNA. Devin, can I explain UTP? On the first day, we talked about the pinouts on these cables. So Devin, if you want to go back to the first one, you can definitely look at the pins. Like I told everybody on the first day, I'm a network architect. I'm not an admin person, and I've never made an Ethernet cable in 25 years of networking. Okay, so let's start talking about some OSPF. Now, and we've played with it a little bit along the way because I don't want to drag it out because OSPF is one of my favorite things. But let's talk about it. Routing protocols. They basically build you a map of the network so you know how to reach your destination. And when we talk about routing protocols, we're going to talk about two kinds. Distance vector routing protocols, which are terrible, and link state routing protocols. And what is a distance vector routing protocol? A distance vector protocol is Eva Doikia says, I have the route to this. And I say, thank you, Eva Doikia. And I say, Ash, here's the route. And Ash says, hey, Eric Stout, this is the route I know because Eva Doikia told Mike. And then he told me, and I'm telling you, Eric. And Eric says, Jafar, here's the routes, which I learned from Eva Doikia, from this person, from this person, from this person. So if you really think about this, if you've ever played the game Whisper Down the Lane and you say, I have a green bathing suit, and what somebody else hears on the other side is that you're a leprechaun, and it goes that kind of goofy. So, keep those things inside of your mind. Look at these things. So that's exactly what's going on. So that's what a distance vector protocol does. It routes via rumor. I tell you, who tells someone else, who tells someone else, who tells someone else. Well, if you've ever played Whisper Down the Lane, how accurate was that? Not so much. So distance vector routing protocols such as RIP, something called Cisco made called IGRP, and then another routing protocol that Cisco made called Enhanced Interior Gateway Routing Protocol, which they like to call a hybrid, but was predominantly a distance vector routing protocol. Those are the ones that route via rumor. Now, alternatively, we've got two link state protocols. We've got the one which we'll cover in this course, which is called Open Shortest Path First, or OSPF as it's named. And there's another one called Intermediate Systems to Intermediate Systems. They're very similar in functionality. Intermediate Systems to Intermediate Systems is a 30-year-old routing protocol, and it's typically used by some big internet service providers. And we love that. And realistically speaking, most systems, especially enterprises, are run using OSPF, or Open Shortest Path First. And it really doesn't matter if you're on Cisco, if you're on Juniper, or any other devices. They run these same routing protocols identical. So when you're on Cisco or Juniper or Palo Alto, or it doesn't matter if you're using network standards. So same way on the cloud, I say don't use this or this. If we avoid concepts like EIGRP, even though it's a good routing protocol, we can intermingle our networking devices with everything. So we're going to be talking about dynamic routing, and the whole point is to build a map of the network. So going back to the static route environment, I've got a link to Chris's house. Why, it's good. And I know how to get to Chris's house. And if that path is good, life is good. But if it's not, we got a problem. So maybe I'll walk you through one more time of the static. No, we did it before. So just kind of keep that in the back of your mind. That's what's going on, is we need to build a map that is self-healing. And because of this, we're using a dynamic routing protocol. And we're going to talk about the way these kind of things work. So let's look at an example. I want you to see what organizations look like. This is current routing. Now, organizations themselves are going to be running their own routing protocols internally. And this is what an interior gateway protocol is. So if you can look in this environment, we've got one organization that's running EIGRP. We've got another company that's running OSPF. We have another company running EIGRP internally. We have another company running EIGRP internally. And another company is running something called OSPF, which is what we're going to be talking to. Now, why does this work? Because organizations internally run an interior gateway protocol that's responsible for their routing. And they connect to external organizations through BGP. So inside of our organizations, we use an interior gateway protocol, EIGRP, RIP, OSPF, intermediate systems. But we connect external entities to via BGP. So when we've got our connections to the cloud, we don't run OSPF to them. Why? Because the cloud is an external entity. So we run BGP. If we connect to two internet service providers, I'm on a load share, we run BGP across both links for the same reasons. For the same reason. That's how, what, where, and why we're doing this. So keep that in the back of your mind. Now, when we're dealing with these algorithms I mentioned, we've got a distant vector, which is routing via rumor. We've got the link state. And how do link state routing protocols work? Link state routing protocols work via the following concepts. They send information about their links, and then the routers run a calculation. So let's talk about this. Let's kind of imagine. Let's imagine we had roads, and the roads all sent some special messages to like some fancy Google application that says, I'm here and up and running. 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 And then when you get in your car and you say, I want to go to Chris's house, you pop Chris's address into your GPS, and all the routes are telling the GPS, I'm here, I'm here. Then all of a sudden, a route gets blocked because there's a tractor-trailer accident, and the GPS basically removes that route and redirects everybody. And now you're being moved in a new way, and now there's an ice storm directly in front of you. The road tells this beautiful thing in the sky, hey, I got ice on me, I'm not safe to drive. Reroute. That's why we're using routing protocols. And that's how, so how do the link state routing protocols work, like OSPF? Every route that's there says, I'm here, here's my links, here's my links, here's my links, here's my links, here's my links. And if you know all the roads, You run what's called a calculation, what's called the shortest path first calculation on it, and it builds you the map, and you know to get there. So that's how I get to Chris's house. I get in my GPS, and it tells me, make a left, make a right, make a left. And I have to do that. You know why I have to use a GPS? Because it's Florida, and somebody's will be in an accident on the way of my house to Chris's. And if not, I get lost easy. I mean, really easy. You know, a static route to a static route to a static route, that doesn't work for Mike. I get lost. I can get lost in my own house. And it doesn't have to be that big. I can get lost easily. So I need those directions. I need a routing protocol. And guess what? Routers need cool routing protocols to get our stuff there, so they don't get lost like me. Now, what is this? All these things that we're talking about. If I say, road, I'm here, road, I'm here, road, I'm here, I'm here, I'm here, I'm here. It's called an advertisement. Yes, I'm here. Now, what is it called specifically? It's called a link state advertisement. Why? I'm sending you the state of my links. Up and running, up and congested, up and blocked, down, dead. That's the link state algorithm. So what happens is you got thousands of roads saying how to get here, how to get here, how to get here. They do something. Where are you going to store data? We have a website. We want to store transactions. Where do we put it? We put it in the database. Customer buying patterns, we stick it in the database. So where do we think we're going to pop in all these link state advertisements? A database. So now we got all these devices saying, I have all these links. We pop them into a database, and then we run this math calculation, and we determine the best path to the destination. That's all it is. That's exactly all it is in every stretch of the imagination. So let me show you what it's going to look like. In this environment, all these routers are going to be sending the status of the link. I got a link, 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 all my links. And then after everybody sees all these links, they run that calculation. So it's no different than the roads broadcasting to the magical Google thing in the sky. So that's what's going to happen. So we build a database and we run a calculation from the database. So, you know, let's talk about the process. For this to work, I got to know who I'm talking to. Now, I want to talk to Eva Doikia. It's pretty easy. She speaks actually exceptionally good English, even though that's not her primary language. Bulgarian's her primary language. She speaks Italian. She speaks lots of languages. It's pretty cool stuff. But, you know, that's the key is what are we doing? We're sending information and we're running a calculation on it. So, you know, kind of keep that at the back of your mouth. So first thing that's going to work. Let's say I want to, Eva Doikia's got the blue wrench. So I want to form a neighbor adjacency with her. Eva Doikia, are you there? What am I going to do? I'm going to send a multicast hello. Hello, 224.0.0.5. Hello, 224.0.0.5. Hello, 224.0.5. Hello, 220.0.5. And what's Eva Doikia going to say? Got this message, Mike. Hello, Mike. How's you and how is Cindy today? And I'm going to say Cindy's really good. The metric to Cindy is to get to my house, and it's a little further away because Cindy's in her own bedroom. And yes, Cindy has her own bedroom, even though she sleeps on my feet or on my chest or my head every night. But she has her own bedroom to sleep in during the day. And yeah, she's got her own blankets and she's got her own special pillows. And Cindy's a very pampered cat, but that's the key. So Eva Doikia, are you there? Hey, Mike, I'm here. Eva Doikia, would you like to exchange routing information? Yes, Mike, I'd like to exchange routing information. So I send Eva Doikia the routes to my subnets, the routes for my storage area network, the routes for my experimental network, the routes to my cloud, the routes to my workstation. And she's over here because I know Eva Doikia. She's great. She's fantastic. She's doing all kinds of cool stuff. And now there's that. And she also knows how to get to Cindy. And I even gave her the key via a route to the special cat food that makes Cindy really happy, the fresh shrimp and the fresh scallop cabinets, so she can even remotely cook it in the fancy IP-enabled oven and give my cat Cindy some shrimp and scallops, which makes my cat Cindy happy. And that's really what's going on. Is I reached out to reform what's called an adjacency. We have to become neighbors and agree to talk to each other first. So how does that happen? We send a hello message. We negotiate whether we want to get along, and then after that's the case, we do that. So what goes into this hello message? Well, tell you what, I'm going to show you. Let's And then I'll actually tell you, but let's have fun with it. We've got all these things, we can debug them. So let's go to router. Let's do this. Let's remove the EIGRP from these routers.
Make sure to share your screen.
Thank you. It's so helpful to have that eye in the sky. You have no idea. So let's say let's look at the EIGRP configuration on here. Okay, so we've got config T, no EIGRP, no router, EIGRP 1. Let's do router OSPF instead 1, because I want you to watch what happens. Let's do the network 1.1.1.1, mask 0.0.0. Let's put it in area 0 so you can see it. And then we'll walk through these other areas. And let's do the 192. Let's do this. Network 192.168.1.0, 0.0.0.255, area 0. Let's go to this other router, router 2, while we're at it. Let's get rid of its EIGRP configuration. We'll swap it out with OSPF. Okay, so we're going to be on router. I'm going to go to router run right now. And we're going to debug. I want you to actually see the OSPF message is going to be. So we're going to be debug IP. Okay, now on this router, you can see it sent a hello. Now, is it going to receive a hello yet? No, because I haven't fully enabled OSPF on the far link. So you can see right now on this link, hello, are you there? This is reaching out to Eva Doikia. Hello, are you there? Note, it's being sent to the multicast address 224.0.0.5. Now we're just going to see hello. We're going to get no responses. Now on the second router, router 2, once I put this interface in OSPF, we should expect something different. Oh, look at this. All of a sudden, we received a hello from somebody else from 2.2. We're sending some LSAs back and forth. Now we've got a database. Our things are full. We'll be able to do this. Now, if we go to this config to router and we do a show IP route, we're going to see some routes via OSPF. Can we ping that 1.1.1? We should be able to. We learned it via OSPF. Let's go to this router. No debug. See, as you can see what happened. Now, if we go to this router, show IP OSPF, we can see the link states, the database. It's got a database. And what do we see? We can see the link for 2.2. We can see where it came from. We can see how many seconds it is. We can see where our things are coming from. So we're going to talk about a couple of different kind of link states. They don't cover it in the CCNA program, but I might do it anyway. So what you're going to see is you're going to have a couple of kind of link states. You're going to have something called network links, and you're going to have links and then router links and then network links. So yeah, this is the first type of links which you get per link. This is called the router LSA. This is a network link which is generated by the designated routers, and then we're going to have a link which goes in between areas, goes intra-area links, and I'll show you what I mean by that. So now let's do this on this router. Let's add another loopback, and well, before we get to that, let's just see let's make sure everybody understands it. So what did we do here? We streamed hello, hello. As soon as we agreed hello, then we decided to be neighbors. Eva Doike and I, we basically shook hands. Then Eva Doike sent some scallops for Cindy, and I sent Eva Doike a beautiful t-shirt that had Cindy's photo on it saying, thank you so much for feeding me. And it was personally signed by my cat with her, really horrible handwriting, but it was cute anyway. So, that's kind of what's going on. We're building a database. So if you notice, the advertising router, what it used is it used the highest loopback address to be the, to be the router identifier. So kind of keep that in the back of your mind, that routers use a 32-bit identifier. And it's based upon the OSPF router ID that you tell it or the loopback address that you pop on it. So hello, are you there, et cetera, et cetera. So let's walk through the neighbor state. And we've got two routers like, hello, do you see me? Yes, I see you. And then after that occurs, what the routers do is they start exchanging LSAs. I've got this link, I 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 got this link. And then they're basically exchanging their databases. They share each other's links. And then after they do that, they run a shortest path first calculation. Done, done, and done. So let's talk about a couple of timers. The hello interview. How often you send hellos? Dead interval. How many hellos do you need to miss until you mark the link as dead? Pretty much it. So, a lot of times we make complicated areas mean, and then let's talk. So let's talk about this. So now let's talk a little bit about the architecture of OSPF. So I'm going to walk you through this. And realistically speaking, we do it in the following methods. Actually, before we do it, we may have a fair number of questions on this content. So maybe I should answer some questions. And then after the questions, I'm going to walk you through the database. So let's do that. Looks like we had a bunch of questions from what I can hear. Eric, I have no idea. Some are the highest loopback, some are the lowest loopback, et cetera, et cetera. Each protocol's got its own standard. Like lowest is what you use for a spanning tree, for example. LM, what does area 0 mean? That was what I was going to get to next. How does the router choose between an OSPF route and an EIGRP route? Wow, that is an exceptionally good question. So when you look at all these routes in the routing table, they have something called an administrative distance. So whatever the lowest the administrative distance is the answer. So when I showed you BGP had an administrative distance of 20, and I showed you that OSPF had an administrative distance of 110. If you learn the same route from BGP and the same route via OSPF, then you will choose the BGP route. EIGRP has an administrative distance of 90. OSPF's administrative distance is 110, which means that if you learn the identical route from OSPF and EIGRP, you will choose the ERP route because it's got a lower administrative distance. OSPF's is 110 and EIGRP is 90. So that's realistically speaking how this is working. Now, if you wanted to make OSPF more believable than EIGRP, you just reduce the distance of OSPF through the distance command, or you increase the distance of EIGRP to make it look less believable. But that's all based upon the administrative distance, and we'll be playing with that. I'll let you play with that in a lab. That's a good point. It's not typically something you do until the CCNP or maybe even CCIE, but we can play with it in one of the labs. Good point, Angelo. I'm happy to do that. Chris, you can bring in the next one.
That was it. I just wanted to make sure we took care of this before we got too far down any rabbit hole. in case we couldn't come back to it.
Okay, that's a great idea, Chris. We're going to go down some fun rabbit holes. So while we're at it, if everybody's here, type hashtag CCNA. Excellent. I see you guys are here by typing CCNA. I like knowing you're awake, you're alert, and oriented. You know, we take pride in our Cisco Certified Network Associate courses, our CCNA courses, the way they call it, or for the CC exam 200-301. We just want everybody to be successful. Okay, so now let's talk about what goes on. So with OSPF, you got to look at it this way. What's really going on is we're trying to segment our network. So everything we do is about scalability, 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 and more scalability. So the way OSPF works is we create something called a backbone. Now the backbone, these are our most critical routers, the most critical routers that we have. The backbone, these routers need to be the smartest, biggest, and fastest routers. So by doing this, these routers need to know everything. They're like the Oracle. They know everything. Everything. Like that song, Everything's Going to Be All Right. These routers need to know everything. And this is also, it's called Area 0. So LSPF specifies the ability to basically segment or modularize or decouple your network. So this is called Area 1. Let's say we make it Area 1. And there's some sci-fi thing they talk about Area 51. So while we're at it, let's make an Area 51. It doesn't matter. We can name our areas anything we want. We can make this an Area 2. And we can make this an Area 4, just because we chose to. Now what happens is each of these areas is connected to the backbone via a cable or multiple cables. So in this protocol, which creates a link state database, which stores the links in the router, it's not like we're going to be using MySQL or Postgres or MongoDB or things like that. This is just part of the routing protocol, and it's going to sit on the routers. So what happens is we're going to have 5 kinds of link state advertisements. There's more than, but we're going to talk about the 5. The first one is the ones that are generated by the routers. Hey, I'm here. The next one is generated by the links. The next kind of links, the advertisements are going to be links that we get from external areas. And the next kind of links are going to be things that are related to external entities. And we'll pop this. I'll show you what I mean by external. Let's just call this EIGRP. So in an area, you have access to everybody's information. What does that mean? Every router, every link in my area, I know about everything, 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 everything. And anytime anything changes on any link in the center, I run a full recalculation. So what you could imagine is if we had 1,000 routers in this backbone and we all shoved them all together, all these routers are going to be screaming, I got links, I got links, I got links, I got links, I got links going away, links going away, I got new links, links going away, new links, new links, new links. Imagine a database that's got 50,000 links in it, that's going and coming and going and coming. It's going to be recalculating. CPUs and the routers are going to go high, router's going to crash, and it's going to reboot, and your network is dead. So what do we do with web apps? We decouple them. Web tier, app tier, database tier. What do we do with networks? Core distribution access layers. What do we do with our routing protocols? We segment them and decouple them. So with OSPF, we have 5 kinds of LSAs. We have type 1 and type 2 LSAs. They are all the links inside of an area. Inside of it, the area 1, what are we going to have? We're going to have a minimum of a type 1 LSA. We're going to have a type 2 LSA too. Minimum we have to have there. Now, this backbone needs to have its type 1 LSAs. Needs to have its type 2 LSAs. One is based by the router, one is created by the link. Now, area 1 is not part of area 0. So area 1 is going to send a summary of its links. Now that's going to be called the type 3 LSA. I didn't make this up. I didn't make up these goofy names. But if you really think about it, every area must have its type 1 and type 2. Type 3, and the backbone has to know about this stuff. Now, let's say you wanted to tell OSPF about some routes you learned via another routing protocol, like EIGRP or BGP. I don't care. Although you wouldn't redistribute the entire internet routing table, but it doesn't matter. Heck, it could be a static route you wanted to redistribute. Meaning redistribute, meaning, so Eva Doike speaks Bulgarian. I speak Greek. Redistribution is translating Greek to Bulgarian. That's all it is. Taking the information from Bulgarian and turning it into Greek and vice versa. So that's what we've got here. So now when this stuff, and this stuff gets here, this is now called an external link. And an external link is a type 5. So anything that we learned externally is what's called the type 5 LSA, which means which is an external LSA. It would be helpful if I could type. And this is called the type 5. So the next type of LSA describes, and I'm going to describes which router can reach these external routes. So what's called a type 4 route is something related to ASBR reachability, and I will go over that right now. So here's what we've got. This is called the backbone. Any router that borders between the backbone and another area. So let's say we've got a router over here that connects us to this other area. And that is called an ABR, or a boundary router, an area boundary router. Because why? It's connecting OSPF to an external area. Now, this particular router, because it's bringing in something else, is called an ASBR. And realistically talking, it's bringing in external LSAs. So what we have in OSPF, we're going to have realistically 5 kinds of LS. Well, more, but I want to keep it relatively simple. We have the type 1, which are generated by the router, and the type 1 and 2 are generated by the router and network. They exist in all areas. Now, when area 0 will know all of its own type 1s and type 2s, but each additional area will only send a summary of its LSAs. So kind of in the distance vector, hey, Eva Doike, I've got routes to this, and she says, okay. And then Eva Doike tells her friend Abigail, and then Abigail goes and tells her friend, I'm drawing a blank right now. But anyway, you guys get the concept. So distance vector, route by rumor. So OSPF, intra-area, shortest path first algorithm. Intra-area, they use like a distance vector. Hey, I've got the routes for this. I've got the links for this. And then externally, you got that ASBR. So I know I went into way, way, way more depth there. Now, the next thing we have to understand is on regular links, we just have OSPF routers. But when we're dealing with something called broadcast multi-access networks, it's a little different. So if we had two routers and a serial link between them, but a WAN link, what do we have? We have a single wire. Life's really good, like my iPhone, just a cable. Everything is perfect. But now with Ethernet, we could potentially put 30 routers or 200 routers on the same subnet. We could. And if we put all these routers in the same subnet, we're going to have an election. And we're going to have one primary router. So we have a war. One router wins. And then we have a backup. Now what happens is you've got the designated router that basically sends the information. Okay, I got you. You're over here. This is the information. And it tells all the other routers on the subnet. And you've got a backup designated router. Why? Because 1 is none and 2 is 1. So you can't just have a designated router. You've got a backup one. So you've got a primary designated router. Hey, these are the routes. These are the routes. These are the routes. And you've got a backup designated router saying, hey, by the way, these are my links. These are my links. Now you know what we're talking about and why we have them. So we're going to have the concept of a backup designated router and a designated router. So if we go back to our things and we're running OSPF, do you think maybe we can see some of this stuff? Let's go see. Let's go find out. Let's go back to our server. Let's go back into here and let's walk through some of this OSPF stuff we can see. Enables Cisco show IP route. Let's make sure you can see them. We got some routes via OSPF. So show IP OSPF database. You can see that we only have a single area, so we don't have anything. I'm going to generate some other, I'll generate some external routes for you so you can see the LSAs in a minute. But I just wanted you to just see this, especially there. I just wanted you to get a feel for it. So you can see this. So now if we do the show IP OSPF neighbor, we can see a little bit about the neighbor. Now look, the neighbor is full and it says BDR, backup designated router, which means it's number 2 in the election. Well, there's only 2 routers, which really means it lost the election. So now if we do a show IP OSPF neighbor, the other one should be the designated router. And you can see full BR. Okay, so now let's do this. While we're at it, let's do a show running config. Let's see what we got in here. Okay, so let's do this. Config T. Interface. Let's create a new loopback. Loopback 1. Let's do IP address 13.13.13.13. No shutdown. Now let's go to our OSPF configuration. Let's put this subnet in there. Let's do the 13.0.0.0. Oops, the 13.13.13.13. 0.0.0.0. Now instead of putting in an area 0, let's put it in area 1. I just created a new area. Now let's go back to this router and let's see what we see. If we go back to the database, now look what we see. We see the router links, we see the network links, and now we see the summary link. You see that? Heck, while we're at it, let's add some external links to it too. Let's go to config T. Let's do interface, loopback 2. We don't have a loopback 2, right? Let's do network. Let's do IP address, IP, ADDR. Let's do 14.14.14.14, 255.255.255.255. You probably don't need to shut it down, but it's just my practice to do it. Now let's do this. Now router OSPF 1. redistribute, connected, metric, so say subnets, metric, 1. Now let's go back and look at our database over here. Now notice the database changed. You can see lots of things that are different in this database. Look very carefully first. The first thing you now see is you see the type 1 LSAs that you had before, the router LSAs, then you see the network LSAs, then you see the type 3 LSAs, and then you get this type 5 external LSA. What is that? It means it's not coming from OSPF, it's coming externally. We're learning it externally. And let's look at the routing table and see if it looks the same way. Show IP route. Now, when we look at the routing table, we're going to notice a couple of things. Let's look to determine the administrative distance over protocols. So this is learned via BGP 2.2. The administrative distance is 20. This is connected. So it's got no administrative distance because it's on the router. We know it's accurate. Now, this 13.13.13, it says an O, which means OSPF. But it doesn't look like this O over here, which we learned via OSPF. Instead, this O says OIA. What does that mean? It means it came from another area. We're area 0. It came from area 1. OIA. And now there's this subnet that I redistributed in. And it says OE2. So we go to our legend. O, OSPF. OIA, intra-area. E1, external LSA type 1. E2, external LSA type 2. Poof. Guess what? We're running external LSA type 2. And that's what we can see in the routing table. So this OSPF protocol is kind of cool, huh? It's fast. It works real well. It's really good. So on the LAN, like I mentioned, we've got an election, designated router, backup designated router. It's kind of like me and Chris. If I go down when I'm going on vacation next week, Chris is going to be there. He's going to make sure everybody is successful. I'm the designated router. He's the backup designated router. When Chris is gone, when Chris is covering for me next week, Leopoldo will be Chris's backup designated router. Whatever the case is, this exists in all parts of the world. We don't need to make routing protocols that complicated. We have an election. We've got a backup winner to the election. And then if we need to, we have a new election and everybody else gets there. So I kind of love this stuff. I think it's kind of cool. So what goes on is it's going to be like this. We have this election pattern. This person becomes the designated router. They all communicate back and forth to the designated router, and that's what makes everything work. That's why we do these things in networking. That's why we do it. So let's play with it a little bit. Let's think about the things. When you just form a neighbor relationship, hello, Eva Doikia. And she says, hello, Mike. We are in a two-way state. Just two-way. We're halfway there, halfway there, halfway there. Then all of a sudden, Eva Doikia gets all the LSAs that my cat Cindy sent her. She's got a picture of Cindy doing this, a picture of Cindy cleaning our fur, a picture of Cindy jumping up the stairs of my house, a picture of Cindy chasing aluminum foil balls, a picture of Cindy on her back, a picture of Cindy doing everything. Then what does it say? It says full. So, for example, and I drew a slide here. So we initially come up, Eva Doikia and I, and we're two-way. Cindy, the cat on my end, sends her all of her links. She sends all of her links about all that cool stuff that's going on in Hungary. I know how to reach all of her cool stuff in Hungary. She knows how to have a private conversation with Cindy the cat, can access my files, and everybody's happy. That's what we're talking about with these shortest paths first. So now, how does it work? How do you do it? So we do it as follows. Everybody sends a list of costs to their link. So if we know this link costs 10, and we know this link costs 30, and this link costs 60, we can aggregate a cost. So why is OSPF so useful? And why was RIP and all these old distance vector protocols so bad? It was the way they ran the calculation. So think about this. This is like the old distance vector, RIP. And we're going to swap it out. But let's just say we've got a couple of distance vector protocols. So, okay, we've got this via an old school distance vector protocol. This person tells this person about the route. This person tells this person about the route. It's not the most reliable thing in the world, but that's the way the distance vector protocols work. Now, how does distance vector protocols work? How far away is this subnet? Let me put an Ethernet segment over here. How far is this Ethernet segment away in RIP? 1 router hops, 2 router hops. That's a metric. Now let's pretend this is OSPF. Actually, let's do this. Now with RIP, let's add 2 links or a distance vector protocol. Now the top link over here in a distance vector protocol is 100 gigs. The bottom link over here is 1 gig. Not even sure. Well, I don't even know how I got that upside down, but I'm never going to figure out how to straighten it back up. So, so in this particular case, we've got a single 1 gig link. In a distance vector protocol, which direction do you take? Do you take the top link or you take the bottom link? It's random. One packet goes over the top link, one goes over the bottom link. Let's make this even worse. Let's pretend this is a distance vector protocol. We've got these 2 options. This is 100 gig. This is 1 gig. And you've got a choice where you can go straight from this router to the server. Or what you could do is you had the same server and you had a 100 gig link to the server this way. And this is 100 gigs, which is faster from a networking perspective. Assuming, hold on while we're at it, let's just add another one of these. So in this particular environment, what's the best path for this? I want you guys to tell me who has what's the best, most efficient path to this route, to this web server for a high throughput environment. Is it on this is it on this link, which is 1 hop, 2 hops away? Or is it over the top link, which is 1, 2, 3 hops away? Which is the faster way to get there? Which is faster? Tell me in the chat box. The top link. The top link. The bottom link has nothing to do. The bottom link is the worst path because over here we can do 100 gigs all the way there. On the bottom link, we've got 100 gig bottlenecked by 1 gig. So we don't want to use this, but if we're using a distance vector routing protocol, we're going to use the bottom link, which is terrible. Now, if we swap this out with OSPF, we've got OSPF over here. OSPF is going to calculate the cost, and it's going to say this is harder to get to than this, and it's not going to be looking at these things. So that's what we're talking about. We're talking about choosing the optimal path, and we don't get that from distance vector protocols. We get them only from link state protocols because link state protocols are keeping track of what's going on. They're looking at the connections, etc. So that's why we really don't use distance vector protocols for the most part anymore. So now let's think about how big OSPF can actually get. I really want you to think about why we segment and why it matters so much, and think about how critical this is. Because if we go back to this environment, let's go back to a place where we draw another slide in. If you have 100 of these, and 100 is nothing. I work on networks with 10, 20, 30,000 routers, and that's still nothing. I've worked on a lot bigger than that. So let's say you've got all these things in your network. Yeah, that didn't work. I should say we got a network with all these routers in it, and it's an ugly looking box. Who cares? Every time any link on this entire network dies or moves, with every recalculation whatsoever, there's a new LSA. So literally speaking, if this port was connected to a PC and it was only one PC and you rebooted it, realistically speaking, everybody else is going to need to know that this link went down. That's why we're segmenting these, because these links get so much so fast with every one of these things constantly running a calculation. You got to remember, routers aren't using in general 128 core servers with 6 terabytes of DRAM. Routers have relatively small CPUs for the most part, because they're only designed to route packets. They're running a routing protocol. They're not running graphical user interfaces. They're minimal devices that have ASICs and devices that are designed to forward packets fast. So this is our area 0. Everything that occurs here, we need to know about everything. Everything. So by segmenting it to here, if this is the area 1, the only thing that we need to send over here are the summary routes. Why? Because there's only one way to get to area 1 through this cable. Likewise, while we're at it, if we had a branch office, the branch office might need to know about everybody's routes locally. But does the branch office need to know about the routes in area 1? Maybe. Let's see. Does the branch office need to know about all these routes in the center? Maybe. What if the branch office only has a single link to the data center? Just a single link. Now, if this branch office, let's say the branch office is a Starbucks, and it has one link back, does Starbucks need to know about every one of these links in here? No. Does Starbucks need to know about the information over here? No. Could the Starbucks have its own local subnets and just a default route pointing to this thing? Yes, it could. So does anybody have a networking background? Know what type of area this is called if it only is allowed to have type 1 LSAs and type 2 LSAs and nothing else? If you know what that thing is called, only type 1 and type 2 LSAs, type it in the chat box. And this is going to be some tuning that we would do in an OSPF. We only need to know about our local stuff at the Starbucks and how to get to the cloud. So what is this called? What is this called? What is this called? This is called a totally stubby area. So network brow, good try. We'll give you some OSPF knowledge, but good. This is a totally stubby area, not a stub area. Why? A stub area has type 1, type 2, and type 3 LSAs. But here, all we know is about our router LSAs and our link LSAs, and that's called a totally stubby area. A totally stubby area. So it's totally stubby. Now over here, we've got an area, and in this particular area, we want to redistribute some external subnets. But we don't want, by any stretch of the imagination, we don't want any type 3 LSAs or type in this area. But for some crazy reason, we want to redistribute some RIP routes into this OSPF area. Does anybody know what kind of area this is and what type of LSA we're going to be using for this external one? I'll bring on the Jeopardy music. Do 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 pop Boom, 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 bump, ba-dum, bump, 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 bump. Okay, anybody that knows networking, what kind of area is this that only allows me to take in an external route and an external area? But wait, anytime we use any kind of stub area, we're not allowed type 5 LSAs. Oh my God, how do we get external LSAs in an area that's not allowed it? Does anybody know what this is called? Okay, this is called a not so stubby area. And when you hear NSSA, this is called a not so stubby area. So the rule of a stub area is you're allowed to have type 1, type 2, and 3 LSAs. The rule of a totally stubby area is you're only allowed type 1 and type 2 LSAs. The rule of a not so stubby area is you can have type 1 and 2 LSAs, and you can have external LSAs that you redistribute. But we got a problem here. The OSPF specification says you can't have a type 5 or external LSA in anything that resembles a stub. So we've created some new wacky LSA called the type 7 LSA. What is a type 7 LSA? Identical in every way to a type 5 LSA, but it's one that enables us to break the rules, meaning in an area that's a stub area where we want to redistribute a stub route, we call it a not so stubby area. I didn't make it up. It's been going on for about 30 years. Anybody with a CCNP, CCNIE, or anybody that's doing any kind of routing or is going to be working with stub areas, not so stubby areas, and totally stubby areas. Why? See, let's say this router has got 800 OSPF routers. This might have a database of 50,000 or 100,000 LSAs, which would mean that the Starbucks router can't handle it. Now, a $100,000 router could, but a $10,000 router we're going to stick at Starbucks cannot. So by creating a totally stubby environment for our branch offices, we can enable optimal communication between subnets in their office. And if they only have one egress point, we can just give them a single route. Now, with the not so stubby, it's the same situation. Maybe we want to send everything through the backbone, except we have one route that we learned from some Linux subnets. And that's why they're not so stubby. No big deal. Now let's create a regular stub area. We've got over here. Now in this area, let's call it the campus. And we've got a couple of links. So we want all of the type 1 and type 2 LSAs, but maybe we only needed a summary to get to other branches. And that's why we would make this a stub area. And by doing this, we can minimize the data that's there. So decoupling. Now, wait a second. Mike drew a cloud. When he drew the cloud, he was trying to do this. He wanted to come up with one subnet over here, 10.0.0.0/16, and then he had a cloud, which is AWS, and he wanted this to be 10.1. And then Mike said, for Azure, let's make it 10.2. And heck, while we're at it, because if we want high availability, we're going to use multiple clouds. Let's add Google while we're at it. I love the Google Cloud. It's a fun cloud. GCP. Because that's mostly what we network engineers are doing. We're either building the clouds or making the clouds work or connecting the clouds. So now we've got links to everybody, links to the primary, links to the backup cloud, links to the secondary backup cloud. Now in this particular environment, if we only send one route to AWS, did we overwhelm AWS with the routing capability? Not one bit, no big deal, not at all. Did we overwhelm Azure with by sending them thousands of routes, or did we just send them a single one? No big deal, we sent them a single one. We also sent a single route to Google. Is this any different than this? No. This point of this is the same thing. Now, if we were designing our architecture, and this is how we designed them, in the core of our systems, we've got a bunch of really high performance routers. And this is what it's going to look like, your traditional network. We've got this. I want this to hit home. because otherwise it's just, a bunch of type LSA nonsense. But if we've got a link like this and we've got link aggregation groups between these things, links here, links here, links here, links here, links here. Oh, wait, this looks like a nice area 0. That looks like an area 0. And this distribution layer, so you could call this core. Actually, let's do this. So with OSPF, they would call this core. And then they would, in OS, this is core / area 0. Now, the next thing we typically do is something called the distribution layer. But as a distribution layer, it's a way to decouple your things from the core. Now, this distribution layer, realistically speaking, is going to be its own area. And generally speaking, we have these little access switches. And these little access switches, typically speaking, plug into these distribution layer switches. So these feed into these. That's just while we're at, just do the same thing. This feeds into this. This goes from here to here. Now this distribution layer feeds, goes from, say, here to here, and say here to here. So what you can see is we've been decoupling our systems forever. And if this is area 0 and this is area 1, fine, it all works. Or if it's route aggregation to make sure that we don't send too many routes to our cloud providers, same thing. If it's OSPF and we're decoupling by creating areas, it's the same thing. So realistically speaking, it's all the same. Whether it's OSPF, core access distribution, or adding a 3-tier web application where you're separating your web servers, your app servers, and your database servers. The whole concept is to decouple your architectures. Why do we decouple them? Because go back to here. If this one switch dies or makes a lot of traffic, and it goes away and it's got links flapping, we can constrain it over here so the core doesn't see it. So, most companies, they've got the CEO, you can't find their phone number, ever, no matter how hard you want. They've got a secretary in front of them. You try and call the CEO, they don't let you through. It's called the gatekeeper. It's the same thing. They're trying to make their people scale by going out further and further and further apart. That's what we're doing. We're dealing with modularity. We're dealing with scalability. So let's go through these areas one more. And this is, again, way, way, way above the CCNA level. This is going into the CCNP level and to some degree the CCIE level. Why do we like OSPF? Let's go back to it for the following reason. We like them that they can figure out the shortest path first calculation by calculating the bandwidth of the links. We like that they're accurate by building a whole map of the network, and we like that we can scale them with regards to areas. By doing that, we can create some scalability. So type 1 LSAs, router LSAs. Type 2 LSAs, network LSAs. Type 3 LSAs, LSAs that describe intra-area routes. Type 4 LSAs, how do you reach the router that's closest to the router that's bringing in external routes? Type 5 LSAs, external routes. Type 7 LSAs, the same as a Type 5 LSA, but in a not-so-stubby area because you're not allowed to have a Type 5 LSA. So what happens in a not-so-stubby area, like the one that we drew over here? Over here, we've got some things. We've redistributed the BGP route. It's a Type 7 LSA, but it gets converted to a Type 5 LSA when it gets sent in. And then OSPF area 0 gets to see a Type 5. That's how it works. That's how it works. So all this, core access distribution, OSPF areas, 3-tier web architectures, queuing systems. Same point, same principle. Separate your layers so that what happens in one part of your systems doesn't happen in another part of your systems. Let's open this up. It looked like there were some people, especially I went pretty deep into OSPF. fast. Didn't mean to do that. Hold on a second. So, Chris, are there any questions? Because I would assume there might be. And if everybody's got a question, I'd love people to ask them now before we move on to more complicated areas. Anybody have any questions?
Are you looking at StreamYard?
Oh, so that's the problem. I've got a lot of windows open. Is core access distribution a 3-tier architecture? Absolutely. And margin, that's been recommended by Cisco for about 2.5 decades. And I got to tell you, it's the most effective network architecture I've ever seen. I know lots of times people are now doing what's called collapsed core. And what they're doing is basically running monster core routers and then plugging their servers into the one switch away. I don't like it. I'm telling you, I've ripped out a lot of those systems because they don't stop problems when they occur. They're good systems, but you know, I want something to really let my systems totally fall apart and still work. OSPF is designed 100% for routing. Now, OSPF, because it's a link state routing protocol, does have some additional LSAs that can be used for like congestion analysis with regards to MPLS traffic engineering. But OSPF is completely designed 100% just for routing. BGP is only for routing. OSPF is only for routing. Just routing. Good question there, Eric. Angela, yeah, these names, I don't know where they came from. Even Dyke, yeah, totally stubby, not so stubby. Yeah, that's kind of a cute topic. Kind of stubby, but not really. Exactly, network bra. It's like you write a specification, and then you got to write a rule to break the specialization. Yeah, area on a stick, Angela. That was funny. I remember doing that router on a stick back in 1997. I remember thinking it was bad then, and let's face it, I like it even less now. Chris, are there any others here?
Not yet.
All right. Well, how many of you guys want to build out a nice, fun OSPF lab where we build it out, we put multiple areas in it, we build a core access distribution? Does that sound fun for everybody? All right, let's do it. So let's bring this a little bit. Let's do. Okay, so let's build a new lab. We're gonna make it fun. We're gonna have to be real. We're gonna have to get kind of fast with this though. So we're gonna say we add 8 nodes. For this, we're not going to hopefully not need all 8 nodes, but let's do it. So I want you guys to help me configure these things. Let's pretend I don't know how. Oops, bear with me. Okay, so let's have a little bit of fun over here. Wrong one. Let's open this up. Let's give ourselves a couple of routers. Let's say we add 6 of them. Okay, let's pop one over here, one over here, and then let's say we pop one over here, and we're going to make these all connected. Okay, so 1, excellent. 2, excellent. 3, because this way you get to walk through a full, you're going to get to see the full database. This is your traditional area. Okay, so let's go to router 1. Let's give it a base configuration. Hold on. Let's start all these routers up so they'll be ready when we need them. Go to this router. We're going to be a little fast when we configure some of these interfaces because we don't have a lot of time. Bear with us a minute. All right, slowpoke routers, wake up for us, wake up. This should be a really good fun lab for everybody. Because what we're going to do is we're going to install OSPF Area 0. Then we're going to add some external stuff. Okay, so I'm going to make this pretty easy. All right, let's get through this thing. And when it's ready, oops, we'll get started. Okay. Router's up. So let's configure this fast. Let's give it a host name and give it a password. So we'll use the host name command. Oh, won't even let me do that. Host name R1 int LOO IP ADDR 1.1.1.1. Configure this one over here, G0/0/0. Let's say we do IP address 172.16.0.1 255.255.255.252. No shutdown. Router OSPF1. Let's enter the loopback information. How do we do it? We loop the loopback was 1.1.1.1, so we're going to do an exact match. Let's pop it in area 0. And let's also add the WAN link, that 172.16. Dot 0.0. Remind you, I've got an extra period in there, so it's going to break things. And then we probably should configure the console ports. Didn't mean to type that. I was going to go. Now it's going to go try and telnet. It's going to resolve the DNS name for telnet, but we'll get there in a minute. You can see it's trying to resolve that. Okay, so let's do this. Config T line V GY 04. Okay, so this is router 1. Now, we probably should put on router 1 a link to this subnet as well. So what link is this? Interface G0/0, 0/1, IP address 170. Well, if the last one was 172.16.0.1 and 2, what's this one going to be? Make sure we didn't make any mistakes. We've got 2/30s here. Excellent, excellent, excellent. So fantastic. Now, can we grab this? Let's go over to here. Now on router 2. No, we don't want this initial configuration dialog. Configure this. Let's change the host name so we can find it. Host name R2. Let's make sure we can telnet SSH into them. So put an IP address in the loopback. Two dot 255. Let's make it a host. Okay, so now we're at router 2. So we're at router 2. What's the IP address on this link of G00 on the other side? If you don't know, you can see it over here. It's .1. So what's the IP address? The IP address is 172. Okay, we're going to be on this side, 172.16.0.2, right? What are we going to need on this link? We're going to need another link on this side. Now, on this link, we've never been on the subnet. So which subnets have we used so far? We've used the 0 subnet and the 4 subnet. So where does the next one begin? .8. So let's do this. Interface. And what interface is this going to be over here? G0/1. We can do 172.1 IP address, 172.16.0.8, right? Or .8 would be the subnet. So what's the next address? .9, 255.255.255.252. Let's go to OSPF here, router OSPF 1. Would help if I could spell. Over here, we can pop in the loopback 2.2.2.2, 0.0.0.0, which means exact match, area 0. Stick in an exact 0. We could actually, well, we can do a network statement, and we can basically do 172.16.0.0, 0.0.0.0.3, which is the wildcard that gets that subnet, area 0. And then over here, what's the next one we're going to do? We're going to get the .8. Now we're going to look at our interfaces and see what's going on. Show IP int brief. Okay. Oh, wait. So this link is down and this link is up. So we probably should turn that link on. Config T interface G 0/1. Let's do a no shutdown on it. Save this. Now, is anything going on yet? Do we have any routes? If we do a show IP route, I didn't see any OSPF neighbor chains. Did you? None. Okay, so why? Let's go to this router over here. Let's see what we got. Show IP interface brief. Okay, 172.16.0.0 is one. Can we ping the 172.16.0.0.2? That's not good. Oh. Does anybody see the problem? We got a real problem here. So look at the interfaces on this one. Show IP int brief. Now this is an obvious misconfiguration problem. Note, I attempted to put this address on gigabit Ethernet 00, and instead I put it on the loopback. Config. That's why it didn't work. Config, because you got to be on the same subnet on both sides. Config T. Interface loopback 0. Interface LOO. IP address 2.2.2.2 255.255.255.252. Now let's go to interface int G0/0, and now let's put the address that we really wanted to put there in the first place. IP address 172.16.0.2 255.255.255.252. Let's turn that interface on. Let's see if anything happens now. Configured it. Line protocol. Oh, look at that. OSPF native are changed. Wait, are we going to have any routes now? Sure are. Can we reach that 1.1 subnet? Sure can. So now I guess we got to go do router 3, huh? And then we'll add some other areas together. So, no, we don't want to enter this ridiculous configuration dialog box. We'll give it a minute. And then we're going to add other areas, redistribute some stuff. We're going to have a party time with OSPF. And if you guys want, and we have extra time, I'll use the same overlay and we can do a BGP, an IBGP, and an EBGP demo if we run out of time, if we have time. So, and if not, I'll make it a boot camp if you guys like. So config T, let's change the host name on this to router 3, R3. Let's make sure we can telnet, line VTY, 0/4, no login, password Cisco, transport input all. Here's where you can say SSH, telnet, etc. I'm on my computer. It's simpler this way. Now what we're going to go to interface, loopback 0, IP address. We're going to do 3.3.3.3. We're going to do 255.255.255 because it's a /32. We'll do a no shutdown even though it already went up. Now router 3 is connected to router 1 on G0/0. So let's go to interface. Let's get out of this interface. So interface, so you can see it, G0/0. Now we're going to enable that interface, but there's no IP address, so nothing's going to work. Now that interface is going to connecting to the far end. Oh God, this is ugly. Is going to connect to the far end of here. So what we need to be is on the same subnet of router 1's G0/1. So if this is .5 and the subnet begins at .4 and ends at .7, 172.160.0.4, that's what the router sees. Then we can do 172.16.0.5. We can do 172.16.0.6, and then 172.16.0.7 is the broadcast. So we can't use that. So now let's go to this router 3, and let's have a party with it. So router 3, we're going to go to interface. Interface G0/0. And we're going to do an IP address. We're going to do 172.16.0. What? What's that far end of that G01 on the other side? .5, so it's got to be a .6, right? .6, 255.255.255.252. Okay, now we got to cover this link on router 3. This link goes from here to here. So what would those subnets be? Okay, so interface G0/1. Okay, now we're interface G0/1 while we're having some fun. Let's go over to here. Now that one's going to router 2, right? Let's be very, so router 2, it's G0/1 on router 2. So let's look at router 2 at our G0/1 to make sure we're in the right subnet. So it's going to be 9. So if it begins with an 8, we can use 9 and 10, and then 11 is the broadcast. So that's going to have to be .9. So interface 0/1, IP, address 172.16.0.10, 255.255.255.252. No shutdown. Now let's enable OSPF router. OSPF 1 network 3.3.3.3 0.0.0.0 area 0 network 172.2.16.0.0. Let's do which 0. Actually, let me go just check and make sure I know which subnets are on over here. But you got to be in configuration mode to do that. One 172.16.0.4 0.0.0.3 area 0. The .8 subnet. So if we did this right, every router should have everybody else's routes all in area 0. So let's see. Router 1 should be able to reach router 2 and router 3. Can we? We can see the loopback address of router 3. We can see the loopback address of router 2. Can we reach them? Show IP OSPF neighbor. Now look at that. We've got 2 neighbors there. We should have 2 neighbors on every one of these. Show IP OSPF neighbor. We've got 2 there, which is what we should have. And if we go over here, it's my recommendation. Show IP OSPF neighbor. Okay, you can see everybody's connecting to everybody. Now, when you can see this, note, I'm working pretty hard here to verify connectivity. Can I ping across the link? Do I have routes? Why? See, if I don't have this fundamentals down, everything else we're going to do is just going to break. So I like to start by verifying that everything works before I lay things. So if I was going to build a building, I'd hire a construction crew to lay the foundation. I'd hire somebody to test the foundation. Then they'd start building. Then I hired an inspector to check at each stage. That's the way I check my work, the same way. So now let's go back into this environment. Now, what do we really have here? We have 3 routers, and every one of these routers is in area 0. This is our backbone. Now let's take this and let's create a new area. Okay, so how are we going to do this? On this particular router, we'll pick a new subnet. Anybody? And you know what? I don't remember which subnets we've used so far. So I'm going to just pick something in a totally different range. So we're going to do interface. We're going to do G0/2. No. And then we're going to put an IP address on it. We'll do IP, ADDR, 192.168.1.1, 255.255.255.252. Do a no shutdown on this interface. We'll go back to OSPF. We'll go to router, OSPF 1. Now let's add this network, 192.168.1.0, 0.0.0.3. Now let's put it in another area, area 0. Now we'll go to router 4. Over here. Oops. We better config T. We never turned the interface on. Interface. Oh, yeah, we did. Okay, good. So let's just go to our router 4. We may have to configure router 4 from scratch, which is okay. We know how to do this. We've been doing it all week for 2 weeks. It's been fun. So let's come back and see what's going on. Okay. Yeah, that's the good news. Everything's still working. Okay, so now we're on this new router. Good news. Everything's still working. That's really weird. Okay, so now we're on this new router. We'll give it a name. Call it router 4. Easy. VTY 0 space 4. The loop back on it. Now we'll put an IP address in the Ethernet port. We're going to pop in area 0, and then over here we'll put the IP ADDR 192.168.1.2, which should be the other end of the link. Just wait and see what happens. If we did this right, we should see the line come up. We can see it. Line protocol comes up. If we did it right, if we got everything in OSPF, we should see a neighbor adjacency change. And we haven't seen it yet. So did we forget to put OSPF on an interface? Is one of the interfaces not turned on? Got to check. So let's do a little debugging. Now we reached the 192.168.1.1 on route. Yeah, that's right. We ping the far end of this link, 192.168.1. Ping 192.168.1.2. We reach it? Now we can. Okay. Okay, that's up and running. Show IP OSPF neighbors. We only have 2. So what's going on here? Why aren't we running OSPF? Show IP int brief. The link is up. Now let's look at our running config. Did we configure OSPF correctly? Oops, let's go back and see what we did over here. So we've got 4.4.4.4, which should be correct. And we've got the wrong subnet in OSPF. That's why it's not working. So what are the links we chose over here? 192.168.1.1. Okay, what is the interface that we configured on this router? 1.2. Is that in the same subnet as this? 192.168.0.0. So this command that I put in here will get us from 192.168.0.0, 0.1, 0.2, and 0.3. So no, this doesn't work. So we put it in here wrong. So what do you do when you do something wrong? Router OSPF1 config T router OSPF1. Now, when we get to router OSPF1, we're going to type a no for this. Control A gets us to the beginning of the line. Now we're going to remove that. Now what we're going to do is we're going to fix this and pop in the right subnet. And the right subnet is going to have a 1 in front of this. Now let's fix this. Let's see what happens. We should be getting a neighbor adjacency. Received a mismatch. Really, that's not good. Mismatch area. We got a problem. Something's not liking it. But, at least we can see what's going on. We received a mismatch ID. Why? Do we have a wrong loopback address? Do we have the wrong address? We've got something that's wrong here. So we have to debug. That's what we figured out, because this is obviously not going to give you what you're looking for. Anybody see the problem here? What area was this supposed to be in? Area 1. What area did we put it on here? Area 1. In fact, this is how good these routers are. Received invalid packet, mismatched area ID. Received invalid packet, mismatched area ID. So they literally tell you. Let's fix that. See how easy it is. Config T. And this is why you debug router OSPF1. But you got to be able to type router right. Put a no in front of this. Now, by comparison, let's go back. Let's get rid of the no. Get the area right, because remember, this is an area border router, or a router that goes to another area. Now let's swap that. Whoa, look at that. OSPF adjacency change, loading to full. So how many neighbors is this router going to have? Router 2, it should have 3. Show IP OSPF neighbor. Look at that. Now here's where it's going to get interesting. Let's get out of here. Let's keep this up and let's close this. If we go to router 1 over here, look at the routing table. Show IP route. Look at that. Why is this link intra-area? And why is this link intra-area? If router 1 is in area 0, and router 4's loopback is in area 1 and link is area 1, that's why it says intra-area. That's why it says intra-area. I hope that kind of makes sense to you. Let me just check something real quick. That's why we like it. So maybe we'll give you one more. Let's add one more router to this. Have some fun over here. Let's really get deep into this. So now let's add another link. While it's doing its thing, bear with me for a minute. Now we have this link. Now let's give this a new link. No, we don't want to do this. Let's see if I can remember how to do this. Okay, so now, look, when we looked at router 4, I just want you to see if we look at the routing table of router 4, show IP route. Note it's got a lot of routes, and every route that wasn't in its area is going to be intra-area. But you can see the routing table. So let's go have a little bit of fun on router 6. Enable. We'll configure this guy. We'll call it a host name. We'll call it R6. Let's do enable password. Cisco, because it's easy to remember. Interface loopback 0. IP ADR 20.20.20.20. Okay, what subnets exist in the routing table? We've used the 172.16.0, .4, and .8. But what haven't we used? We haven't used the .12. So we're on router 6, so it's going to be G0/0. We can say int G0/0 IP ADR 172.72.16.0. So the next subnet begins at 12. So we've got .13 and .14. So let's make this .14. Okay, so so anybody that wants to know why we skip the initial configuration, the initial configuration is a series of questions like a wizard. Do this, do this, do this. Unfortunately, there's basically nothing that happens automatically, whether it's an AWS service or a Cisco service that actually works. So when you train network engineers, you tell them never to use the automatic. By the way, if you're working on the cloud, don't use any of their automatic anything either, because it's going to break stuff for you. So that's why we manually configure all network devices.
So the configuration that people are asking about skipping is it's like automated template type thing.
It's an automated template that will always yield an incorrect configuration.
Gotcha. So
most likely.
So it's not that you're skipping configuration, so to speak. You're skipping the automated.
Exactly.
Okay.
Everything we're doing here is we're configuring it. We're just not using the automated. We're actually doing it manually. Let's go to router 1, and we're going to do some experimental things with this so we can play around with it. When we configure this thing, you have to remember I'm a network architect, and though my CCIE number is 7417, it's Cisco. When I left engineering and became an architect, once you become an architect, you don't touch routers anymore. In fact, all architects don't touch the technology, we design it. So, I've been designing this stuff for so long, it's actually really fun to play with. So let's go to let's do the show IP int brief. Big T. Let's go to interface G0/2, and it's got to be on the same subnet as the one on the opposite side. Does anybody remember the name that I wrote on router 6? I know I sure don't, so let me do a show IP interface brief. And it's going to be .14, which means this is .12, which gives us .13, .14, and .15 is the broadcast. So this means this is going to be So this is going to be .13. So 172.16 .0.13 255.255.255.252. Back to the beginning of the line, because we can see I typed 172 incorrectly. That's how easy it is to do. I called it area 3 on this one. Yeah, let's make sure it's area 3. Okay, so let's do this. Let's wait, see if we see a neighbor change, a link come up on both sides. Whoa, we got a new OSPF neighbor. So let's make sure it's on both sides. Show IP, OSPF neighbor. We got all 3. Let's make sure we've got a neighbor over here. Okay, so now if we do a show IP route on this guy, notice how everything is intra-area, because everything is learned via intra-area. Now let's go to router. I haven't done this in a while, so we're going to have to play with the configuration commands a little bit because it's been a long time. But let's go to G0. Let's go to router 1. What I did is I changed it to a totally stubby area. So it's going to form a new neighbor adjacency. I may have to put it on both sides. I forget. It's been a couple of years. I may have done something that's a little goofy. Show IP OSPF name. Done. So that didn't work out so well. Let's go to that. You may have to agree. If not, I will definitely show you this. Don't remember if to put it on one side or both sides. So on router 6 now, if we do a show IP route, now look what we see now that we're a totally stubby area. We see our route, and all we get is a default route. Now because of this router, let's look very carefully over here. Router 6 is a totally stubby area, which means if I do a show IP OSPF database, what kind of links do you think we're going to see here? We're going to see the router links, the network links, and just the default route that's coming in as a type 3. Now let's get rid of the stub area configuration. Let's see the difference. Show, run. Router, OSPF 1. Excuse me. We'll make it a regular area. Now we should be a regular area, so show running config, make sure we deleted it. We still have area 3 stub in there. And now we got to go over here, do a show run, see if we removed it from this side. Haven't. Okay, we got rid of the stubby area. So now what's this database? What's this database going to look like? Show IP OSPF database. Remember, you saw one router. You had a now look at this database. It's a lot fuller. Now, why is it? Because now that we're a stub area, and I sent it to send no summary LSAs, we didn't have these before. We just had the default route. But now we've got more. We've got all the information from all the areas. That's why we do this. Now, heck, while we're at it, let's take router 4. Let's play with it a little more. Let's add another loopback. Config T interface int LO 10. I don't even remember int because I don't even know LO 10. IP ADR 64.64.64.64. Let's go back to router 1 now. What are we going to see in the routing table? Ooh. All of a sudden, we got this type 5 external LSA. 64.64.64. Note it says type 5. Why is it type 5? Because this router redistributed or translated Bulgarian to Greek and popped it into router 4. So now when we look on this routing table, look, it's going to look a lot different. Show IP route. And it shows as an OE2. OE2. So I kind of hope this is making sense what we're doing. We're walking through this. And as we walk through this, I can make it a stub area and we lose different types of LSAs. And that's really what's going on is the LSAs determine the kind of things that we're doing. So what are the kind of stuff that you're really looking for? We showed you how to look at the database. We showed you how to look at neighbors, showed you how to look at the routing table. Now, what if we wanted to configure the router ID? We could basically tell it, if we did nothing, it's going to pick the loopback address. But so let's just out of curiosity show IP OSPF database. We can see this is our router ID from the loopback address. Now, if we had multiple loopback addresses and we wanted to be careful, what we could do is we can go to config T, we could go to router OSPF 1, and we could potentially tell it which router ID to use. Do that. 1.1.1.1. Do you think the router ID is going to be now? The same 1.1.1.1 that it was before. Note that the database is going to look a little bit different where you're at. In area 0, every router will have an identical database of everything outside of the areas. So now let's think about, we could play with this. And now you know what a stub is, a not so stubby areas, a stub no summary is, etc., etc., etc. So let's talk about another thing. What if, for example, we wanted to add a switch? We're bringing a switch. I did bring in a switch, right? Well, I meant to add a switch. Guess I didn't. So implement, add an object, add a node. Let's bring in a switch. Let's make ourselves a nice happy switch. Now we're connecting a port to the switch. The only reason I'm doing it is I want the port to come up. Ugh. Now let's turn the switch on. Let the switch come up. Get on the console port. We'll watch it boot. They take a little while. Servers, Xeon workstations with a 0.5 terabyte of RAM. They're just, they run these big power on self checks. They're real slow to boot. It's not like a hobbyist computer that's optimized for video games that boots in like 3 seconds. Should be getting there, etc., etc. Switch is coming up, etc., etc. Life's good. Okay, enable. Config T. Let's give it a host name. Actually, let's just call it SW1. Now, let's pop an IP address on this port. It's going to be some ridiculous one. We're just going to make it up as we go along. Interface 0/1 E8R 192.168.10.1 255.255.255.0. We're going to make it a LAN segment. No shutdown. Router OSPF 1 network 192.168.10.00.0.0.255 area, let's say 3. Let's call this a passive interface. Auto sync, G. Which interface was this that we just configured? G0/1, G0/1. Like 0, 1. What we do is we would tell it the passive interface gigabit Ethernet. I don't remember which one it is. And what that will do is it'll tell an interface to participate in routing, but not form a neighbor adjacency. So let's go back to the switch a little bit more. The port should be shut down. So a show IP interface brief will show us the port shutdown. Gigabit Ethernet is up. Okay, so if that's really the case, when we get to router 6, we should have all of our interfaces up. And if we do, and we put everything in our routing, if we go over to here to router 4, we should be able to see all these routes, including the new route that we just popped in there. Oh, look at that. We can. It's an intra-area route. So let's do this. Let's see if anybody has any questions. Let me figure out how to shut this. Hold on one second. Okay, Chris, does anybody have any questions?
Let me take a look.
I can no longer see the YouTube window, so.
Well, can you see the StreamYard window?
I sure can, so I'm completely dependent on whatever yours. Because we covered a lot of stuff today.
Here we go.
Eric Stoltz, I will say this. I said in the beginning, I've said it every single day. There is no reason to buy any content other than the Cisco Press book that we gave you and this. I would not buy a Udemy course. I would not do any of it. I would read the Cisco Press books that we told you, which are the official Cisco manufactured books. And I used to teach these kind of things to Cisco engineers when I worked at Cisco. So you're getting official Cisco training. So follow the Cisco training thing. No boson needed. Get the Cisco Press book by Vernon Odom. There's a volume 1 and 2. It covers about the 2,000 pages of material that we're covering throughout these 2 weeks. And they're what you should use. Always, always, always go to the manufacturer. That's what we do. Every documentation, everything we do always comes from the source. Always, always, always. Great question, Eric. Please go over the area types again. Are you talking about area types or are you talking about LSAs? So I want to make sure that I completely understand what you're doing. So Anthony, could you let me know if you're talking about area types or LSAs? And while we're trying to figure that out, Chris, if you want to bring in the next one.
The next one is about the book. They're asking for the title of the book. And Evdokia just put the link directly to the book in the chat box.
Okay, great. It's the official Cisco Press Vernon Odom book, and Eva Ducky put a link to the book.
It is literally called Official Cert Guide.
Right, and it says Cisco Press on it. It's got Vernon Odom's book on it.
This is what it looks like.
There's a volume 1 and volume 2. It's part of a package. You can usually get the whole package for $30, $40. It includes practice test, practice lab. It's literally everything. Yep. That book is worth $500, and they charge $30 for it. It's for the two. It's fantastic. I've literally taught at least 10 people straight out of that book and nothing other than that book, and then they pass the exam right afterwards.
Yeah, so I wanted to make it clear because it can be kind of confusing when we say get the official cert guide. That's the name of it, official cert guide.
And I like Boson. They're a good company, but on a scale of 1 to 10, Boson's a 5. And the Cisco Press book is a 10 because Cisco made the book and Cisco made the exam. And Vernon Odom is a Cisco guy like me. His CCI number is like 1060, so he's old school Cisco. That's what we're referring to.
This is what it should come like if you get the official guide. It should come like that. Obviously, I have volume 1 somewhere else right now,
but that's the point. You've got our own employees. My CCI number is 7417. You better believe I've got a copy of that because I work off of official materials for everything I do. And Chris has got a copy, and I bet you Leo's got his own copy in Brazil as well. I don't know, half of my team all over the world has the Cisco books. Okay, so I can do that. Chris, how many more questions do we have? Because this is a CCIE level question, which I'm happy to answer. It's not part of the CCNA program. I just want to make sure we have time to answer everybody else's question.
Yep, the only other question right now is this one.
What lab goes with the official book? The official book has its own official labs that are attached inside the official book. Do everything with the official books, and you don't need anything else. We've given you the course, and we base our training off of the official materials. And follow that plus the official book, and you are good to go. So with regards to areas, we have a normal area which receives everything. Type 1 LSAs, type 2 LSAs, which are the local ones. Type 3, which are those intra-area LSAs. Type 5 LSAs, which are external LSAs. And type 4 LSAs tell us how to reach the router that has the external LSA. So that's normal. Now we can create something called the stub area. And what is a stub area? A stub area basically says, you have access to the type 1 and you have access to everything in your area, but you but you don't get all the things. So for example, in a stub area, and let's say a stub area is area 1, you'll know of all area 1's routers and network links, and you'll know about how to get to area 0. And once you get to area 0, all those routers are there. So if you've got a not so stubby area, that's basically that same thing, but it's enabling you to take external routing information from RIP, from BGP, from EIGRP, from intermediate systems to intermediate systems, and import that data that makes it an external route. So not so stubby, you're allowed to have it. Totally stubby means you only have network and router links and a default route. So stub means you've got a partial of your things. Not so stubby means you've basically got your own, and you can take an external links from an external routing protocol. When you redistribute that into OSPF on your router, it's considered a type 7 LSA, and that router translates it to a type 5 LSA, which is what's seen by the rest of the router. So that's called a not so stubby area. And a total stubby area is basically a stub with no summary routes, which basically means just a default route, and that's it. So it's whether you get stub and summary routes and no externals, whether you get, and that's a stub area, whether you get a totally stubby area, which basically has your own intra-area route and a default route to area 0. And we have a not so stubby area that enables us to, what's the word I'm looking for? Take external routes and redistribute them into OSPF. That's a not so stubby area. And that's a great question. And it's definitely a CCNP, CCIE question. But it's definitely a good question. I just wanted to make sure we had the chance to do that.
So, Mike, I wanted to follow up about this official book because a lot of people keep asking about resources. So I'm reading straight off the content here for everybody. This, when you buy the official one, not used. If you buy it used, there's like a 50-50 shot you get all this stuff. But if you buy this from Cisco, you get access to the companion website, which contains more than 600 unique practice exam questions, CCNA network simulator software, online practice exercises, and more than 2 hours of video training, in addition to the actual book. So along with that simulator comes with labs that they have prepared for your development. So that's the reason we recommend going to this official, et cetera, is because for $50, you get stuff prepared by the people that are making the exam. And
Exactly.
it's not just the book. It's the reason we recommend it is because it comes with all of that access through their website.
And it's not like somebody that just made it up in their basement, someone that's just trying to teach on their own. This is one of Cisco's best, one of their original CCIEs that's working for Cisco, writing for Cisco, for training you for Cisco. Now, I like Boson, but you compare that. It's like if you want a Ferrari part, do you get it from Ferrari, or do you go to Fred's Aunt Martha that knows how to make something in the backyard by using a drill and some sandpaper and things like that? It's nowhere in the same league. Yeah. Always go to the source when you can. We do. I'm from Cisco,
and we continuously point out that Mike's CCIE number is 7617.
7417.
7417. So Wendell Odom's CCIE number, and I'll let you explain where these began in just a second, Mike. Wendell's CCIE number is 1624.
I really want you to figure this out. So in Cisco terms, we're a little geeky. We started counting at two. The first CCIE was 1028. Why? Because we thought 2 to the 10th would be cool over at Cisco. So by the time I took mine in my number 7417, 3 million plus people had attempted Cisco certification, and I was the 6400 guy to pass. Now that was when the exam was 2 days, like when Wendell and I took it. The first day they made you build something that was impossible. The next day they basically sent 90% of the people home because they had failed. The people that survived, which was like 1 out of the 15, would get to configure their things before lunch, and then you'd go to lunch. And here's what would happen. When you come back for lunch, you were either sent home because you failed, or if you were there, you'd come back to a completely broken network. They'd recable your network, they'd change your subnets, they'd change your routing protocols, they'd mess up your redistributions, and they'd cause you all kinds of loops. And then they'd say, here, you got a couple hours to fix it. Yeah. That exam had like a 90-some% failing rate. You can see instantly when they took the CCI exam, from a 2-day exam to a 1-day exam, the pass rate went up by about 80%. And it became a much simpler exam. That's why the CCI today is still very appreciated, but it's not like it was for the guys that had CCI numbers less than 10,000. His number is 1100. What that means is there were no books for him to read.
Right.
He had to read all the RFCs, all the Cisco documentation like we all did, and there was no training. He had to know it in such depth to pass it. So when you get one of those guys that's teaching, listen, he is awesome.
Yep. And so not just Wendell, the technical reviewer for all of this content is 1837. And contributing authors are 4594 and so on and so on. So this is all created by people that didn't have this type of stuff to prepare, and so they created this for you to prepare.
Exactly. So the reason I make so much content out there is because when I wasn't available, there was none. And when I look at what's out there, none of it impresses me. So it's like, okay, I'm going to give you Cisco materials because I want you all to be successful.
Yep. So,
that's kind of the reasons we're kind of talking about this. Now, I think I'm going to end today. Chris, can we go 15 minutes more for me to talk about network types so we can talk about something new tomorrow?
If by 15 minutes you mean
15
minutes?
Yeah.
Yes.
Okay, so let's just talk about the concept of a network type with regards to OSPF. And realistically speaking, there's just two kinds of networks. There's a point-to-point network, which is basically a WAN link. And we've got this kind of broadcast multicast link access. So I know I've demonstrated this very heavily, but let's just go through this for about one more minute, a couple minutes. When we've got routers on our LAN link, this is what's called a broadcast multi-access thing. And that's why we've got that election of this designated router, or this is the designated router on the LAN, this is the backup designated router, and everything else that's not a designated router or a backup designated router is called a DR other when you do the show IP OSPF neighbor. And you can see that if we go to our labs. I just want to walk you through this. I just want everybody getting a great experience. So when we go over here, if we go to router 4, for example, enable Cisco show IP OSPF neighbors, you can see the neighbor is the backup designator route. But that's all I really wanted you to see, is that you could see that was going on with that. So going back to the interface, the interface knows. It automatically knows if it's broadcast or non-broadcast. And let's see how I can show you this. Well, maybe not. I'm just going to show you in a slide because I don't even know where this window disappeared to. Oops. Nope, not this window. Bear with me, guys. Okay, so note when we look, when we go over here, if we're looking at the show IP OSPF interface, you see where it says the interface is up and the IP address. It will tell you the network type over here. So you can see that directly in the OSPF command. I'm just trying to see if there's anything else that we missed that I really wanted to cover. Yeah, I wanted to show you this. So if it's a point-to-point interface that you had, like a serial link or a different type, if we were to set it as point-to-point, like over here, we're going to tell OSPF not to have the election to make it look like a WAN link. It's going to say network type point-to-point, but we're not going to do that on a WAN link, on an Ethernet link ever. Realistically speaking, it's going to be very rare. There's going to be specific use cases to do it, but point-to-point links, like a cable, like a serial link, they show up as point-to-point. Ethernet, why is Ethernet? Well, Ethernet goes into the switch, right? What does the switch do? Broadcast all ports except for the one it came in on, at least for unknown frames. And so that's why it's a broadcast multi-access for Ethernet ports. Same kind of concept. And we can see, we can go walk through our show IP OSPF neighbors. We'll see that they were full, I showed you. And if we look at the interfaces that are running OSPF, we can see the type of interface and the number of neighbors. How many neighbors can you have on a point-to-point link? One. Let's so talk about things that have to happen for it to work. Your interface on both sides need to be on the same subnet. We can't have any ACLs blocking out OSPF hellos, for example. The hello and dead timers must match. Can't have one router claiming to be 1.1.1.1 and another router claiming to be 1.1. What's that mean? The router IDs have to be unique. Two routers with their links have to be in the same area. Note, we got the area wrong and poof, it didn't work. And those are kind of your main things that you need to remember between OSPF neighbors. Here's a good one. If you're ever trying to troubleshoot something and it's not working, and you do a show IP OSPF interface on both routers, let's look very carefully at what's going on here. On router 1, show IP OSPF interface. Timer interviews configured. hello 10, dead 40. What's that mean? Every 10 seconds, Ivadoikia, hello. And every 10 seconds, she says, hi, Mike. Every 10 seconds, Cindy sends Ivadoikia a per message or a hello message. And every 10 seconds, Ivadoikia replies. If Cindy sends 4 hellos and Ivadoikia doesn't respond for 4, the link is marked as dead. And then Cindy and Ivadoikia aren't talking anymore, which is really sad. They assume the link is dead. And then Cindy reaches out to her good buddy Ivadoikia over there in Hungary, and she finds a backup path because this path went down. She finds a new path, and that way she gets to talk to her friend. And Cindy places lots of international phone calls and does all kinds of cute things. You have absolutely no idea the kind of ruckus my cat Cindy could do. And realistically speaking, if we ever wanted to shut down OSPF for any reason, there's the ability under OSPF to enter the shutdown command to shut it down. So, and once we shut it down, what's it going to look like? Show IP OSPF neighbor. Wait, we got to, well, you know, shutting. This will happen if it's for some other reason. So let's get that out of there. But that's really what I wanted to walk you through today. I really wanted to walk you through OSPF, areas, how they work. So what did we do today? We talked a little about the ping command and how to use it to see if the network's good. We talked about traceroute and tracing your way through the network. We talked about OSPF. We talked about link state routing protocols and the way they work. We dealt with the type 1 LSAs, which are router LSAs. We talked about type 2 LSAs, which are network LSAs. Again, this is way above the Cisco Certified Network Associate, more of the CCNP thing, but that's okay. We talked about stub areas, totally stubby areas, not so stubby areas, mostly CCIE level stuff, but that's okay. We talked about the hello messages, the dead timers, and how OSPF calculates a path, etc., etc. So we pretty much covered most of OSPF today. So I guess I'm going to end it with this. Do you have any more questions? If you do, let's answer them. And if not, I'm going to ask you to type 1 or 2 last commands, and we'll get ready for party time tomorrow, which is going to be really, really fun. Are there any other questions for me there, Chris?
So we have people asking if they can see Cindy.
Yes.
And then, hold on. We got some actual questions first, but I was giving you the heads up there.
Okay. Ferdy, I think it's depending upon the person. I thought the CCNA was exceptionally easy. I passed it in 4 days. I have seen other people that knew literally zero about networking pass it. So I don't think it's very hard. The key is, do you know subnetting? Do you know basic switching? Do you know what an IP address is? Do you know what subnetting is? Do you know the OSI model and the internet protocol model? And if you do, it's a relatively simple exam. Now, I will tell you this, Ferdy, the Cisco exams are what I call straightforward exams. And what I mean by that is you could take an Amazon exam, and the hardest part of an Amazon exam is reading through the question, because they stick the word elastic in 50 different places, and you read through these exams and you're like, what are they even asking? And once you read the question the 3rd time and figure out what they're asking, it's a simple answer. Not so with Cisco. Cisco gives you very strict, clear questions. And it is very obvious if you know the material, the answer. So Cisco materials are very clean. Cisco writes in a certain way to make the questions very understandable. So I found the CCNA exam to be extremely easy. I will tell you, Ferdy, I've coached now, I can't tell you how many people. I've never had anybody fail a CCNA exam. Now, quite frankly, the only CCNP exam I've ever seen anybody fail was the troubleshooting exam. That was one of the people that I trained. And this was a person that basically took the troubleshooting exam like this back when they used to have the CCNP exam. He said, Mike, here's the thing. I have more money than time. And I said, yeah, so. And he says, I'm not ready, but I'm going to go take this troubleshooting exam and see if I can pass it. And I said, but you said you're not ready. And they said, yeah, but I could study, or I could just pay the couple $100 and pass the exam. And if not, I'll just pay a couple $100 and take it again. And I said, that's not the way I recommend studying. And he says, Mike, you recommend that I learn the job, not the certification. I said, you're right. And he said, so I'm going to get through this certification the laziest, fastest way I can. And I said, okay. I will tell you, this person went on to become such a good network engineer that they made it to the top of, what do you call it, of one of the world's best networking companies. And he rose like a rocket ship. The key is he focused on all the things. But I don't think it's going to be hard for you, Ferdy. I think it's going to be a very simple exam. I think if you don't know networking, it's a very challenging exam. I don't really let anybody tell me things are hard, Ferdy. No, I have a different perspective. I was told I would never walk again, and I literally spent 6 hours a day in a physical therapy center every single day for almost 8 years straight. And I still spend 3 hours a day in a physical therapy center just to be able to walk down the stairs of my house every single day. So to me, that's what hard is. I don't think you'll have a hard time with this, Freddie. I think it'll be easy for you. I think you've gotten some solid training this week. I think you'll be good. Sadie, still confused what is broadcast versus multicast? Okay, great question. Every one of you, listen to me. You have to listen to me no matter what. I am broadcast. That's what a broadcast is. By comparison, now, Sadie, 50 of you are going to subscribe to pictures of my cat Cindy. And only of the 50 of you that subscribe to my cat Cindy can see it. I send the cat Cindy. Eva Doikia sees it. Abigail sees it. Chris sees it. Mesh sees it. But only the people that subscribed. That's a multicast. You want it, you got it. You want it, you got it. You want it, you got it. A broadcast is, everybody listen to me right now. That's a broadcast. The multicast is, all of you that want it, you got it. Your food's delivered. Like that. Great question, Sadie. Great question. Hope I made that in not too obnoxious manner, but I don't want you ever forgetting it. What are we covering tomorrow? I'm not sure what we're covering tomorrow yet. My team is going to be sending me the slides tonight and the topics from the official team, and we're going to have a party with it. I can tell you that. I'm going to bring Cindy in about 2 minutes. Eva Doikia per messages, love them. I'm going to bring her. She's this. Are we ready to see Cindy?
Yes, we are.
Let's make sure she's in, because she did go out this morning and she was terrorizing some people. So let me go see if she's in her bedroom. And if she is, I'm going to bring her. I did hear her. Could you come with me, Princess, for a minute? So we can all see Cindy. So everybody can see my beautiful, beautiful helper in the office. This is my Cindy. She's very sweet. She doesn't like to be held, but she does like to sit on us. Okay, you can do whatever you want, Cindy. Not right now? Okay, well, that's my baby Cindy. She comes when she wants. She goes when she doesn't want to be held, but she's a lovable, sweet, wonderful little child. Now, we all know why I always have fur on me all the time. But I wouldn't trade my Cindy for anything.
And why you're always sneezing.
And why I'm always sneezing 24 hours a day. But I wouldn't trade my Cindy for anything. And the really funny thing is, I was always a parrot person. I had parrots. I love birds. My wife likes cats. I go to the cat rescue. The little kitten puts its paw up to the glass. I put my paw up to the glass. I'm not very mechanical, so the cage was locked. So it was like a glass window thing. It took me like 5 minutes to figure out how to open the door when it was just a lever. I go in there. The cat rubs against my feet. I have a foot problem. I literally sit down on the chair. The kitten jumps up in my lap, purrs, and falls asleep. An hour and a half later, she's still in my lap. And guess what? That little mini lioness, Angelo, thank you so much. She wasn't going anywhere. Thank you so much, MJ. Yeah, she doesn't love to be held, but she loves to come over on her own terms. I'm a dog person, but I love cats too. I love all animals with fur or feathers. I never was a cat person, but this one, oh my God, she's just my little baby girl. Thank you so much, Sharon. Eva Doikia, I know she's always looking for you. She actually asked for you by name. So if you're all here and you had good time, type hashtag CCNA. That way I know we all had a great time. And of course, Tomorrow, we will get involved in some fun networking. I'm excited to find out what we'll even be talking about. We do follow the Cisco curriculum, so if you've got the official curriculum, you're going to know where we're headed next. Your brother gave you the CCENT, CCNA. I'd probably change by the new one. So here's the thing. There used to be a CCNA divided into two pieces. You could do a CCNP. This is a single exam, so it's a little different. They're going to be 90% the same, but for the cost of the book, which is less than $50, I think you're better off just getting the newest version. Yeah, Alex, we're going to leave the IPv6 off of this curriculum. There's a tiny section in there, but we're going to focus more on the heavier duty stuff that's more related to getting cloud hired or network architect hired, which for the most part is IPv4 stuff. That's where my strength lies. Yeah, 1624. It's pretty incredible. Sharon, I'm honored and privileged to try and go out there and help you. Mufaz, it's always good seeing you. Okay. Well, everyone have a wonderful, wonderful, wonderful night. We'll get back to it tomorrow. We'll continue through the week. By the end of this week, you guys should all have some serious network knowledge. And go out yourselves and get yourselves network administrator jobs, network engineer jobs, cloud architect jobs, cloud engineer jobs, or whatever it is that's going to make you happy. That's the whole point. Get cloud hired, network hired. Actually, you know what? On ending, can you all type a hashtag cloud hired, and then we can end for the day. Have a wonderful day. It's an honor and a privilege to be with you. And look forward to seeing you tomorrow. Hashtag cloud hired, please. Take care, everyone. Welcome, everyone. This is Michael Gibbs. I'm the founder and CEO of Go Cloud Architects and Go Cloud Careers. And I'm super excited to be back here with you today to go over day 6 of our completely free Cisco Certified Network Associate Bootcamp. This is preparation for the CCNA 200-301 exam, and this is a free CCNA 200-301 bootcamp. The things that we're going to be covering in this course are obviously the CCNA, but we'll be talking about Cisco Networking Essentials, and this is Cisco Network Administrator training, this is Network Engineer training, and of course this is training in networking for cloud computing. And it's a critical cloud computing technical skill. And this is network skills training for the cloud architect, the solution architect, but then again, the network engineer or someone that has the future desire to be a network architect as well. So if you're a cloud architect, this is cloud architect training, and this is some critical cloud architect skills because the cloud is nothing more than a network and a data center that's been virtualized. So take this Cisco CCNA course and Cisco certification training and this free network training and help build yourself that network career, whether you're a network administrator, network engineer, network architect, cloud architect, solution architect. I just want you to have the best career. So please take this intro to networking course where we'll teach you everything from what is a computer network to networking and cloud computing, and go out there and build your best career. Before we begin, I want to let you know about some free things that we have to help you tomorrow. If you're in the cloud computing space and you're looking to get your first cloud architect job, please join us on our completely free How to Get Your First Cloud Architect Job webinar. The link is in the description below. Chris from my team will also post it in the chat box. I want to make sure you all have the absolute best experience and get hired for the job of your dreams. So please join us for the free How to Get Your First Cloud Architect Job webinar. In addition to that, please join us and receive a copy of our completely free AWS Certified Solution Architect Associate and Professional ebook. The link is in the description below. It takes you everywhere from beginner to passing the AWS Certified Solution Architect Professional exam, which is everything that's necessary to get you your first cloud architect job, at least from a technical perspective. Obviously, there's the business, there's the communication, executive presence, emotional intelligence. But at least from a technology perspective, at least we've covered the certification and given you enough to be close, one step closer to getting that free first cloud architect job. As we actually talk about what is the technology, not just how to configure it. So if you're ready to begin our free CCNA training session, please type hashtag CCNA in the chat box. Sarah Ahmed, good to see you. Ash, CCNA. Please, everybody type hashtag CCNA. Eric, good to see you. Martin, hello, everyone. Leo Parades, CCNA, fantastic. Leo Parades on Cloud Hard, yes. Nikhil, so good to see you. Hello. Tom Orthius, good evening from the Netherlands. Fantastic. Mr. Gee, CCNA. Angelo, thank you so much. Dan DTM, CCNA. Danica, GC, CCNA. Eva Doikia, so good to see you. I'm so happy to see you today, Eva Doikia. Cindy was asking about you, by the way. Sarah Ahmed, yay, CCNA. That's the way I feel about it. And Marge, and hi, Mike and Chris, hi, GSA family. And Neil, good to see you. Chakot, good to see you. Mr. Businessman, CCNA, fantastic to see you. And FM McKeel, CCNA, fantastic. Georgetta, CCNA. Alexandros, CCNA. Yasas, Kalispera, and Jazz. Thank you for being a Blue Wrench today. Thank you for everything you do. And, it's wonderful to see you. Good to see you.
This is day 6.
This is day 6. We still have day 7 and 8 coming, and I think coming. So we've got plenty more. Beta Point CCNA, fantastic. MJ CCNA, Sarah Ahmed, yes, it's good to see you, and thank you for my team. Marty CCNA, Cloud Hired, good morning and good to see you. And Twinkle CCNA. Brian McCool CCNA and Angelo CCNA, fantastic. Jim Weaver, it's always good to see you. And Jazz CCNA. Williams, good to meet you, CCNA. Martian CCNA and Twinkle, yes, CCNA for life. Carlito A, CCNA. Felix, who's amazing, CCNA. Mohammed, absolutely. AJ CCNA too. And Sharon CCNA. Anna Nils, you guys are waking me up from all over the realm. Good to see you, Earl Ovens and Eric Stoltz. So we are here for the CCNA training, and I'm super excited, Daniel, to see you, and Janine and Eugene. So happy to have you here. Thrilled for the coaching and prepping you. Fantastic. So let's start talking about some network. Oh, I'm in Mozambique. So fantastic. Okay, I'm really loving this. So fantastic. So let's have some fun. Let's start talking about some more naming, some more networking things. So now we're going to get into more TCP/IP stuff, which is kind of my favorite things in the world. We're going to start talking about some protocols such as TCP and UDP. We'll talk about flow control, etc. So when it comes down to it, we have multiple ways that we can send our traffic. We can send them via TCP to control our connection, and we control it via UDP. And depending upon the application, whether we use this transmission control protocol or this user DAM data protocol, it's depending upon the application. So let's talk about it. There's a major difference between the way TCP does things and the way UDP does things. TCP is used for reliable communications. TCP is used for reliable communications. What does that mean? If I need to send Chris a message and I need to know that he got it, guaranteed, I'm going to use TCP. And guess what? If I have something where it's less critical, I might use UDP. But if it matters, I have to use transmission control protocol. So what makes transmission control protocol reliable? Here's what happens. Jazz is over there. I want to send a message to Jazz. I send the message to Jazz, and Jazz says, Mike, I got it. Send me your next message. And I send it to him, and Jazz says, I got it. I send a message to Jazz, and Jazz says, got it, Mike. I send another message to Jazz, and he says, I got it. Now I send a message to Jazz, and he doesn't get it. I send the next message to Jazz, and he doesn't get it. And then I send another message, and I know he didn't get it. Now, he didn't reply to me. I know he didn't get it, so I'm going to retransmit it until he gets it. So TCP is used for reliable. It's like a conversation. Do you understand me? Yes. Do you understand me? Yes. If I was talking to people in Greek, I'd say something. We'd say "Katalavas dipa," which means, do you understand? If I was communicating reliably in Spanish, I might say "entiendes," because I want to know that the person understood me. TCP is just that. I send you a message and you acknowledge it. Now, we're going to talk about TCP in depth. We're going to talk about flow control and retransmissions. And we'll talk about UDP when it's appropriate. But I just wanted to let you know we're going to start with TCP, which is used for reliable services. Now, we're going to use UDP or user DAM protocol, datagram protocol, for something different. We're going to use it for real-time applications. And we'll talk about why we can't use reliable communication for real-time applications like voice and video, and why it must be UDP for voice and video. And see, Angelo responded. I already heard that he knows. He used reliable communication with me. So looking at this, if you understand why, then it'll be much easier to figure out the way we do things. So let's talk about the TCP transport layer. Realistically speaking, we've got the ability to do error recovery through sequence numbers and acknowledgements, and I'll show you what we mean by that. We have the ability with TCP to do flow control using windowing, and this stuff is really, really cool. We can make sure that we establish the connection, etc. And we can make sure that our packets arrive in order. So TCP gives us some really good information. Now, TCP, if you really want to understand it completely, you should go to the Internet Engineering Task Force specifications. Specifically, it'll be specified at the Request for Comments RFC 793. And this will talk about everything that you need to know about TCP. So TCP realistically uses, when it provides error recovery, you have to understand this error recovery that it provides takes up a lot of bandwidth and CPU cycles. And we'll show you why. So let's look back at a message header. At a TCP message header. Let me share this with you for a minute. In this environment, we've got a checksum, which shows that, which is basically a mathematical hash that shows that the file has been damaged. We've got this degree of service type of things, which can say if it's urgent or not urgent. We've got the source port, meaning like port 5000 or whatever, and the destination port, port 80 for www, 443 for HTTPS, 22, etc., etc. Port 69 for TFTP, etc. Port 53 UDP and TCP for DNS, etc. And those are those common ports that you just have to remember. But look in the header, you've got a sequence number and acknowledgement number. So, Chris, I'm sending you a message, 123. Chris, did you receive message 123?
Yes.
Okay. He said, I've received message 123 with acknowledgement number 1. Now, Chris, I'm going to send you packets 4, 5, and 6. After you receive packets 4, 5, and 6, you previously acknowledged it with the number 1. Now, the next time you're going to acknowledge it, can you acknowledge that with the number 2?
2.
Okay, Chris, I'm now sending you packets 6, 7, 8, and 9. I went up more. Chris, did you receive those packets?
3.
Okay, Chris got it. Now, I'm going to send more because we've got a good connection. I'm going to send 10, 11, 12, 13, 14, 15, and 16. Chris, did you get them? Okay. Chris, did you get them? Chris didn't get them. Okay, I'm going to resend message 10, 11, 12, 13, 14, and 15. Chris, did you get it this time?
Yes. 4.
Okay. Now I'm going to send him some more. That's how TCP does it. It has something called it's a sliding window. I send one message to Chris. He responds, I got it. I send 2 messages to Chris. He responds, I got it. I send 3 messages to Chris. He says, I got it. Now I send 4 messages to Chris. And guess what? He says, I got it. I send him 5 and he doesn't. Guess what? I start all over at sending 1 package. So what does this tell you? With TCP, it will only send as much data that's possible without getting lost. And if you have some loss on your network link, maybe your link is too busy. Maybe somebody plugged you into a hub and you had collisions. Maybe you're on wireless and 2 people tried to transmit at the same time. What can happen is you try and transmit, you start to transmit, and then you stop transmitting, and then you restart transmitting. So if you're losing any data on your link, you might have a 100 gig link, but you might only be able to get 1 or 2 gigs worth of traffic on it if you've got what's called packet loss. And that could be coming from a bad router microcode, a bad card, a bad wire, a bad fiber optic connection, etc., etc., etc. So when we're using transmission control protocol, that's how it does flow control. It's called the sliding window. You might see this in exam. Sliding window, TCP flow control. That's exactly how it works. Now, when you're dealing with these kinds of things, you're going to have to know protocols and port numbers. And the reality is we just need to know this. And why? Well, we're not going to necessarily be working with firewalls as a network engineer. That's the security engineer. But we're going to be making access control lists to be protecting one subnet from another. So you need to know that, like, for example, what are the common protocols and ports, whether they be TCP, UDP, or ICMP, pinging using ICMP. So, for example, TCP port 20 and 21 are used for FTP, file transfer protocol. If we want to secure a cell into the system, we're using TCP port 22. If we're going to telnet into a system, we're using TCP port 23. If we're going to use DNS, we're using TCP and UDP ports 53. TFTP uses port 69. Port 80 is traditional www web traffic. Port 110 is POP3 or Post Office Protocol, the old mail protocol used for mail. SNMP is port 161. SSL, which we use for HTTPS, is port 443. And we do a ton of syslog stuff. All those ugly messages that are coming on our screen constantly, that's syslog messages, and we typically send them to a syslog server on UDP port 514. So there's some common protocols. So realistically speaking, I'm going to walk through it again. The TCP connection establishes before anything occurs. Connection establishment really refers to the process of sending a sequence and an acknowledgement and beginning this like three-way handshake. So let's walk and show you what it looks like exactly. In this particular environment, we've got somebody that wants to go to the web browser. They send an open request to destination port 80 because it's a web server. Hey, open up a connection with a SYN or a synchronize. Now the web server responds and tries to open a connection back with the web browser. It says, open a connection with me. And it says, I'm going to open a connection with you. And I acknowledge that I got your measure. Now notice this message over here is exactly what this message is over here. Now the web browser, the computer acknowledges to the web server and says, guess what? We've got a connection. So I ask for a connection. They reply to my ask and say, yes, I'm willing to accept yours. And then I say, yes, I'm willing to accept yours. It's called the three-way handshake. And guess what? Now we're talking computer to server, computer to server. This is what my cat Cindy does when she's typing on my keyboard and she's going to the Science Diane page, when she's researching shrimp, when she's researching lobsters and researching scallops. My cat Cindy, when she sits at my computer and she types these things, that's how it goes up. That's how she initiates the session with Google to find out where she can get her next shrimp meal. So let's walk through that sliding window one more time that I talked you through. We send a message, we go back and forth, we send a message, we send 1, 2, 1, etc. So that's the flow control I was talking about. So again, TCP calls this flow control windowing, and it's a concept that's applied to data. Basically what happens, we send some, we come back, we acknowledge it. As we send more and more, we open the window and we send more data time. If we lose any data, we slow it down, just like the discussion I had with Chris. Now we talked about TCP being reliable. Now let's talk about UDP, which I said is used for non-reliable communication. So think about this. If I'm singing Jeopardy music, do 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 do, and we lose one of that, does it matter? No, who cares? Now imagine having a conversation with TCP. Chris, meet me at the restaurant at 5 p.m. Now imagine I sent some of that and some of the packets got lost and some were retransmitted. So what if I said, Chris, restaurant, meet me, 8 p.m., be here? Because the packets got out of order, that would be a problem. So when we're dealing with real-time voice, we send it via UDP using something called the real-time protocol. We use the same thing for video. Why are we using UDP? Because if I say the word yes, actually, let's say I said, my wife called me and I said, yes, dear. If dear came out before yes, because yes was lost and dear was retransmitted, dear yes might not be the same thing. So when we're dealing with video or voice, we're basically sending the data. And if you lose it, you lose it. We can't retransmit it ahead of time. Imagine transmitting a stock ticker and the stock ticker is sending out old prices that are no longer valid. That would be a problem. Imagine a sports person playing a game where they missed something, so they go back and went back in time and then retransmit it. It would be a nightmare. So user datagram protocol, or UDP, is used when you don't need error checking or flow control, or when error checking or flow control would be a problem. If we were to type A, B, C, D, E, F, G, and A, B, C were there, E, F, G were lost, and then we had H, I, J, K, and then E, F, G were retransmitted after H, I, J, K, the alphabet wouldn't be so solid. So that's one of the things we're trying to talk about, why we use UDP as opposed to TCP. So some applications can lose data, and they're perfect for UDP. Some applications like TFTP have a means to basically make it reliable, even though it's UDP. But it's in the application. So TCP makes network reliability there. UDP is used for real-time transfer protocols. And that's kind of one of those things that's pretty important for you guys to know. So we talked about TCP, we talked about UDP. Let's talk about ICMP, or Internet Control Message Protocol. If I send a ping, I'm sending an ICMP echo message, and the person responds back and says, I got your message, was what? An ICMP echo reply. When I do a trace route, that's ICMP. So what are our layer 4 protocols? TCP, reliable. UDP, real time. ICMP, network troubleshooting. There you go. Now you know it. That's how they work. So the next thing to do this is we're going to show you how to use this cool TCP and UDP stuff to make some access control lists for security. But before we do this, we talked about TCP and UDP and ICMP. And this is fun network engineering stuff, and it's a great part of the CCNA program. But I want to make sure you're there. I want to make sure you got it. I want to make sure you know. So Chris, if you want to walk through, let's make sure we don't have any questions before we get into access control list.
Yep, give me just 1 second.
Sure.
That's a good point right there.
Jazz, absolutely. TCP versus UDP. If you're in a cloud architect interview, it'll be there. If you're in a solution architect, it'll be there. If you're in a network engineer interview, it'll be there. If you're a network administrator interview, it'll be there. If you're in a support position, it'll be there. And yeah. Great point, Jazz. Critical information to know. Angelo, ping actually uses Internet Control Message Protocol, which is used for troubleshooting the network and mapping them out. Angelo, that's pretty much it. When you ask your kids to do chores and they don't respond, that is UDP. There is no acknowledgement whatsoever that they'll do it. And you know what? UDP makes me darn nervous, just like when I ask somebody to do something and they don't acknowledge it. So whether I say entiendes, que tal vez de IPA, or do you understand me, I'm definitely going to confirm and make sure that they understand. Jazz, excellent. TCP is sending mail with a signature required. UDP is just sending it and hoping it gets there. Well put, Jazz. Excellent. That's why you're a fantastic cloud architect. Angela, is it correct that UDP is used partly because the receiving hardware can't handle the volume of the request? No, not at all. If so, will the hardware meet the requirements? Angela, now I will tell you, back in 1975, the hardware was a little weak with all the volume of TCP requests, but after, say, 2000, even then, it wasn't even a problem. So, no, it wasn't really the issue of the acknowledgments. It's more the issue of, do I need things to be in real time, or do I need them to be retransmitted? There is a lot of overhead with TCP, which means, let's say you've got a connection that's 10 gigs. If we lose 2% of the data via TCP, we'll retransmit it. But that flow control and windowing of TCP could slow it down so much that we might not be able to utilize our link well. So it depends on the kind of data and how the criticality of the retransmitting that determines whether we should use TCP or UDP. But no, we haven't had these kind of hardware problems in decades, thankfully. Now, when I started, sure, we had all kinds of hardware problems. We had routers, and the first routers that I worked with had like a 15 or 25 megahertz CPU and about 8 megs of RAM. Now, those routers, they were limited, but now we're not dealing with anything that's a problem. Sadie, Can the acknowledgement from the receiver not reach the server? Yeah, sure. If the acknowledgement goes back to the server and doesn't make it, the server says, oh my God, my data has not been received. Retransmit. So it's the same thing. Did you get it? No? Okay, come back. Same thing. Great question there, Sadie. Chris, you can bring in the next one. When we need to use TCP, given that it's unreliable, anytime you want to do any audio things like a phone call, right now we're using real-time video with YouTube, so that has to be this way. Anytime you're doing cable TV, that's IP multicast, that's also UDP. So TCP is used when you need reliability. UDP is used the rest of the time. Half of the things don't need reliability. And I will tell you that most internet traffic is UDP at this point because it's video or it's voice. And all that uses UDP because you can't retransmit voice 30 seconds after the fact. So if you look at bandwidth on the internet, it's video, 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 audio, video, audio, video, voice, Zoom, video, 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 and that's why it's all going to be UDP. Mohammed Zoabi, a question related to the last session. What are the purpose of areas in OSPF? We've got to segment our network somehow, because if not, and go back to yesterday, we talk about all these LSAs coming in from everywhere. LSA, 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 LSA. If we don't segment it, and then each time we get a new LSA or an LSA is withdrawn, we've got to run the Dijkstra algorithm or the shortest path first algorithm in the routers. And that's computationally very expensive. And if we don't segment our areas, what happens? We have so many LSAs coming in and out, our network will actually break, our routing break, and then our network will crash, and we will have nothing. So we have to make sure that we optimize the routing, and optimizing the interior gateway protocol is what those areas are about. If we don't use it, we will have catastrophic outages, and I've seen so many organizations that have. Chris, are there any others? Angela, so trying to stream TCP, if it were possible, it's not just that it would lead to network congestion. That's not the problem. If I say 1, 2, 3, 4, 5, and I need that to be in order, and I send it via UDP, if you hear 1, 3, 4, 5, it's fine. Or if you hear 1, 2, 3, 4, 5, it's still fine. But if I do 1 and 2 gets lost, and 3 gets lost, and 4 and 5 comes out, and we're using TCP, after 4 and 5, we're going to retransmit 2 and 3. And now I've got 1, 4, 5, 2, 3. It's out of order. We can't retransmit things that we don't want to be out of order. So if I'm sending you a movie, imagine you're watching a movie which has to be UDP. You've watched 5 minutes of it, and then 5 minutes later, something from 5 minutes pops across your screen for 3 seconds, and then you go back. That's what would happen if we used TCP. It would literally basically just throw stuff. Now let's talk about the way voice and video works. So the way voice and video works is as follows. You would think that right now we're digitizing every move that I'm making and sending it to you. You would think that's the way video encoding works, but it's not. I'm sitting here. Now, right now, I'm here. If I open my mouth, what really changes? Now, we're capturing 30, or actually, I think I'm streaming to you at 60 frames a second. So 60 times per second, there is a little mini change. My mouth may open and close once per second. And in the process of doing that, there'll be 60 frames. So instead of taking a picture of me and sending each 60 frames, what do these voice over IP codecs do? Unified communication codecs, video codecs? They send the difference in each frame. So the first frame is my picture. The next frame moved over, moved over, moved over, moved over, move over, move over, move over. So you could send that whole 8 meg picture each time because I stream in 4K, or you could just send the little difference between each thing along the way, and that's what's going on. So because of that, because we're using a compression algorithm for our video that's based upon sending the delta between frequencies, whether that be voice or video, it's called a codec. Right now I'm using an H.264 codec to stream at you right now. I am. And because of that, we've got another issue. So I can't say something and have the old stuff come back before the first place. That's the problem. Imagine I don't know anything about this American game called football. So I know that people run a ball from one side to the other, and they're big, strong people, and they each try and keep each other from getting to the side. One of these days, I'm going to learn this game. But imagine if there was a play that after the touchdown occurred, which I think is the good thing, there was a tackle that kept them from getting the touchdown. It's automatically having to get everything in order and not watching and not replay. That's why we're dealing with these things. Okay, and I see you responded that it makes sense. You got it. So perfect. Chris, we can go to the next one. What about when you download something and get a smaller size? That's totally unrelated to anything. That's the way your storage system on your computer stores it in blocks on your hard drive. I know hard drive storage is not block storage, but it always stores it in a block. So that's just typically the way that works. And when you're dealing with real-time data, it's always sent via UDP instead of TCP. And it's not because of the time. We can't have old data retransmitted. If I want to buy a stock, 1 million shares of Cisco at XYZ price, and the price has gone up, if I try and make a bid at the old price, it won't be filled. Or if I try and sell at the wrong price, it won't be filled. We have to have accuracy to the data. That's why things are done. Real-time things are not done in UDP, in TCP. They're done in UDP. Chris, are there any others? Margin, how do you segment those areas? That's something we did yesterday when we created area border routers, and we actually did that. So, Margin, what I would say is go back to yesterday's video, and if we have time towards the end of the week, and I hope we do, what we can do is we can do like a little mini CCIE lab, and we can build a big network, and we can have some OSPF and create some areas, and we'll redistribute some EIGRP routes, and maybe we'll run some IBGP and EBGP on top of it. If we have the time, we'll do it. We'll call it a CCIE day. Make sure you guys are all super capable. Okay, so before we get into the next topic, everybody type #CCNA, and we're going to get into access control lists, and this is going to be fun. We're going to get into some security principles. So before we begin, everybody type #CCNA, and then I know you're all here. I'm looking for some CCNAs when I see enough of them. Danica CCNA, Alexandro CCNA, Eric Stoltz CCNA, Marjan CCNA, Eugene CCNA, Brian CCNA, Chakot CCNA, Sarah Ahmed CCNA, Mohammed CCNA, and Felix CCNA, Marty CCNA, Sajar CCNA, fantastic, Beta.1 CCNA, and Mr. Gee CCNA. Love all these CCNAs, Angelo, Jim Weaver, CCNA, and Ruth CCNA, and Reginald Duncan. I'm so happy to see you, as well as Mr. Businessman, and Nike, so happy to see you, and Abigail, so happy to see you here today. Leo Paredes, CCNA, and Neil CCNA, and Jeannie. Well, good, the three of these, Jeannie CCNA. Earl Owens, William Burnham, so thankful you're here, William, as Eva Doika, and Anthony Benjamin, well, as Elvis. Andy, I'm so happy to see you. Daniel Mitchell, you're all here. This is fantastic, FM Merkel, and Sharon J. So, loving all this. Pierre, I haven't seen you in a couple days. AK, good to see you. And Roberto, my good friend and amazing voiceover IP architect and cloud architect, good to see you. So super, super thrilled to have you all here. And now we're going to talk about access control lists, and we're going to have some fun with it. So let's say you want to keep your system secure. Who doesn't want to keep their system secure? I know I do. I know you get to my house, I got an access control list blocking room to room. I mean, so what are access control lists? Access control lists are a means to give the network engineer, the network administrator, the network architect, the cloud engineer, the cloud architect, a means to keep data from going to places they don't want it. When we create access control lists, we can look at things like the TCP port. Whether it's TCP, UDP, ICMP, we can create a filter to allow what we want and block everything else. This really gives us some options. So when we're dealing with IP version 4 access lists, they're usually used for packet filtering. But with these access lists, which we're going to create, We're going to use them for everything. We're going to be creating access lists and matching them up to route maps. We're going to be creating access lists and matching them up to BGP policies. We're going to be creating access lists for policy of policy of policy. So access lists can be used for lots of different reasons. Now, they may be called certain things such as distribute list or filter list, but effectively they're all kind of an access list. And you put an access list on a router to basically keep traffic out of a subnet, for example, just like you would use an network access list on the cloud. So when you hear a cloud provider talk about a network access list, just realize Cisco had it 40 years ago. So when we're dealing with access control lists, they're usually used to keep control access, but we can use them and we may show you excuse me, how to mark traffic to say Mike's traffic is more important than Cindy the cat's traffic, although more likely we'd be marking Cindy the cat's traffic as higher priority than mine because Cindy is the queen of the household. She runs it. She sits by the door, looks at us, tells us what she wants. So she's the royalty. So we've got that. But that's what we can do. We can use access controllers to protect subnets, to filter routes. We can do it also to mark traffic, to prioritize it. We'll have lots of fun with it. We can use it to mark traffic high priority for quality of service policies. Now, when we're dealing with access control lists on routers, we apply them to an interface as a rule. An interface. And we apply it to inbound traffic on the interface versus outbound traffic. So what are we talking about when we say these kind of things? Let's draw it out for you. So let's draw the difference between inbound and outbound traffic. Let me give me 1 second. I'll make a little whiteboard environment for ourselves. And then after I make a little whiteboard environment, I'll share my screen. Okay, so let's do this. Let's draw a new slide in. So let's pretend we're here. Let's assume we've got a router over here. Router. And we'll put R on here so you can know it's a router. Circles are routers almost exclusively. And we've got these two routers. And let's pop a link between the routers. Let's put an Ethernet segment on this last router. This is the traditional way that Ethernet segments are just drawn. Okay, so now we've got our Ethernet segment. And now let's put another Ethernet segment over on this side. So first thing, every one of us, assuming we don't have any loopbacks, how many subnets do we have here? We've got this LAN segment, we've got this WAN segment, and this LAN segment. So everybody, what's the minimum number of subnets we can actually have in this environment? Minimum number, type it in the chat box. And then after this, I'll show you what you do with the access control list. What's the minimum number of subnets, everybody, that I can use in this particular environment? Jim Weaver, 3 exactly. Sarah Ahmed, 3 exactly. 1 for the WAN, 1 for each LAN segment. Leo Paredes, fantastic, 3. Sejar, well, it's 3, but okay. We'll get there. Nike, fantastic with 3. LM, 3, I'm loving this. Mohammed Zabay, 3. I got a couple of monitors. Bear with me if I'm searching to see if you guys are answering it. But you guys got it. It's 3, so good. So now let's pretend you're a PC over here. Actually, I'm using Windows. I really prefer my Mac. I'm really struggling with Windows. I've got this beautiful 64-core computer with like a half a terabyte of RAM. I miss my Mac. So let's pretend it's a Mac. And the Mac wants to send its data into the network. So no big deal. Cindy the cat is on my Mac. She wants to send data from her computer to Abigail's here. So Abigail has the most beautiful cat called Noni. So let's say this is Noni over here, which I probably misspelled. So Cindy's on my Mac and she's trying to send a message to her friend Noni on the Mac. The data, and we're going to walk through everything that happened. Let's say Noni's got a website over that's full of pretty kitties. So the first thing that happens is Cindy on her Mac does a lookup, www.nonithecat.com. She gets the IP address of Noni the cat. So what happens next? Cindy's computer, Mac, says, ARP! Who has the MAC address of Noni's computer? This router says, I have the MAC address. Then, and we're going to add the access control list. And then the packet makes it to the router, and the router says, who has the next hop to Noni's subnet? And it says, go to this router. And when it gets to this router, the router says, hey, how do I get to Noni's subnet? And the router says, I have it directly connected. ARP! Who has the MAC address for Noni? And Noni says, I have the MAC address for Noni. And then Noni looks back in her routing table and she says, my friend Cindy's over there in Florida. I'm over here in North Carolina. Do I have a route to Cindy? And she says, no, but I have a default route. So she says, ARP! Who has the MAC address? And this router says, Noni, I got the MAC address. It's mine. I'm proxying for it. So the packet comes to the router. And now Noni says, do I have a route? The router says, do we have a route in our routing table that says to reach Cindy the cat's MAC? Yes, we do. Send it here. Packet gets here. And now what? Now the router already knows the MAC address. And Abigail's cat, Noni, and my cat, Cindy, they're sharing pictures of balls. They're sharing pictures of their shrimp. They look a little alike. They're real cute. They're having a great time. Now let's talk about the way this TCP. So this is now Noni's web server instead of Noni the cat. Here's going to be the flow control, and then I'm going to show you how we can use access controllers. Cindy the cat already knows where to go. She sends her packet here. She sends her packet here. Packet arrives at Noni's web server. Packet arrives with a sequence number of 1. Noni's server says, I got your message 1, acknowledged 1. Oh, by the way, I would like to open a connection with you. So the packet gets forwarded to this router, goes back here. No, Cindy's computer says, Noni, I see that you saw my connection. I see that you asked me to open a connection. I'm going to say yes and open that connection. And now what do we have? We have established a TCP session over the network. This is going to be a TCP session. So let's go over here. This is going to be a TCP session. TCP. Now what's going to happen? Let's walk through. We're going to walk through the TCP flow control. After we walk through the flow control, we'll play with some access list. Cindy sends a message request. Noni sends her the packet back. Over here, Noni sends the packet back to Cindy. Cindy's on the computer and says, I really love that photo, but I need more of it this time. So she sends her request, and Noni sends 2 packets back. And now that's why it's a bigger arrow. It's 2 packets. And she sent it back. And Cindy's like, oh, I love your pictures. Things are really good. Let's go back. Let's turn it around. So Cindy says, yes, I got your messages. And Noni says, okay, you got those messages? Now I'm going to send you more data. Noni sends a little more data. And the message gets lost along the way. Cindy doesn't acknowledge it. No, no, no. Noni says, Cindy never got my message. Let me send her a little data and check. So she sends 1 message. And Cindy says, got it. And she sends her message back. And Noni's feeling a little better. Well, she got the last message. Maybe it was just a hiccup in the network. So she sends 2 messages. And then Cindy says, got him. And then Noni's like, okay, life is good. So she sends a couple more messages. And Cindy says, I've got him. And this will occur the entire time the session occurs. They're always going to look for the perfect amount of data to send. Now let's talk about an access control list. Now we've got Cindy. Let's get the word Mac off. Let's just call her Cindy. We got happy little Cindy over here. This now wants to reach out to her friend Noni. Now, let's say Cindy's IP address is this. Now, let's say Noni's IP address is this. Let's say we've reserved .1 for the router. Now, let's say Noni over here has a website that is on HTTPS. So HTTP S, which happens to be TCP port 443. I want you to understand what's going to happen to understand how we can do this. So what's going to happen is little Cindy is going to send a packet. And what's going to happen is the packet's going to have, it's going to have the source address, it's going to have the source port number, and it's going to have the destination address, which is going to be the 192.168.1.2. So it's going to be the destination address, and it's ultimately going to have the destination port, which is the dest port. Can anybody tell me what the dest port is going to be here? For HTTPS is going to be 443. So what we can do is we can put an access list that on this thing that says allow Cindy, allow 10.1.1.2 source port whatever to reach Noni on TCP port 443. Now, if I've got that as an access list to permit, and now Cindy tries to reach Noni on port 80, it's not going to work. If Cindy's IP address is not what we told them that it's allowed, Cindy won't be able to get on the network. So an access control list is going to look at the packet. It's going to look at the TCP header, the ICMP header, the UDP header. It's going to look at the source address and destination address. And it's going to work that way. And we'll have plenty of time playing with these things. But I just want you to understand it. That's what an access control is. Now, we have two ways that we can control an access control list, inbound and outbound. So if Cindy wants to send a message to Noni over there, Cindy goes to the computer and it has to send it to the router. Then it has to leave the router. Then it has to go into another router and out of another router. So inbound is this direction, entry into the router. So when we apply an access list, we can apply it inbound or outbound. So let's think about this. Inbound allows Cindy's subnet on the network to reach Noni's subnet. Outbound allow any of this traffic to reach Noni's subnet. So it's just whether we're letting it into the router in the first place or whether we're letting it out of the router. So access control lists can be applied inbound and outbound, and should be applied inbound and outbound. Inbound to control your traffic in one way, outbound to control it another way. Control your traffic in multiple directions, and you will have a fantastic high-performance, high-security environment. So let's kind of walk through access control lists and how they work. Access control lists take an action when a match occurs. I'm going to say this again. An access control list takes an action when a match occurs. So what happens when we configure the ACL, there's going to be a logic. Match this source address. Match this source subnet. Match any source address to reach this destination server, this destination subnet, etc. What can we allow? We can say, Cindy can talk to Noni, or Cindy can't talk to Noni. Maybe Cindy was a bad girl. Maybe Cindy brought her daddy a squirrel and dropped off the squirrel's head in her daddy's bed, and her daddy was very upset that day. So I might put an access control list to say, Cindy, you can't talk to your buddy Noni that day, because I would be frustrated with Cindy. Now, Cindy's the princess, and thankfully Cindy hasn't done that more than once, but I just want to make sure that kind of makes sense. So that's what we're really talking about. Is an access control list really any different than a bouncer at a bar? You're allowed to come in. No, you're not allowed to come in. Is it any different than when you go to Disney World and you have a ticket and they look at your ticket to see if it matches? And when you leave, they stamp your hand and you have the stamp in your hand, you can come back. It's the same principle. It's just admission control. All it is. So let's talk about these kind of ACLs on Cisco routers. Now, I didn't make up these names. We have standard ACLs that are numbered from 1 to 99. We have extended ACLs, which are from 100 to 199. We have these additional ACL numbers that we can use from 1300 to 1999 for standard ACLs, and then 2000 to 2699 for extended. I didn't make it up. And guess what? We've got named ACLs, which is, instead of giving an ACL number, I can call an ACL noni. And we can improve our editing with some sequencing numbers, which we'll talk about. We're going to first start by beginning basic access control list. And we'll milk some. What I want to tell you is first, the logic. ACLs are processed in order. I'm going to say this again. ACLs are processed in order. What happens is the ACL uses a first lodge magic, meaning if a pattern matches a logic, the first action is taping and then stops. So imagine if you had the first line that says deny everything, and then the next line that says permit Cindy from speaking to Noni. Well, what happens? Data comes in, deny everything, thrown away. We'll never get to the point where it says Cindy can talk to Noni. Now, by comparison, permit Cindy to talk to Noni, block everybody else. That's going to work. Now, when we talk about ACLs, we're going to talk about logic and flows and numbers and sequence numbers. I'd like you to think about this. If I created a rule, for example, that says rule 1, block, let Cindy talk to Noni. Rule 2, deny everything. Now, what happens if Abigail over there gets a cat called Garfield and I get a cat called Spike, and Spike and Garfield want to talk to each other? Okay, so the first line of that ACL was allow Cindy to talk to Noni. And my next line was deny everybody else. So now let's say I went out a third line. And the first one is let Cindy talk to Noni, deny everything, and allow Spike to talk to Garfield. What happened? Cindy got to talk to Noni, everything was thrown out, and now Spike can't talk to Garfield. And Spike is sad, and Garfield's sad. So, Spike is, rubbing up against my leg, saying he wants to talk to its friend. And Garfield's rubbing against Abigail's leg, and it's staring at her with sad eyes because she wants to talk to her friend Spike, and they can't. So when you make an ACL, rule 1, allow Cindy to talk to Noni. Rule 100, block everything else. Give yourself room in your numbers to manipulate things and move things, edit them. Because whatever you think you need now, I promise you, you're going to need more. You buy one dog, you realize how nice the dog is, you buy 2 dogs. You have one cat, the next thing you realize you have 2. You have one computer, at some point you need 2. You think you need 2 servers in a data center, you need 22,000. You think you need a 1 gig link, a week later you're at up 100 gigs and you didn't even realize it. So give yourself room. That's what we experienced. Architects will tell you. Whatever you think is going to be small, won't. It's going to grow beyond your wildest dreams, and you're then going to be like chasing a tail. So kind of keep that logic with things. So now let's look at what this kind of looks like. Let's make an access control list. I haven't done one of these things in a really long time, so let's play with one. Let's make a router. Let's work through and have some fun. And Abigail, if you're ever thinking about getting a cat Garfield, I'm sure they'd be friends. And let me tell you, I keep thinking about getting a cat named Spike. Been thinking about it for a while. So let's go to our EVENG server that we had, and which I actually think I was crazy enough and closed that window, but we'll figure it out. Bear with me. Okay, we're in the server. Now let's see. Can you guys see it? Oh, woohoo! You got it right. This is fantastic. Love it when a plan actually comes through. So
Cindy closed it, not you.
Yeah, she opens and closes things. She does all kinds of cute stuff, and thrilled to have her with whatever kind of help she wants to provide. Okay, can you see that full screen now?
Not yet. Still, it's not widescreen on the browser.
On the browser, but is it in StreamYard?
Yes.
Okay. So let's come up with let's create a new lab over here. We'll call it ACL lab.
I think you have a second one open that you're.
Oh, maybe that's what's going on. Yes, I do have a second window.
Yeah, the one you're on now is the one that we're seeing.
Okay, so thank you.
There you go.
I knew something wasn't right.
Yeah. Big brother, big brother's here to help.
Thank you. I really did need that. So let's see if I popped it in here, and if not, I may not. Okay, so is this? So let's create out an object. We'll add 2 nodes. We'll add 2 routers. And we'll set ourselves up an access control list. Build 2 routers. And of course, by doing it this way, we'll turn it into a full lab. We'll get better at our network engineering skills. And while we're at it, we'll turn on some routing. So, whatever we do, we're always going to make sure, we try and give you guys as much stuff as possible. So let's turn this one on, turn this one on. Let them boot up, boot up, boot up, boot up, boot up. Okay, have a little bit of fun over here. Start is done, selected node. So far it looks like things are working. We'll come up with these things, let them boot up. Set up a nice access list, show you how it works. We'll do some standard access lists, probably some extended lists, some named access lists. They're still booting up. They're a little slow. Definitely on the slower side. But we'll get to our goals. We'll have some routers. We'll have some fun. Actually, while we're there, if we're all having a good time, if you could type CCNA while we're waiting for the Cisco routers. We all know me, and I love all my things in chat boxes that kind of keep me awake, alert, and oriented. Okay, for this one, we're going to type no on both of them. No. We'll go to this router, and we'll go no. Good job, Margin CCNA, Marty CCNA. Okay, fantastic. I'm loving it. We're all here. I love when I see these CCNAs coming across the screen because I know you're here. Love knowing you guys are here. We put a fair amount of time and effort into putting these sessions together, and we do it for you. We want to know that you have the best career as a cloud architect, cloud engineer, network architect, network engineer, network administrator. But it takes a lot of effort. So if we know you're out there with the CCNAs, we kind of love it. Okay, so let's name our routers here because, of course, we're going to have some fun with them. How do we name them? We go to config T. Why config T? Config terminal. How do we name the router? There's a host name command. We'll call it R1. We'll set an enable password, which is like the super user password. We'll call it Cisco, which is not what you should ever use on a router because it is the most commonly used password on the internet for these kind of things. After that, let's make sure we can telnet or SSH into these things. You know me, I'm all about making sure every router has a logical address that won't go down called a loopback. I like my /32s for these things. Now we got a link over here. Let's between 1 and 2. Let's put that interface int G0/0. No shutdown. Now let's put an IP address on it. 192.168.1.1, 255.255.255, 252. This is called IP subnet 0. That's what we need to know. So if we use .1 on the /30, what's the other side? Should be .2, which we'll do in a minute. Let's just put some routing stuff on here. OSPF1, network. We can do 1.1.1.1, 0.0.0.0, which means exact match. Let's tell it to be in area 0. If you guys want and we have time, we can do a little mini CCIE thing in the end to make sure you guys are really good, far, far above anybody else that ever took any other CCNA program anywhere else. And then we can do a network statement, 192.168, 8.0, I'm sorry, .1.0, 0.0.0. And if we do a .3, that's going to match the subnet of 0, 1, 2, 3, and 4. And then we'll pop that in area 0. Guess what? That's pretty much all we need to do on this. We'll do a copy running config starter config or write memory, whichever you want. And that's going to take us to saving this configuration. Now let's go to the switch or router on the other side. Enable gets us to privileged executive mode. Config T gets us in the ability to configure it. Then what are we going to do? We're going to give it a host name, R2. Now it says R2. After we do that, we're going to set a root password, which is the enable password. We're going to call it Cisco. Now you really should type service password encryption on this, and I'll show you why. Later we'll show you this, but we'll do that for right now. Then we'll put a loopback address on this because we don't want any addresses on these things that can go down when we manage them. We'll give it another /32 IP address 2.2.2.2. Really easy to remember, 255.255.255.255. That's called a host root or a host address. We'll do a no shutdown, even though it looked like it already went up. Then we'll go over to here to interface G0/0. Then we'll put the IP address on it, IPP ADDR. Remember, it was 192.168.1.1. So what's this one going to be? It's going to be .2, 255.255, 255.252. No shutdown. So this interface will turn on. Then we need to enable some routing. Actually, we should, before we do that, we should enable the virtual terminals. Line VTY 0/4. Why? I have no idea why they came that way. Input all. Okay, so now let's just enable some routing. Put the loop back in there. Hopefully I didn't make any typing errors because I've got some pretty bad arthritis and my typing is not always the prettiest thing. Let's just put it that way. People from my team can tell you. .0.0.0.Stubby3, area 0. Let's see if we did this right. What should happen is we should see an OSPF neighbor adjacency change come up in a minute. Let's see, is it coming? Is it coming? If we do a show IP OSPF neighbors, don't have any. Why not? So let's see if we get a neighbor adjacency on their own. And if not, we'll have to figure out what I misconfigured, because obviously I would have misconfigured everything. So let's look at our interfaces. Show IP interface brief. Are they all turned on? They look turned on. How about on this thing? Show IP interfaces. Okay, that's up. Can we ping across the link? 1.2. Yep. Okay, so we can. So let's look at our running configurations and see what we missed before we add any access cliffs and break things. Triple A new model. Okay, Ceph. Got our loop back. We've got our addresses over here. But okay. We misconfigured the OSPF for this statement. What we did is we put a 0 instead of a .3. Wait, Rajan, good job. Good job. You noticed that I got the host mask wrong. Thank you so much, Marjan. That should fix it. Ah, look at that. As soon as I changed that, you saw that OSPF adjacency changed on the other one, on the other router. So let's make sure it works. If we're on router 2 and it works, we should be able to see the loopback address on router 1. Show IP root, and it should be the 1.1. So let's make sure we can reach it. And if we're over here, we should be able to ping the loopback. Okay. Ping. Make sure we can reach the 2.2. We should be able to. It's in the routing table. Okay, so we've got perfect connections. Now, let's say, for example, let's do a ping, and let's source the protocol IP, target IP address 2.2.2.2. Now, let's source the address. Sorry, I missed that. Change the source to 1.1.1.1. Note, we sourced it from 1.1.1.1 all the way to 2.2.2.2. You're with me, right? So now, if we were going to configure an access list, we'd have 2 places where we could do it. If we had a PC back here, we could put it on the inner interface, but we could also go outbound. So let's say on this interface, let's create a basic access list. And how do we do it? We're going to do config T. We're going to do access list 1, and we're going to permit. We can look at it this way. We can put any host if we wanted to, or we could do a specific host. Let's say 1.1.1.1, for example. But let's just say we do any. Well, let's just not do this. Let's just permit and then after this, for example, let's say we want to permit something else. So let's say we wanted to permit 192.168.1.1. Let's permit .2.2.2. That's all we've permitted. So that's actually, we don't even need to do that. So let's go there. Now, what we want to do is we want to pop it in to an interface. So if we pop it into this interface over here, what's the interface? So what we would do then is we go to our interface. So it would be interface G0/0. And when we're here, what we would do is IP, access, group, and then it's going to be the name of our access list, which was 1. And then we're going to apply it in the direction and in. Ping, local IP, target address. Oops. Ah, did you see that? Did you see that? OSPF went down. Why did OSPF go down? Why did OSPF go down? Did I block anything important? Was there any kind of thing that I didn't permit? What did I permit in this? Show IP access 1. What are we permitting here? Look at it. I'm permitting 1.1.1.1 to reach 2.2.2.2. And I'm permitting this host. What am I not permitting, everybody? Can anybody tell me this thing that I didn't permit? 224.0.0.5. I did not permit 224.0.0.5. If I didn't permit 224.0.0.5, what did I break? Well, static routing. Does static routing cause a problem? No. But I blocked 224.0.0.5. Who says hello on 224.0.0.5 every 10 seconds? Hello. 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 OSPF. Did I allow the IP multicast group 224.0.0.5? No. So Alexandros, you're mostly there. We didn't allow OSPF through. So can routing work? Now we're not going to be blocking it anymore. Wow, I removed the access list. Did you see that? OSPF. Woohoo! It came up, 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 up. Okay, so might there be something wrong with my access list? Did I potentially block OSPF? I did. So, no OSPF, no neighbor relationship, no routes, dead. So what did you see? An overly restrictive access list that basically took down an entire network. I took down the control plane of a network with one access list. I lost all my routing with just one access list. That's when we start thinking about cloud environments and a cloud provider says, hey, you can stick it all on my one cloud by multiple availability zones and regions. You can break everything with a single access list if you're not careful, no matter what kind of network segmentation you do. That's how fast you can do it. And it doesn't take that much of a mistake, which is why we use 2 internet service providers. We always recommend 2 cloud providers. And when you buy private lines, you never buy both private lines from the same company because it's pretty darn easy to do that. So, just look at that. Now, if we do show access list 1, maybe if we did this, I haven't configured an access list now in a very long time. Because that's what happens when you leave engineering to architecture. You get hands-off tech and you do heavy-duty design stuff. So now let's pretend we did this. Config. So bear with me because we're doing it on the fly and I haven't done this in a while. Let's do no access list 1. Now let's do access list 1. Permit 224.0.0.5. Access list permit 224.0.0.6. Access list permit Now, I haven't made one of these, so my syntax could be potentially a little wrong, so I shouldn't demonstrate this live, but I'm going to do it anyway. You can see we've got a neighbor adjacency. Now, what do we have in this access list? I've got permit 224.0.0.5, which is for OSPF, 224.0.0.6. I've got my loopbacks and my WAN. So if I didn't make any mistakes, which is quite possible that I made a mistake over here, but if I did, so let's do this. Access, is it IP access group, or is it, yeah, it's IP access group. IP access group 1 in. Let's see. So right now, I mean, we haven't lost our OSPF, so we should be able to ping anything we want. We can check that by pinging 2.2.2.2. Still reach it. So the key is what's going on with our neighbor adjacency over here. Still up, it's still full. The dead time is 32, 31, 36. See, now that we've permitted the control plane or the routing protocol, everything is just perfect and we don't have any problems. So that's really what one of the things that I wanted you to see. An access list is your security friend. It is your security friend. But do you see how easy it is with one little mistake on an access list to totally break a network? Now, if I had done that on a core router, it would be rippling through things. Now, they would reheal around me, but depending upon the router, one access list like that can really do it. So I also wanted you to see this. So this is what's called a standard access list. Why? It's just destination only. So it's basic. But now you can see how we do a basic standard access list on Cisco. Now what we'll do is we'll do different kinds of access lists next, but I figure that was a good chance, a good, relatively good lab. Maybe we should see if you guys have any questions, make sure that everybody's doing good before we go to the next top, before we do more access lists. So I want to make sure everybody's doing great over here. Oh, here's my thing so I can see the screen. We've got like 3 monitors and 6 screens to try and do this. Are there any questions for me? We could actually definitely use a wildcard mask. No, when I was putting OSPF, when I use 0.0.0.0, that means exact match. And 255, 255, 255, 255 means permit any. So a wildcard mask is used differently in 2 different things. But yes, wildcard mask could be to allow multiple addresses or all addresses or an exact match. Yes. Good questions, AK. And I will demonstrate some more of them. Eugene. What do I think of GNS3? It's a fine little simulator to do some things. It's not like this. This is EVENG. Cisco's got one, which is good. This is one. I personally use EVENG for the following reasons. We can run our Cisco devices with our Palo Alto devices or Fortinet devices or Checkpoint devices, and we can connect this to multiple clouds and multiple networks. So Eugene, EVENG is a tool that people use in all kinds of big companies because it enables, if like AT&T, for example, might use it to figure out, if they design something for a customer, does the routing going to work? Is the switching going to work? Is the MPLS going to work? Is the tuning. So this is used EVENG by big organizations, big companies like service providers, big manufacturers. And they use this because it runs the actual software identically. DN3 does a lot, but this enables you to scale, connect it to clouds, connect it to your networks, run ICSIs through it to really even load test your virtual environments. So I think GNS3 is a fine way to learn. I've used it in the past with students. I like this better. And the Cisco one I also like better. So I view GNS3 as like the freeware thing that's out there, which is okay. The Cisco one is basically a better version because Cisco made it. And EVENG is made by people that are building systems for the world's largest technology companies to test things. So knowledge of EVENG is a good career skill too. So I'd rather see people use EVENG. There's a free version of EVE-NG, which is basic. And there's the full professional version like this, which isn't that expensive. I got to say, I love EVE-NG. But if you can't afford it, the GNS3 is perfect. But it's like $100. It's not a big expense for the software. So I just love the EVE-NG. Network, bro. EVE-NG is a pretty lengthy to set up, but once you get it going, it's awesome. Yeah, you know, I'd say that's a really good way to describe it. But I think when you actually know how to set up EVE-NG, it's pretty easy. So I'll tell you my perspective. I started with it. In fact, 2 of us were working on it. I had the entire server up and running in, I don't know, 30 minutes. Now, here's what I'm going to tell you, Network Bro. It was up and running, and I had absolutely no idea how to create my first lab. And for this, I had to call a buddy of mine, and the buddy of mine had to say, well, actually, you know what, this thing? No, we got to fix the permissions here, or it's going to be buggy. Oh, wait, we got to fix the permissions here. And then being shown by a professional how to set it up, it was the simplest thing. So what I would say is EVE-NG is an incredibly good product, but it's got no documentation worth talking about. And GNS3 is buggy and is much simpler to get set up if you're not used to it. But EVE-NG, especially the pro version, can enable you to test things and learn things, run your own CCIE labs. I mean, it's amazing. When I did my CCIE, I spent $200 every Saturday and Sunday for 6 months straight to run a rack. It was a fortune. And I can do better with EVE-NG. It's a better product in every way than those racks. I actually don't even use live routers anymore when I teach things because this is so much better. I might actually just bring in a couple of live routers for people to just plug in a console port to see what it's like to connect to that 9600 8N1 with a serial port, and then be done with it because this is just so great. But I love it. Can ACLs be stateful? Well, routers aren't really firewalls. So we can create a pseudo-stateful ACL, but not exactly. We can trick it. So what Angela is actually asking is state. And here's what state is. If we take a firewall, my iPhone's my firewall. I want to go to www.gocloudcareers.com, my website. I go for my desktop, www.gocloudcareers.com. Then my computer sends it through my firewall and it goes out to the internet. Now this firewall, which happens to look just like my iPhone, says, I'm watching this and this is Mike is going out to this website. And when that website answers, like we just showed you with the TCP connection, and it comes back, the firewall sees it and says, yes, that's Mike going to gocloudcareers.com. You allow it in. Now my next request goes back to gocloudcareers.com, and then gocloudcareers.com comes back to me. I go back out to gocloudcareers.com, and gocloudcareers comes back to me. The firewall knows to allow my return traffic because why? It watched and saw it was coming from me. The firewall saw that I initiated the traffic, and it let my traffic come back. That's what we mean by stateful. It's like the security guard watching you come out, come back in. When you go to Disney World and you leave, they stamp your hand. When you come back, you show them the stamp, they let you back in. It's that security thing that's stateful. So access control lists as a rule are not stateful. Now, Angela, we can kind of trick the ACL a little bit, but it's not great. So let's go back to this process. Noni's out there. Noni's a very beautiful little girl. And Cindy wants to go see Noni. So Cindy goes to www.nonithecat.com. And when Cindy's message goes to there, it goes out that access list. So Cindy sends a SYN or synchronize or open message to the Noni the Cat's website. Now, when Noni the Cat's website responds to Cindy the Cat, Noni the Cat, when she responds, it looks like this. I acknowledge you, and synchronize here. So because she used the word acknowledge, I acknowledge you, we can trick the firewalls, the routers, to using this command called establish. And what establish means when Cindy the Cat gets on her computer and she goes to nonithecat.com, Noni the Cat comes back and it has that ACK number, and the access list can look for that acknowledgement and allow it back. So it's not exactly stateful, But we can do ACLs in one direction with these routers because we can use that establish function that allows our traffic to come back. But it does not provide the level of security of a full firewall, which is why, we use firewalls at the perimeter, and then our IDS IPS systems, and then our access list, et cetera, and we will use multiple layers. But that's a fantastic question you asked there. Does it run in a VM? Oh, you mean this EVE-NG? Actually, it literally launches all routers and container and routers and either their own virtual machines or containers, and it is really, really cool. It's basically a whole cloud when you install it. It installs all the hypervisors and your container engines and databases. The same way if you would build an OpenStack cloud, it's very similar. It's a very robust package. Check multi-vendor, multi-cloud architectures with it. It's fantastic. How do IPs on different subnets connect to each other? Fast, that's what routers do. That's what we have those routing protocols. Routers just take you from one subnet to the other. Mufaz, that's a really important question. We actually spent about 2 hours doing it on the first day. And Mufaz, I want to make sure you get that. Please, please, please go back to the first day. And Mufaz, I think you're also one of my students. And if that's the case, please make sure in the next class, which will be not next week, but the week after that, we do another big routing demo. But please watch that first video soon, just in case. But if not, for some reason, we'll have a big multi-cloud network architecture day. And on this big multi-cloud network architecture day, not only will we connect to 3 clouds and set up all the cool BGP, but we'll show you the routing part at every hop along the way. So let's make sure we take care of that either way. But please go back and watch that first one first. Can you configure access control lists on switches? Mufaz, what a great question. On a layer 3 switch, we can configure layer 3 access control lists that look just like this. But you know what else we can do? We can configure layer 2 access control lists on switches and literally restrict MAC addresses to MAC addresses. That's the kind of security we can never get on the cloud, but we can get in our data center. We can restrict MAC addresses. And Mufaz, you know what else we can do? We can even use something called 802.1x authentication, which means when you plug your computer in, if the computer's MAC address is not recognized by a database of allowed MAC addresses, they don't get on the network either. So yeah, we got some cool stuff we can do on switches. Very much so. Chris, are there any more?
No, that's it.
Okay, well, first, I want to congratulate all of you guys because this is 6 days of networking. And I know it's not easy to do 6 days of networking. I've done 25 years of it. But I know when you're initially doing these things, you're overwhelmed. So let's make some more access lists. But before we make all these access lists, everybody, hashtag CCNA in the chat box. It perks me up. And if anybody knew the kind of days that I have, I need some perking up from time to time. So since we talked about numbered access lists, basic numbered ones, now let's get involved into some other things. Actually, let me show you the ACL real fast for the EVE-NG server. I want to show you some show commands that I probably should have shown you before. So let's go back over here. Admin. Let me just show you one more command that I wanted you to see. And we can see even what's going on with it. So that's how you can see the access lists that are there. That's how we can look at it. Just there's that. So I didn't go over that before. I meant to show you that. So I wanted to make sure we did so. So now that we've configured a basic access list, let's talk about a way to try and maybe make it understandable. Because I don't know about you guys, but if you've ever shown up on somebody's routers, and when you get to routers, this is what you see. pretty much you're going to get to a router. You're going to be able to do a show IP route, and that's going to show you the routing tables. Then you're going to see what's on the router with the show running configuration. And this is going to show you things. And you got to see, this is not the most descriptive thing in the entire world. But, you know, we might want to be a little more descriptive. So what if we just take, can do this as we're going to remove this access list again and pop it back in. E0/0.
Are you sharing your screen? Okay.
So if we come over here and we remove this one, no IP access group 1 in. We get rid of that. Now let's config T. We're already here. No, let's do IP. Let's get out of here so I can use the tab. So we got rid of, we didn't. Oh, I think. Okay. Okay, so we got rid of this, but let's do it this time. Let's make this access list a little differently. Let's do the first time. Let's do this. Access list 1. Let's describe what this does. Allows Cindy, OSPF to reach Noni. Now, at least if you see this, you're going to be less confused when you go back to this. And now we can obviously pop in, you know, we can pop in the same access list. We literally speaking could cut and paste the same commands in, which is exactly what we're going to do. And then we'd go reapply it to the interface G0/0. And we always apply these things, IP access-group 1. And let me make sure, I always check my IP access group 1. There you go. And even someone like me that's been working with networking stuff for 25 years, I always double check my configuration because it does that. Now I'm more of an architect, so I don't really configure things that often these days, so I definitely want to double check. But always, you've got a sanity check in these machines. Don't put it in your head and assume, because trust me, you'll make these mistakes. I do it all the time. Others do it all the time. That's why if I'm going to configure things, I literally type out my commands ahead of time in Notepad, and then I can just cut and paste them in and watch and make sure they work there. So let's now get into a different kind of access list. Now let's talk about extended access lists, whether they be numbered. We're going to talk about extended numbered, and then we'll talk about name later. And you could see lots of questions on this for your exams. So we just did standard access lists. Now extended give us a little more. We've got a lot more control of the access list. So if we really wanted to be able to talk about good logic, source address, destination address, protocol port numbers, then we're actually going to use an extended access list. Reality is, I don't think I've ever used a standard access list for actual security. I think they've all been extended because, you know, we've always needed a little more control. But, you know, on these exams, they have standard access lists. But it's really what the parameters that you can talk about. So let's talk about what these parameters realistically can be. So What we're really talking about is the protocol source and destination IP. The extended ACLs let us do that. In fact, the syntax is pretty much identical, at least up to the permit or deny keyword. And at that point, that's when the command changes a little bit. So your extended access command requires 3 matching parameters now. The IP protocol type, TCP, UDP, ICMP. Source address, destination address. There you go. So the IP headers protocol field will tell you about that. And, we've shown you that before, but, let's go back to it. I think we've shown you a diagram that looks like this, where you've got your header, which is your protocol. Your checksum shows you to make sure nothing went bad. We show you the source IP address, the destination IP address. And there you go, your basic kind of information. So realistically speaking, that's what we're talking about. So what's the syntax going to be like then? Well, it'll be more like a access list 101 or access list 110, deny TCP any, or permit TCP any, or access list whatever 10 or 110, deny host 2.3.4.5 going to host 2.6.7.8. It's really about that. It gives us the ability to just have some fun out there and do this. So these are the kind of parameters that are going to more make sense to you. So let's go do it. Let's play with it. Let's go back to our servers and let's just look at our options here. So let's go over here. Let's go back to this group, to this router. We'll go to the interface G0/0. We'll get rid of that no IP access group in, which is how we apply the access list. It's gone. While we're at it, the access list we left here isn't doing anything, but just for argument's sake, no IP access list. I think it's 1. Oh, let me just tab over. Standard, and then it should be 1. That's gone. So now let's create an extended access list. Same kind of thing. How are we going to do this? Let's say we did an access list 101, but they start with 100. Now let's say, what do we got? We're going to permit something, right? We're going to permit whatever we want to put in here. See, we can do it. Let's say permit OSPF, any source address, any destination. So we're going to allow OSPF, so now we shouldn't have any routing problems. What else do we want to do? Let's permit we want to permit. Let's say ICMP. Source address 1.1.1.1. Source destination wildcards bit. Let's make it an exact match. Destination address 2.2.2.2.
Hey, Mike, you need to share your screen.
Thanks, Chris. Okay, so let's do this. Let me just delete anything that I just started to do there. No access list 101. Okay, so you'll be able to see that let's verify that there's no access list in this router. There's none, so we can see there's none. Now, instead, the last time, what did we do? We created a standard access list. Now, here, we're going to create an extended one. So how are we going to do it? Like anything else, we're going to go to configuration mode. We're going to go to access list. In this case, we're going to have to use a number greater than 100, 101. So let's say we permit. Let's look. So now we can figure out what we're going to permit. OSPF, we can just tell it to permit OSPF. Isn't that cool? Any source addressed. So any source addressed. The destination address we really know is going to be 224.0.0.5, but let's just leave it as any. And then let's just let that go. So we've permitted any of the OSPF stuff, and that way we don't have to worry about whether it's 224.0.0.5 or 224.0.0.6. Now, while we're at it, let's allow the loopback address to reach 2.2.2.2. So let's see what we've got over. We can do permit, let's say ICMP. Let's to the from the source address of 1.1.1.1, the loopback, right? Source wildcard bits, we can leave it the same as an exact match. Destination address, we can select any. Now, what else we could do? We could have also selected 2.2.2.2. What else should we select at this point? We should select the 192.168.1.1 destination to any. While we're at it, let's just add the 2.2.2.2 because we're using exact wildcards. Setting interface, gigabit 0/0. Now we'll still apply it the same way. IP access group 101, it should be in. Let's see if we broke anything. Do a show IP OSPF neighbor. We're still full. We should be able to ping 2.2.2.2. Ah, now look at that. Let's see what happens if we source the ping from 1.1.1. We broke something. We didn't permit something that we needed. That's how granular this gets. That granular. Let's play with it. See what were to happen here if we were to do this and we went to access list 101, permit IP, any. If it changes anything. Now we could. So we obviously needed something more than what we were blocking. So we had ICMP. I sent an ICMP echo. Did we need to allow maybe something else? That's the key. And that's what happens when you do these things. So when you do a show access list, show IP access list, you can usually see 101. You can usually look at the map. You can see that OSPF packets were getting through, but our ICMP messages weren't. But you can also see that once we hit the permit any, those were my 5 ICMP echoes. Watch what happens if I send another ping. It's gonna that match is gonna go up. It went from 5 to 10. I'll send another ping in case you missed it. You can see which rule you're actually hitting. Now, I just allowed everything through because I have to diagnose what that actual thing is that we needed to interact, because it's ICMP, but it's also something else. You just wouldn't apply in any like I just did by any stretch of the imagination. But it's the concept. That's what you need to do. So when you're setting up your protocols, and this is why we proof of concept a lot of this in labs, and that's why people love these EVE-NG servers, because they can do it all in the lab. They can look at their traffic flows, and then we can see this. We can figure out what we were missing. We can see it on a protocol analyzer. We can see it in NetFlow switching. When we know what we got, we can go, whoa, that's what I need to allow through. So that's part of that network discovery phase, which they don't talk about in your CCNA, CCNP, CCIA things that you will be doing is, what is that actual stuff coming through your network, what it needs to be. If your application developers truly know it, you're in good shape. But whether you're on the cloud and you're looking at VPC flow logs to see what your security groups versus your access list block, or whether you're on routers using Cisco NetFlow, you're going to be doing the same thing. So we'll keep that in the back of your mind for a little while. Let's look at some more things that we want to show you through here. Let's show you how you would do these things the more intelligent way with a wildcard, for example. So let's just work through this one more time. I want to show you how we could use some wildcards. Okay, so let's assume we wanted to do it a little differently. So let's say we had an access list. Let's say it was access list 101. Permit. First thing we got to do is make sure our routing works, otherwise we're broken. And
Mike, you're not sharing your screen.
Again. Thanks, Chris. So let me just do a note of that. Oops, didn't mean to do that. So let's do. Let's take the same command. Let's remove it. Control A. We can start fresh. So we should have show access IP. You can see we've got no access list. This time, let's configure that access list a little different, so you can see a different approach. So let's do an access list 101. Let's do a little bit. Let's tell you what this is. Remark allow Cindy cat treats. I don't know. Now we know what it is. So now with access list 101, we're going to permit. We obviously have to access list. We have to give it a number 101. We're going to permit. Make sure we permit our routing protocols because that's our control plane. We lose our routing, we lose everything. Now, in this particular case, let's say we've got a bad guy or girl we want to block. We see we're getting hacked from a different thing. In fact, let's do that. Let's just block this one bad actor. But while we're at it, if we've got a bad actor on a subnet, let's just block that whole subnet. So let's try it. We got a bunch of people trying to hack us. They're all on this 172.16.3.10 subnet. So let's block them. Here's how we're going to do it. We're going to do an access list 101 deny TCP. Let's say over here, let's say a source address. Let's say 172.16.3.11. Let's say that's an address. And then let's say we don't want to let them get to the destination subnet. So let's say the destination subnet is 2.2.2.2. And all we have to say is we have to figure out, so let's make sure we do this. We have to give it a match. Apologies. So do we want to match this destination address or the whole subnet? We're gonna match the whole subnet. So let's do a 0.0.0.255. And then when we're done this, let's tell it what we're gonna block. block a specific port. Okay, let's say which port we want to block. It gave us port numbers. Let's pick one that we want to block. Let's block port 80. Web traffic. And let's say the destination address is, let's give it 2.2.2.2. That's what we're denying access to. What the heck am I missing? Wildcard. So this is going to be an exact match. So when you look at this, what do? We're going to block a bad subnet. And in this particular case, we're going to allow everybody else. So let's talk about when you would do this. Now look at this logic over here in this access list. The first thing we did is we told our routing to work, okay? The next thing we did is we blocked this subnet from talking to this web server. And then we allowed everything else. So let's think about this. Let's assume you're in a company and you've got an intranet server on a private subnet. Let's say you want everybody to access that private server, and you don't want access lists on your internal routers. But you've got one subnet where you've got a couple of kids, and these kids, they get a little rowdy, they drink too much, like to do some funny business after hours and listen to music after hours. And while they're there, they occasionally hack into the systems. So you're the network administrator and you say, no big deal. Those guys on that subnet or those girls on that subnet, they can't reach our web server. Everybody else can have it. That's all that is. So that's really what we're talking about with access lists. Like, these are not like military grade firewalls. This is not a Cisco firewall. This is not a Palo Alto firewall. This is not a checkpoint firewall. This is a basic packet filter. And you use it because if they breach your firewalls and your IDS IPS systems, it's something else you got at layer 3 before you do your layer 2 access list. It's just about layer after layer after layer. But we're going to use lots of access lists for lots of other reasons. So that's why we're walking through a bunch of these things in a ways that I want to make sure that you understand it, the point of them, because there's a lot of other reasons. But it's really about making sure that we deny what we want and then permit everything else. Or permit what we want and then deny everything else based upon the use case. Now, we showed you standard access lists and we showed you extended access lists. Now we're going to get into something called a named access list. Look, I didn't make this up by any stretch of the imagination, but let's do this. Let's get on this router, get rid of this access list, no IP access list 101. You have to say extended. Spelled the number. All right, so we got a clean router all over again. Now we'll just talk for a minute about named access lists, and then we'll have some fun with them. So we have the numbers 0 to 99 for the basic packet filters, and 100 to like 199 for the more advanced packet filters. And now we've got names. So a named access list pretty much is the same as a numbered access list, except we name them instead of numbered them. So we have the standard ACLs that have the same fields, and we can do extended ACLs would have the same fields. And it's basically, we've got our option with the named access list. So it's basically any kind of access list you want. When you use a name, and the name says allow Cindy to communicate with Noni, it's easy. You know what it is. When you use access list 101, you don't know what it is. So with access list 101, I said access list 101, remark, Cindy can talk to Noni. And then the access list 101, then specify your logic. Because that way you would know what it is. And that's what the older network engineers like me did. We used standard and extended access list. And around that time, I guess it was, maybe 11.3 iOS or 10. Something. It was one of those early iOSs that I used to work with. All of a sudden, we had named access lists. Maybe it was even before then. And then we could give them a name, Cindy Talk Noni, or whatever we wanted. And that's really all it is. So a named access list is effectively the same thing as a standard or extended, just a named way. And we do them more this way as some sub commands as opposed to global commands, which makes them much easier to edit when you need to edit them, which is a very good thing. So we'll talk about what this actually is and what it looks like. So we're going to create one. And it's going to be so simple. And you'll see it's just a new version of the old thing. Isn't there a song I think it's The Who? Meet the new boss, same as the old boss? Well, meet the new ACL, same as the old ACL, but with a new number. Okay, so in this particular case, let's say we're going to create an IP access list. IP access dash list. We're going to tell it, right? Standard extended, but we're going to go extended. Now here, instead of the number, we're going to call it Cindy the cat. I mean, most people like Cindy the cat. Even dog people like Cindy the cat. So now notice we're in ACL configuration mode. So let's say what we want to do. Let's say we permit. What do we want to permit? OSPF. We don't want to shut down our routing protocols now, do we? So we're going to pick any source host. Let's just say any destination host. And let's leave that. No OSPF. You've seen that happen. You see how bad that is. So I wanted you to see that because I wanted you to see how you can shut down the control plane with a moment's notice and totally destroy a network. So now let's go back to over here with, you can see what we've actually done over here. We created an access control list. How did we do this? We did it as following. Actually, I don't think I actually shared my screen when I did that. So let's redo it again. Sorry, it's hard to actually see many as many screens as I actually have things popping in to try and do this. So let's do this, config T, let's get rid of this, no IP. Okay, so we have no access list. So let's create a different kind of access list. Let's create that named access list. So when we create this named access list, we're going to have to do it. Give it a name. So IP access dash list. Remember, you got to tell it standard or extended. Now here's how we name it. So we're going to call it Cindy the cat. Seems like a happy name for an access list. Now let's make sure routing works. So what do we have to do? We're going to permit OSPF, any source, any destination. There we go. Now let's say we want to do a few more permits. Let's say we want to permit 1.1.1.1 0. Permit IP. I think we should specify a source, 1.1.1.1. Destination. Wildcard bits, let's make this an exact match. Destination address, we can say 2.2.2.2 because what we've done. Destination, we can say that's an exact match. And then you can set it. So this is going to permit anything from 1.1.1.1 to talk to 2.2.2.2. So Cindy the cat and Noni the cat, those two can talk to each other and they're very happy. Now we have to make sure OSPF works. So did we permit OSPF? Yes, we permitted OSPF. Yep, you see we permitted OSPF. So now we've got OSPF and we've got the 1.1.1.1. Now let's say we want to deny a certain subnet. So deny. And then we can say, we want to block a whole subnet. So let's block anything this one subnet tries to do. So we can say 192, let's not use them, 172.16.1.0. We don't want any of these people to be able to reach anything .255. We're going to deny any of them to reach anything. Why? These are some bad people. They're hackers. They've been trying to hack us on the subnet. We're blocking them all. So we allowed one. We denied this subnet. Now let's say we got another subnet full of bad actors. We want to block them too. Block that subnet. Let's block another subnet. Block another one. Let's permit everybody else. Now let's look at the logic of this access list. What are we doing here? We're allowing OSPF. We're allowing our SYND and NONI to talk to each other. We got rid of these bad actors, these bad actors, these bad actors, these bad actors, and then we allow everybody else. So this is a very common kind of access list you're going to see on your internal network. And what do? You apply it to the interface. How do you apply this to the interface? You apply it to the interface like this. Interface G0/0, that's the interface's name. Okay, IP, it's access group, access-group, and you name it. Now we have to remember the name. Does anybody remember the name? Let's make sure we get the name exactly spelled right, because if you spell it wrong, and we spelled it Cindy the cat, which is not the hardest name for me, remember, and then we tell it to go in. Now, what do we think is going to happen? Do we think OSPF is going to work? Let's see. Show IP OSPF neighbors. Oh, well, we still have routes. Is the timer going down? You can see it should go down. 38, 34, 32, 31, 39. Okay, hello. Now watch what happens. It'll be, let's see, 33, 31, poof, 39. So what happens, you got that reset timer. Whoa! 40, 39, 38, 37, 36, 35, 34, 33, 32. Hello! 40, 39, 38, 37, 36, 31, 30. Hello! And it does that. And that's why what you're going to see here is we're going to see a decrement. And then, poof. You see it's going to degrade, 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 and degrade. And wow, the timer reset because it got a hello. Don't believe me? Debug, IP, OSPF. Hello. Let's watch it. Let's see what goes on. Every 10 seconds, send hello. Receive hello. Send hello. Receive a hello. Now remember on that access list when we didn't put OSPF in there and this broke? Because this is the kind of traffic on the wire. And this is when we talk about from an architecture perspective, it's not about knowing how to configure the access list for we architects. It's about knowing what that traffic actually is. Because if you don't know what that traffic actually is, you're going to break it. Engineering-wise is very different. It's more how to build it. But in either case, the more you know how it works, the better it is. Hello. Every 10 seconds. So when people talk about a health check in DNS, guess what? It's no different than this hello. Hey, I just responded to the health check. I like to say, are you there? Now guess what's going to happen? Hey, I'm here. You there? It's the same thing. Keep alive for your Ethernet port. Are you there? Health tech for your DNS or for your load balancer. It's all the same. It's the same. So let's do this. No debug all. Hopefully we got through that. So you can see what we're talking about. Some of the things with the access list. Let's talk about a couple more things about access lists, and then we'll get some hands-on time. Now, actually, this is a pretty cool. It's a pretty cool feature of these named access lists. So, show access. Back to the Cindy the cat. What we can actually do here is we can actually do a no for one of the commands inside of this access list. I may have to actually turn off the access group. Let's see if it lets me do it this way. So now if we do the show access list, we were able to remove that line. So it's kind of one of these situations where it's pretty cool, where you can edit and remove and add things. So now if I wanted to do and edit a rule 21, a rule 22, a rule 23, it's pretty easy for me to do. So as I tried to mention before, this is, a router has an access list, which is a basic packet filter. It's not like what you're going to put on a firewall. So the firewall is going to be big and stateful and have deep packet inspection, but this is just basic filtering. And that's why we're going to use the firewalls, the perimeters of the network, our IDS, IPS systems. We're going to use ACLs to protect certain subnets, etc. It's a combination of all of these things and rules that we're going to be using. So just keep that in the back of your mind. Actually, before we do some more configuration, let's see if there's any questions, Chris. Are there any questions from the group?
Yes, sir. There's a couple.
Okay, let me find my StreamYard browser real quick, so I can answer that, so I can see it. And bear with me. Where are all these windows? Where do they all go? Nope, not that. Not that. Okay, Chris. Well, I can't see StreamYard, so if you want to ask me the questions, Just ask me the questions. I don't know where that other window went. Oh, wait, I found it. Okay, Chris, if you want to bring in the questions. So for those of you that are out there, I've used a Mac forever. And I recently switched over to Windows, and I can't find anything on it. So it's just a little bit of a challenge. So apologies. Gus, the engineer, is it better to configure an access list on the router or firewall or on both? Gus, that is a great question. You must do it on both. See, the firewalls are deep, strong security, and the access lists are just a little bit, but the more you do that. So the way security is, it's like an onion. You have to make it hard to get through the first layer and the second layer and the third layer and the fourth layer and the fifth layer. I have 10, 15 layers of security in everything I design. And access lists are everywhere. Firewalls are everywhere, from host-based firewalls in the systems to firewalls at the perimeter of the network. And sometimes I even have different parts of the network firewalled off from each other. So, and then of course I'm using access lists too. So it's definitely a both. And that is an exceptionally good question. And that's one of the things that I think is the hardest lesson for people new to tech. Everybody wants to know which is the one thing that I use, and there is no one thing. It's the, I have a little of this, a little of this, and a little of this, and marry those two things together. That's really what makes a good architecture. Great question there.
And that's the only question that we've had so far.
Wow.
Now,
Well,
of course, you answered some that were coming in during the walkthroughs. So.
Okay, well, I'm either, guys and girls that are out there and everyone, I'm either doing really, really good, in which case you have no questions, or if not, let me know, because I want to make sure you're there. So we'll keep walking through the technology. If you're here, if you can type hashtag CCNA for me, that way I know you're awake. Let me just see. Okay, so you know what? Let's get involved in some security stuff. Security stuff is usually fun. Love security. So let's start to talk about security architectures. We're going to talk about some concepts, some elements, and we might walk you through some security architectures. And in fact, if you guys want a security architecture, I can walk you through a security architecture, which includes the full elements of firewalls, routers, switches, etc., that kind of thing. So let's go through some basic terminology. We're going to talk about vulnerabilities, exploits, and threats. And a vulnerability is going to be as follows. Something that's a weakness. So you've got a martial artist. They've got a bad foot. That is a vulnerability. They can be, their foot is a place that's kind of there. So a vulnerability is a weakness. Every organization has weaknesses. Everyone. It could be the people, the processes, or the technology. There is always a weakness, and a hacker will be good at finding it. So now you know what a vulnerability is. It's a weakness. Now let's talk about an exploit. An exploit is something that can be used to take advantage of a vulnerability. It's typically a tool. So I'm a martial artist. I see a person's got a limp. I don't want to die. I go for that ankle. It's dirty. But that's not the way I would compete in an event. But that's the way war would be done. You see your enemy. You know your strength. You know your enemy. You know their strengths and weaknesses. You attack your enemy that way. And a security attacker is war. Someone trying to attack you, and they will go after your weaknesses, and they do that with exploits. That is how hacking affects a terror. Buffer overflows, DDoS, exploits. And the threat is the actual potential to break in, steal, or otherwise modify anything. So let's think about the threat. What is the threat of someone trying to hack cindythecat.com? Well, a lot, now that I always talk about cindythecat.com. But other than that, nobody's going to want to hack cindythecat.com. Why? What are you going to get? Photos of her curled in a ball? Photos of her making photos? photos of her curled up in my lap, photos of her drinking water out of my glass on the kitchen table, which is embarrassing as can be. Photos that my wife took while the cat was sleeping on my face and I could barely breathe because she was, I mean, I don't know. You're going to get photos of Cindy the cat. Now look at it this way. What's the threat to AWS or Azure or Google? Great companies, right? What's the threat? If I hack into them, I get access to every one of their customers. Hacker jackpot. I hack into AWS and I get access to a third of the internet. Wow. So that's the threat. So what we have to do in technology is AWS needs 100 or 1,000 times the protection to not die every day of a hacking event than Cindy the cat does. Maybe 1,000,000 times more. So what do we have to do? We have to make sure that we solve our weaknesses. We have to make sure that we've patched ourselves and really positioned ourselves well against the weakness that we have so they can't use an exploit to attack us. And then we have to actually see what is the risk that we have. And we have to secure something based upon the risk. So if I've got $1 billion asset, I got a lot of security. If you look at a billionaire walk down the street, they have 5 to 10 armed guards with them at all times. They are in a car that has bulletproof glass, bulletproof steel that you can shoot at them with a rifle and it can't penetrate it. They have roll flat tires. Why? Because that's the threat that they're dealing with. Likewise, Cindy the cat. Nobody cares. So keep that in the back of your mind with every security architecture. What are we doing? We don't spend $1 billion to protect a $10 product. But if our intellectual property is worth $1 billion, we might spend a few $100 million to protect it, because if we lose it, the company's out of business. So that's what we're kind of talking about. We quantify the threat. So let's talk about some of the attacks. We'll first talk about attacks that can spoof an address. So what do we mean by this? So for example, if I was going to impersonate someone, I would actually impersonate their address or their phone number. You know, I wouldn't have, for example, a message that was theoretically coming from my phone that wasn't coming from a phone number, because it would be unbelievable to anybody. No, it wouldn't be believable if my address didn't come from an address that made sense too. So attackers can spoof their address, their MAC address or their IP address in certain ways. And by using fake values, now we've got a problem. So let's say I decided that I want a high security enterprise, and I've implemented 802.1x authentication, which only allows certain MAC addresses in. And somehow the hacker got a list of the allowed MAC addresses, and the hacker faked his MAC address to be one of the allowed ones in. That attacker would get in. Now, if that attacker didn't know what my allowed MAC addresses were, and they plugged in, they wouldn't know how to spoof it. But the point is, attackers are always on the lookout, performing reconnaissance, searching for data they can find a little bit with a ping, a little bit with an ICMP, some trace routes, a little bit of things from some Kali Linux or Parrot Linux tools, a little bit of Google, a little bit of LinkedIn, a little bit of YouTube, a little bit of Facebook, and you've got the ability to do some damage. It's not that hard. And any one of you, realistically speaking, could go out there on the internet, get Kali Linux for free, and figure out how to hack half of these things that are out there. And you know what? When we train cloud security architects, a lot of them I like to go play with those Kali Linux tools just to learn how to use them. Not that we'll ever do that as an architect, that's what engineers do, but when you know how to hack into stuff, you know how to secure it. So kind of keep that in the back of your mind. So, you know, a spoofing attack is a little bit like a man-in-the-middle attack, or can be. So for example, if I think I'm communicating to something and it's the wrong address, that's kind of a bad attack. So spoofing attack is the attacker pretends to be someone that they're not. We believe them, we let them through our firewall, we let them into something because they have the address that's allowed in. Not a good situation. Now let's talk about a DDoS attack. Now this is one of those kind of attacks that occurs that a lot of us networking people aren't super familiar with, because this is more of a security thing. But, you know, I've worked with these for decades, so let's talk about them. What is a distributed service attack or denial of service attack? I want you to all understand this context. Let's say you've got a web server, and it's cindythecat.com. And Cindy the Cat's a pretty strong web server. She can get 5,000 requests per minute and serve photos. And if she does that, her CPU is within the normal limits, everything's working, the web server's coming across through. If she gets 6,000 web requests, the CPU's at 100%, DRAM's maxed out, the drive doesn't have any more ability to do any more disk I/O. And what happens is everything comes to a screeching halt, the server crashes or reboots, and the web page isn't served. That's kind of a problem. That's called denial of service attack. What is the denial of service attack? Quite simply, you ask a server to do more than it can do. That's it. You're just overworking a server. So that's what a denial of service attack is. Attack a server and ask it to do more work than it's capable. Okay. So that's a denial of service attack. Now, what's a distributed denial of service attack? It's a little different. I'm a server. I now hack into a bunch of servers on the internet, and I use them to launch an attack on you. Okay, so I want you to think about this. CindyTheCat.com can handle 5,000 web requests per second. She's doing it. The server's purring nicely. Hey, maybe I could be a comedian. Not really, but anyway, I'm trying. So the server's purring nicely, and people request Cindy the Cat. They get their website, their photos, their videos. Everybody's loving Cindy the Cat. Cindy the Cat's happy. And then there's an evil cat out there. It's called Tom the Cat. Tom the Cat is an evil cat. He's a big, bad, scary cat. And Tom doesn't like Cindy because she's making too much money in her Cindy the Cat photos, and he's mean. So Tom goes to the local library, and Tom takes control over 30 servers. And Tom is going to basically send requests to the server from every server. And they're going to be bad requests. They're going to be pings of death. And they're going to be out there saying, I want your stuff. I want your stuff. Now, Cindy the Cat can happily do 5,000 requests per minute and make money selling photos and calendars and things. Now, this attacker, Tomcat, who's angry, he sends 100,000 requests from 20 servers to Cindy the Cat. Cindy the Cat's server is down. That's a distributed denial of service attack. Now, if Cindy the Cat web server could handle 200,000 requests per minute, and mean Tomcat was only sending 100,000 requests, Cindy's server will be still purring happily. Purr. You'll get your website. You still have room. So there's lots of ways that we can talk about preventing distributed denial attacks. It has to do with content delivering networks. It has to do with some DDoS protection. It has to do with firewalls, IDS, IPS systems, access control lists. Heck, even auto-scaling systems on the cloud, which can let servers add capacity as needed. But cloud architectures are outside of the scope of what we're talking about right now. But now you know what is a DDoS attack. Now let's talk about some other common attacks. Let's talk about some reflection and amplification attacks. And what are these? And this basically, you've got an attacker that sends packets with a spoofed source address to a live host. But here's the thing, the host isn't really the intended target. The goal is to get the host to reflect the exchange towards the spoofed address that's really the target. And when the host reflects the traffic towards that target, it's called a reflector. Now, the attacker might also send packets to multiple reflectors, causing the target to receive multiple copies of the same unexpected traffic. None of this stuff is good. And then what happens? The attacker is able to spend a small amount of the traffic to the reflector and then leverage some sort of a protocol or service to generate a tremendous amount of traffic. And that's why it's called an amplification attack, because you send it to a request, what do you call it? You send it to a reflector and you really push it with a lot of traffic, which basically amplifies the attacker's efforts and it disrupts the servers. And that's why it's called a reflection or amplification attack. And, these kind of things happen and they can be relatively serious. Now let's talk about the next attack. So Chris, who are my blue wrenches on the call? I see Eva Doikie's got a blue wrench. Do we have any other blue wrenches over there?
I'm not sure who I was on the call.
Okay,
it's YouTube, so
it's YouTube.
It's hard for me to tell.
Yeah, fair point. Okay, totally get it. So Eva Doika is out there with the blue wrench. Eva Doika is a very special student. She's one of the disciplines in our discipline program, and she's an exceptionally great cloud architect. So I want to have a conversation with Eva Doika. And because Eva Doika and I work closely on a lot of things, she helps me do some specialized research. I trust Eva Doika to tell her a lot of things. So let's say I want to talk to Eva Doika. And this is called the man-in-the-middle attack. I call Eva Doika, and someone pretends to be Eva Doika that's not Eva Doika. So I have this conversation with Eva Doika, or email exchange, doesn't matter. I'm telling her critical information, privileged information, telling her about the new programs I'm launching, the next kind of innovation. She and I are talking. But here's the problem. It's not Eva Doika on the other end of the phone. It's somebody else pretending to be Eva Doika. And that's scary. So now I've given my trade secrets to that other person that's pretending to be Eva Doika. That's called a man-in-the-middle attack. And guess what? It happens all the time on the internet. We've got something pretending to be a server, but when it's not a server, it's somewhere pretending to be the server, and it's stealing your information. So that's a man-in-the-middle attack. Okay, Abigail is here as well. So I wanted to have a conversation with Abigail and Eva Doika. But now Eva Doika is who she claims to be. That it's not Abigail on the other end of the line. Kind of keep that there. Kind of keep that in the back of your mind.
Sorry about that. I couldn't see because I was trying to tell by the chat box.
Oh, good. So, okay, so that's what a man-in-the-middle attack is. Somebody pretends to be someone else. Now let's talk about what a reconnaissance attack is. What do you think reconnaissance is? Recon. Search around. When people want to break into a building, at least in the movies, they case the building. They run around the building. They look around. They walk into the building. They see what the security is. What is a reconnaissance attack? Guess what? Do some recon. Look around. Use some tools. Maybe you're using a tool like an NSLOOKUP to find out the domain name. Do a little bit of whois and dig commands to figure out, the DNS tools, the DNS records. The DNS servers. Can you hack into these DNS servers? Can you do some ping sweeps to kind of map the network? Can you use some of your Kali Linux tools to figure out what's going on? These are what you're going to do. You're going to run some part scanners, etc. You're going to do recon. You're going to look around. That's what a reconnaissance attack is. It's not for the major attack now. You're looking. Why are you looking? You're looking for vulnerabilities. You're looking for weaknesses that you can exploit. Recon. It's search. Recon. Now let's talk about buffer overflow attacks. We've got our operating systems and our applications. And what happens is these things, they read and write data to buffers, which is basically temporary memory storage. And we've got these buffers where one system communicates to another, and then we have it on our Ethernet frames or network. It's all over the place. The problem is some of these buffers or these temporary memory spaces have some vulnerabilities. It's going to allow these buffers to overflow, which means some of the incoming data gets placed in unexpected memory locations if it goes beyond the limit. Now, that's the thing. You put it someplace where it's supposed to be. It's great where it's supposed to be. But you push too much in there and it gets out, now you can cause a crash or a hacking event. So that's what's going on is the attacker basically creates an exploit that sends data to the buffer that's way more than it's expected. And if a vulnerability exists, the system might store that data, overflowing the buffer into another memory area and cause a system crash. So it could also be done by crafting an especially large message and putting some code in there as well. Now you know what a buffer overflow attack is. Okay, so let's define some more stuff. Let's talk about malware. Got systems, you're designing security architecture on every server. Doesn't matter if it's Windows or Linux, you still need some malware protection. And what is malware? Malwares are Trojan horses, viruses, and worms. and we'll talk about what those things actually are. So when you're dealing with a Trojan horse, it's basically some kind of software that's pre-packaged in some other kind of software. Maybe I download something to go see a picture of Cindy the cat, but you get some virus along the way or some other nasty software. That's a Trojan horse. And that Trojan horse can take an action later. Now, a virus is different. It's kind of like software that self-injects itself into other software and damages your system, which is different than a worm, which is something that hits a system and propagates itself on its own. So with the virus, a lot of times you got to click on it, download it and click it, but the worm will just replicate on its own. And these are kinds of things that we'll be dealing with. What else? So social engineering. This one's pretty easy. Abigail and Eva Doik. I picked out their names because I know them both very well. I have extreme respect for them. Got some great students. I'm also Marjan's fantastic. Robert Welch is fantastic. Jim Weaver's great. MJ, she's fantastic. Mark's fantastic. Oh, I love all my students, but you know they're the only names that I can actually see here. But I just know those two well. So if someone were to send them a message claiming to be me, you know, that might be influenced to do something if they thought it was me. So that's called social engineering. When you walk into a building and the receptionist sitting at the desk is a guy and he's a bodybuilder, and you can see that he's a bodybuilder by his protein shake, by the fact that his neck's real big and his shoulders are real big, and you say, hey, Joey, you're looking muscular there. You've been working out extra? I mean, you always look up at your, oh, yeah, I am. You know, Joey, I've been called like 30 times by this guy, Joe. And he's like, hey, funny, that's my name. And I'm like, I know it is. And he calls me every day, and he's got this emergency with his computer. I come down every day, and every day I come down, and he's never there. I'm so worried I'm going to get fired. Could you help me out? Could you take me to Joe's desk? Maybe I can. Sure. That's called social engineering. So, yeah, being able to manipulate people is kind of something that's out there. So these are really human vulnerabilities. Human vulnerabilities. Now, we talked about a reconnaissance attack. The whole world knows my cat's name is Cindy. Do you think for a minute I would have a password called Cindy the cat or anything with the word Cindy? Of course not. But I'm a security architect. But here's the thing. People do. Their daughter's birthday. Their mother's maiden name. The street they were born on or they lived on. Those are kind of one of those kind of things that you actually see. And, you know, we see this. Now, what else does the company say? We need you to have a 32-character password that's got these 42 special characters, this many numbers, lowercase character. And by the time you're done, do you think people can remember these things? Of course not. So what do? They put a sticky note of their password directly on their monitor. And when you see that, that's even more terrifying. So the point is that we deal with vulnerabilities. Are they related to our code? Are they related to our people? Or are they related to the fact that somebody stuck a core router in the middle of the room and all you got to do is plug a wire into it and you're on the network? It could be any of them. But human vulnerabilities, hugely important. Password vulnerabilities, aka Cindy the cat. So let's talk about some of these human vulnerabilities because they're so important. And whether you're a cloud architect or a cloud solution architect or an AWS solution architect or a network engineer or a cloud engineer or a security engineer, you need to know these. And generally speaking, if you're anyone that wants to have a good life and not get hacked every day, probably should know them too. So the first type of it is social engineering, and that's just realistically speaking, trying to manipulate people. The next thing is called phishing. And, you know, we all get these messages. Hey, it's your bank. Something's here. Go change it. You know, those are your typical phishing events. I get 10 in the day. I look at them and I'm like, well, thank God. Your headers are wrong. Your IP address is wrong. This doesn't work. Nope. So we all get it. Now, spear phishing is different. Spear phishing is like you want to go after the customers or employees of a company and you reach out to them. or you reach out to a bunch of high net worth people at the yacht club. You're looking for a subset of individuals. Now that's more like whaling. Whaling is targeting the billionaires or the super rich or the celebrities. Phishing is using voice calls. Smishing is using SMS text messages. I didn't make up these terms. Farming is using legitimate services to send users to a compromised site. And a watering hole is to target specific victims who visited a compromised site. So now you know the kind of human vulnerability attacks that occur. So how do we deal with some of this? Well, we talked about we'll deal with firewalls. We'll use IP, intrusion detection, intrusion prevention systems, and our next generation firewalls. We'll use lots of things. And we'll use access control lists, layer 2 access lists, etc., etc. But we also have this concept of AAA, authentication authorization accounting. Now, in today's modern world, somebody thought this concept of AAA, authentication, authorization, or accounting should be called IAM, Identity and Access Management. Now, whoever would make up a term like that, I have no idea. AAA, authentication, authorization, and accounting makes sense to me. Here's what this means, without all the complexities. Who are you? What are you allowed to do? And what did you do? So we'll go back with Eva Doikia. Eva Doikia decides that she's coming from Hungary to Palm Beach, Florida. Eva Doikia comes to the house. She's a welcome guest. My wife and I are so happy she comes. We give her her own room. We give her access to the car so she can have a great time in Florida. Now, when she shows up on the front door that first time, I'm going to look at her and I'm going to say, are you Eva Doikia? And if she's not Eva Doikia, I'm not going to let her in because she's not the person she claims to be. How might I do that? Well, I know what she looks like. I know what she sounds like. But if I didn't, might I check her passport, her driver's license and her passport, and 3 bills with her name on it from her power company over there in Hungary, for example? I'd be looking at what determines the level of authentication I need. What is the asset that I'm trying to protect? But she comes, I recognize her face and say, welcome, Eva Doikia. Now, Eva Doikia was a welcome guest. I gave her the keys to the car. I gave her a spare key to the house. She can do anything she wants in the house. And she's allowed to. Now, in my house, I'm a high security guy. I may have some cameras, etc., running around my house. I might have all kinds of firewalls, layers and layers of firewalls. I might have all kinds of cool security stuff in my house. Now, if I did, and I was able to track it. Oh, Eva Doikia went to the kitchen. Oh, fantastic. Oh, Eva Doikia made an omelet. I'm so happy. Eva Doikia found the feta. Really good. I brought Bulgarian feta instead of Greek feta because I wanted her to have Bulgarian feta around the house when she came to visit my family. And I can see that she ate the feta, which she did. That's called the counting. So what is AAA? Who are you? What are you allowed to do? Now, let's say somebody else came to the house. I decided to sell something on Craigslist. Person knocks at the front door. Who are you? I'm Jeff from Craigslist. Okay, Jeff. So come on in. Now Jeff enters my foyer. Now Jeff says, can I go to the bathroom? And I say, no, I don't know you. Jeff says, how about this? And I say, you can stay right here. I'm going to be monitoring you. You can check it out. And if it's okay, here's the money. Now, afterwards, I count the money. Jeff texts to make sure the product I give him. Jeff goes on his way. Wait, Eva Doikia came in. I gave her the keys to the house. I gave her one of the cars to use. Why? She has complete privilege, wrote, because I know her and I invited her. This other trade would be something very different. And Eva Doikia, that's true. You're welcome anytime. And this other person, I did not know. And because I did not know, here's what happened. I gave them a little bit of rights. When they tried to go to the bathroom, I said, no. I didn't allow them because they didn't have privileges. So they didn't have the rights. And when they were there, I had somebody standing guard the whole time. I trained to make sure I protected a different threat. Welcome versus unknown. So now let's walk through it and let me show you what it looks like. Hi, I want to log into cindythecat.com. I log into cindythecat.com and she says, oh, that's Mike. That's my daddy. He has allowed permissions to see any of my videos. I love my daddy. So I go to do this and she says, yes. She maybe gives me a token or permissions and I'm allowed to view it because I am allowed. Now, let's pretend this is a little different. Now let's pretend somebody logs on to the privileged page of Cindy the Cat and it's a guest user. And now they want to access the private behind the scenes Cindy the Cat photo. And they enter their username and password. And Cindy says, no way, Jose, no way. And she blocks them. Then Cindy sends an alert. Daddy, the scary person, was trying to get in and do certain things. AAA, authentication, authorization, accounting. Okay, what kind of IAM services are we dealing with? Well, there's really three. But in today's world, there's two. We're either dealing with a radius server, which is used for authentication of a router. I log into a router, it sends a request to the radius server. And the radius server basically asks for a username and password. We pop in the username and password or whatever. It sends it to the radius server. The radius server sends it back and says, you're in. Or we use Microsoft Active Directory. Now, typically speaking, for networking devices, we use radius servers. But we could also use Active Directory in today's common world. And Microsoft Active Directory is being used for domain authentication and enterprise authentication on and off the cloud and pretty much everywhere these days. So understand you'll be using radius for this. And understand that the other thing that you'll be using is going to be, what's the word I'm looking for? Microsoft Active Directory. There also is another protocol that about 100 years ago I used to use called TACACS Plus. And that was a Cisco proprietary protocol that separates each of the authentication, authorization, and accounting functions. It was secure encrypted over TCP port 49. It was a great protocol, but I have a rule. I use open standards and TACACS only works with Cisco, so I don't use it. Radius, by comparison, is a standards-based protocol that combines authentication, authorization into a single resource. It uses UDP ports 1812 and 1813, and it's not as completely encrypted. But here's the thing. TACACS is better, but most organizations are using Radius because you need to be using Cisco. And the reality is we might have some Palo Alto, some Juniper mixed with our Cisco, and we need to be prepared for it. Let's see what else we should talk about. Okay, so let's do this. Let's see if you guys have any questions before we cover any more topics. Anybody have any questions for me? Because we covered a lot about security in a very short period of time.
Not as of right now.
Really? No security questions? Wow. Okay.
None yet.
Okay. Well, if there are no security questions and everybody's doing great, Chris, I'll have you mute out and I'll talk about securing some network devices.
Sounds good. Let's take just a few seconds for the delay to make sure that nothing pops up.
Yeah, let's do that. Let's make sure that nobody has any more questions, because if you guys do, I want to answer them before we do. And let's see. And if not, we will go about how to secure network devices. Very quiet on the question side. So I hope everything's going well. Okay. Go ask the question. If you've got questions, please ask them because we'd answer them. I just want to make sure that you get a real classroom experience. Definitely not, Brian. Hash tables or rainbow tables, definitely not something you're gonna deal with the average CCNA, CCNP, or even CCIE. That's more security knowledge. Great question, though. Any others? Because it looks like Eva Doike had a question there. Oh, that question was probably about the hash tables and the rainbow table. Eva Doike, is it correct to say that the payload is the element we look at if we use Wireshark? That's where the data will be. Okay, great question. So when you've got your packet, you've got your header, that's your source address, your destination address, and the payload is what we're actually carrying. So if we put something in the trunk of our car or the boot of our car based upon what country we live in, that would be the payload. When we're dealing with the packet, the payload is the actual data. So yes. So if you're using a protocol analyzer or a sniffer like Wireshark, you'll see the TCP or the UDP or the ICMP header, the destination, the protocol import number, and in there you can actually see the data. And that's how we would actually use sniffers to see what people are actually sending on wires. And that's how hackers absolutely do it. Absolutely. And that will basically, that's what the hackers are searching for. Microsoft Active Directory, Sarah Ahmed, is what most organizations use to determine who the users are and what they're allowed to do and what they did on their systems. It is identity and access management or an authentication, authorization, and accounting server that's used by Windows computers and other devices. Radius is an authentication server that's used by network devices, again, to determine who you are, what you're allowed to do, and actually what you did on the network. The same as Active Directory. So I hope I answered that question for you there, Sarah. Because it's a great question. I want to make sure you understand. Chris, are there others? Gus, in my opinion, which is better? Look, I'm a network person, so I love working with Radius servers, but you know, Active Directory has a much more robust features and functionality. So, you know, for routers and switches, I'm always using Radius things, but you know, in the modern world, we're moving to Active Directory, and I'm probably even going to switch from Radius to Active Directory for the cloud that I run in my house, because I actually feel like it's a better solution for where I need to be moving forward versus to where I've come from. I love both, but I think Active Directory is more robust. So if I was going to be dealing primarily with these kind of routers and switches, I'd be using Radius. Now, if I was going to be using more of these like SDN kind of environments, like the Meraki kind of Cisco Meraki kind of thing, as opposed to the Cisco that are more of these cloud managed devices, realistically speaking, I'd be using much more Active Directory than Radius because it's more of that enterprisey, simple to manage feel. But that's a really great question, Gus the engineer. What are you trying to manage the identity and access of? That is a great question. Typically, if I use routers, Radius. What is the difference between authentication and authorization? So, sure. Hi, my name is Mike Gibbs. Here's my birth certificate and my driver's license. That is authenticating me. Authenticating is showing that you are who you are and who you claim to be. Now, I'm in a bar. And I don't really go to a bar, but I saw a movie and they have special rooms in bars where the big wigs are, that the really rich people are. And I go to the bar. And I want to go to the rich people section. And they look at me and they say, okay, you're wearing an Armani suit. You're wearing a Rolex or whatever they use to. So yes, you are allowed to the wealthy person section. You are authorized. I go to that same place. Nobody knows me. I'm wearing shorts, a ripped up t-shirt. I try to go to the wealthy person room and they look at me and say, nope, you are not authorized. So it's kind of like if you were to go to military base, based upon your badge, you'd be allowed to go to certain places or not. That's what authorization. So authentication is, who are you? And then authorization is, what are you allowed to do? Sharon, I hope I answered your question. And the accounting side of it is just, what did you do? Chris, if you want to bring in the next one. What will be the role of cloud security be architects like? Do they need the same level of knowledge as security admins? So ET, admins and architect knowledge is so different. Admin knowledge is this. How do I configure it? Only how do I configure it? That's all an administrator does is configure, configure, configure. So admins typically don't know a lot about what they're configuring. Engineers typically are the people that think about what they're building and have more knowledge about what they're building before they build it. And architects need to know all about how it works, but nothing related to how to configure it because they don't configure it. So the knowledge of the cloud security architect is completely different than that of the security admin. So for the security architect, it needs to be, how do I secure the environment? How do I orchestrate? What kind of firewall strategy do I need? Which is most likely virtualized firewalls that are coming from a marketplace. Because I'm using virtual firewalls, I need load balancers. Behind that, I'm going to use my IDS, IPS systems. What kind of functionality do I need? Okay, behind that, I'm going to use my access control list. I'm going to use my security groups. Then on my servers, I'm going to disable unnecessary services, install some anti-malware protection, add a host-based firewall, etc. I'm going to encrypt my storage, that kind of thing. That's what an architect does. Cloud security architects are going to be focused on that. Cloud security engineers are going to be configuring the firewalls. And the admins are basically going to be creating usernames and passwords and things like that. So ET, the cloud architect needs to know about 1 million times more about how the security works and how to secure an architect than an admin does. And admin needs to know about 1 million times more about how to configure it. So very different. Kind of like me, I'm a network architect. I don't configure routers at all. I did when I was a network engineer, but as an architect, I don't, which is why I'm fumbling my way through the command line. But as an architect like this, I can teach you the protocols, how they work at a level that most people would never be able to, which is why I'm doing it. So you know how to design the systems, because designing the system takes the most knowledge of how the systems work. Engineering is the most knowledge of how to build them. So architect, design a building. Construction crew, hammer the nails. Architect, blueprints. Engineer, hammering the nails. Admin, they're at the fundamental level, bricklaying, hands-on, configure. So I hope I answered your question there. Totally different levels of knowledge. And they are totally different careers. But it's a good question. And a misconfused thing. Chris, do we have other questions?
We don't have any other questions at this point.
Here's what I'm wondering. We've got some really good progress that we're making. And I'm looking at this. I think what we can do is we can have a really good, strong routing day tomorrow. And then I think on Friday, what we can do is we can probably have a relatively good lab day and make some fun with it. So if everybody wants to stop 8 minutes early, type hashtag CCNA and cloud hired. And we'll end 5 minutes early. And while we're at it, tell us where you're from. I love knowing where we're all from. I usually find these amazing because usually we get wonderful people from all over the world. I saw somebody in Mozambique. I know we've got people in Belgium and Hungary and Holland and the Netherlands. I love this. So let's celebrate the night. CCNA, cloud hired, CCNA and cloud hired. I want you all getting whatever job you want. Cloud architect, cloud engineer, and I love Cisco. And that's why I love doing the free CCNA, the CCNA 200-301, and really being out there to try and build your networking careers, your cloud careers. Networking and cloud, they're the same thing. Without the network, there is no cloud. The network engineers build the foundation of the cloud and the computers. Alexandros, Kalisperas, Jim Weaver, good to see you. Angelo stepped away, but I'm thrilled you're here. Mufaz being in Nigeria, I love that. Leo's in Brazil, I love that. Sarah Ahmed is from Toronto, probably from somewhere else with that name. Ibudaika is over there in Hungary, but she's from Belgium. I love that. UAE, Mohammed, I spent so much time in UAE and loved it there. Eric Stoltz, CCNA. Jim Weaver's in Indiana, that's fantastic. Brian, Michael, Philadelphia, that's where I grew up. LM, CCNA. Gus, the engineer, CCNA in England. I used to go there almost every week. ET, it's good to see you. LM's in Mozambique, fantastic. CCNA Mufaz, Cloud Hired, absolutely. Yes, Mibedike, yeah, I know you're Bulgarian in Denmark. Oh, Mark, you're in Scotland. I've spent some time there. Both Glasgow and what do you call it, Edinburgh. Sharon J, Chicagoland area. I haven't been there in a little while. Alex Evaristopoli. Halifax, PA. Wow. Mick B, Cloud Hired. I'm loving this. Dallas, top Cloud Hired. Robert Welch, fantastic. Chikoji, Cloud Hired, Dallas. I'm loving that. And South Boston, Eric Stoltz. Cloud Hired, Mohammed over there in the UAE sounds like a really nice place right now, Mr. Gee. It's actually like 55. It's actually almost cool in Florida. I could use a trip to UAE. Nike, good to see you, Cloud Hired. A man over Cloud in Delhi. That's great. Frank Marco, your wife is from Brazil. That's fantastic. Anya in Maryland. I love this. Mr. Businessman, I've heard you say we need to pick a specialty as an architect, network business security. How do we not get stuck in that specialty if you want to move up into business architect, enterprise architect? Well, Mr. Businessman, I want you to really think about this one step further. When we do management consulting, where we create business architectures or enterprise architectures, our value is the kind of digital transformation we can do for our customers. So I can practice medicine. Do you think my value is greater in designing solutions as an enterprise architect or a strategy consultant / business architect in healthcare than it would be some other industry? It sure is. So when I say pick a specialty as an architect, I typically tell you one of two ways. Pick a technology or pick an industry. So I happen to focus on building high availability systems. Now, I used to use that in banking. I was an expert on BGP. I was an expert on routing. I was an expert in critical systems. Why did I initially go to the banks? Because they paid the most. Who's going to pay more? A hospital that's got no budget or one of the biggest market makers on the NASDAQ? They'll pay anything because technology means money. And when you're dealing with these environments where a nanosecond of competitive advantage can equal millions and millions and millions of dollars a year, getting 10 extra nanoseconds because you have a guy like me is really great. So that's when you've got special people that focus on high performance, high availability systems, and that's what I did. Then later in my life, I realized that I could focus on an industry vertical. And I focused on the healthcare industry. And that was my first enterprise architect job, which was focusing on that. But Mr. Businessman, you can focus on an industry, solutions for transportation, solutions for retail, solutions for consumer products group, solutions for farming, solutions for banking. I don't care. So that's what I would do, Mr. Businessman. If you've got that as a long-term goal, I would focus on an industry vertical, master that vertical, and master the cloud architecture, and wow, you are one heck of an architect with a great career in any one you want. California Bay Area. I've spent a lot of time out there in San Jose and Santa Clara. Mr. Businessman, CCNA, I love that. Eva Doikya, we love you. Mike and Chris, we love you too, Eva Doikya. Tom Orpheus, it's so good to see you in the Netherlands. Danica G, thank you so much for this team, Amazing Bootcamp. I'm so happy. Sharon J, where haven't I been in my life? You know, the reality was this. I would be in 3 countries a week for work, and I got to meet so many wonderful people all over the world. I loved it. I got to see exactly how no matter where we went, we were really all the same. And I got to experience so many wonderful things in Dubai and Australia and England and all over Europe and all over Asia, all over the Middle East and South America and Central America, Canada. It's been a wonderful privilege to get to meet people in so many wonderful places. And that's why when I love to do this, I like to see where you're from, because it's so wonderful. In any case, I think we should do this. If you're not a member of our channel, please like, comment, subscribe, that kind of thing. It kind of helps. I'm excited to see you back tomorrow. We will have some fun. Oh, Felix, I'm so happy to see you again. Frank, you're welcome. So happy to see you. Nick B, thank you. And yes, thank you, all you Blue Wrenchers. Abigail Ivadoika, you have no idea how grateful we are. You're helping so many people throughout the world by helping us. Thank you so much, Blue Wrenches. So, have a wonderful night, everybody. See you back tomorrow at noon. Network hired and cloud hired. Take care.